Okay, so welcome everyone to this training seminar workshop on statistics for isotopic analysis. Today we have with us Dr. Petra Vaiglova, a lecturer at the Australian National University. Petra specializes in isotopic analysis from organic remains, plants, animals, humans. And she's not just applying isotopic methods, she's pushing the frontier forward in this analysis. You will hear more about it tomorrow in her seminar on a case study, very interesting recent case study of her work about zooarchaeology. Now, I met Petra many years ago when she was a PhD student at Oxford, and I was a postdoc in Athens. And it's one of these people that you meet and you think, wow, this person is going to have a stellar trajectory. And she did. And it's such a pleasure to have her here today. And it is an honor. Thank you very much for accepting our invitation, Petra. I want to say that Petra is a rising star, but I would say she's a star. She's not, I mean, she's still rising. She will shine even more brightly in the future, but she is a star. So again, thank you very, very much. Petra will talk to us about statistical analysis for isotopic analysis, but what she will present will have implications for other types of statistically analyzed material. Over the past several years, there has been a lot of criticism on this abuse of the p-value, of this overemphasis we place on p-values and statistical significance. So she will talk to us about alternative methods of interpreting our data. I will not say more about it. I'm also looking forward to learning. As a final note, this is the first of a series of training events we will be organizing in the context of the One Archaeological Science project. It's an ERA chair project funded by Horizon Europe. So stay tuned. Okay, thank you again.
All right. Well, thank you so much for that wonderful introduction. And thank you for having me. I'm genuinely thrilled to be here. It's wonderful to see so many of you in the room and others joining us online. So today we'll be talking about statistics. I've gone down the rabbit hole of thinking about statistics a few years ago, and I never left that hole. And there we are. I've written a paper about it now, and I genuinely enjoy kind of talking about it and finding ways of making statistical training more approachable, because it's people have different views of what statistics is, right? So what I'm going to be talking about today just breaks it down to the fundamentals, and kind of shows that we don't necessarily need to think about statistics in terms of applying these very kind of obscure type of tests. We can go simpler and then build up on that. So just to kind of, oh, is this working? Can I go next slide? There it is. Yeah, I think it's, oh, I think it worked. This mic is on. The mic is on, so it should be okay. It's okay? All right, wonderful. So first thing I want to do today is just to set expectations. So I cannot teach you the whole field of statistics. I hope you're not expecting that, because no one can do that in a day, right? We have to be realistic about what we can achieve in a day. So my plan for today is just to sow the seeds. I'm going to sow the seeds of good statistical practice, what I've found to be really useful ways of kind of reconceptualizing statistical questions, statistical approaches, and provide you with lots of resources. So the focus will very much be on the approach, questions, how do we go about it, and making sure that we start it early, not after we collect our data. And I'll give you lots of really useful resources, since I can't do everything in one single day. Hopefully you'll be able to kind of follow the resources on your own and find your very specific niche or your specific trajectory that will be helpful in your own research. Okay, in terms of specific goals, I have some very specific goals. Number one is to learn to distinguish between descriptive and inferential statistics. You might be familiar with these terms, or maybe you're not, and that's okay. We'll talk about it. We'll very specifically kind of focus on what are descriptive things. We use them very, very commonly, but oftentimes we use them to make inferences, but we don't necessarily draw on these inferential tools that we should be using. So one allows us to talk about a sample, one allows us to talk about a population, and we need to use those tools for the specific purpose that they've been designed for. The second goal is to ask questions based on estimation rather than dichotomous thinking. This will become very clear what I mean about that in a little bit. The third goal is to appreciate the benefit of meta-analyses. Some of you might be familiar with meta-analyses, some of you won't, and either way is fine. I'll show you some examples of how to do meta-analyses using a type of plot, which is called a forest plot, which is very, very useful. It's not used as commonly in archaeology yet. I've been introducing it to the classroom, into research. I've got a master's student who at the moment is writing her the first chapter of her thesis. She's doing a meta-analysis, and it's great. So the approach of using forest plots is really, really useful, and we need to use it more because it's very beneficial to synthesize previous research. And the last goal is to approach data visualization using principles of reliable and reproducible statistics. So I'm going to throw many messages at you today. And one of the main messages I hope will come across is that statistics, it's not just about models. It's not just about tests, and it's not just about numbers. It concerns a lot more. And one of the things that it very much has an impact on is data visualization. So how do we actually show data? Even conceptualizing, you might start with like sketching a graph before you even collect your data. Even sketching that graph, what you think your research will show, that's statistics. Right? Statistics doesn't have to be something that we leave until the very end, until we've got the data and then kind of decide to kind of do the number crunching. It has to be part of the research process very early on. And we'll talk about some principles of good data visualization. So lots of big topics, and I'll start to break them down very, very soon. So Effie's already mentioned this in the introduction, but what I want to start off talking about is statistical significance tests. Who has not heard of statistical significance tests? Everyone's heard of them. Your t-test, your ANOVA. Does anyone want to take a stab at saying what they show us? Like, what do they actually give us? And if you're shy, that's okay. Has anyone used them and is like, okay, I'm feeling really good about them? Maybe I'll save my questions for later. Yeah. Okay, so significance tests are these ways of basically testing a model using one of the most kind of basic statistical approaches, where we like have a null hypothesis and then we try to see if we have evidence to reject that null hypothesis. So in a very kind of commonplace application of these types of methods, we would find things like this in the literature, right? These are just some examples. I notice I didn't put citations on this because I don't want to put anyone on the spot. Like, I don't mean to say anyone's done it wrong. I'll show you my examples of how I've used significance a lot in my previous research. So I'll cite that, but these are just random samples that I got from the literature. And you would see very commonly statements like, when comparing the youngest individuals under 6 years between both chronological contexts, it seems that increased isotopic values occurred only during Neolithic B, with delta 15N being significantly higher during the C phase. Another example, however, no significance was found in mean delta 15N value between males and females, and then you get the p-value. People make statements about significance very early on in papers. So this is the second one is from the abstract, and they say, here we present the earliest statistically significant evidence for such differentiation among the first farmers of Neolithic Europe. And sometimes when people don't find statistical significance, they say, while the results are interesting, they must be viewed with the utmost caution as they were not found to be statistically significant. Okay, so it seems that statistical significance is something that we kind of strive to achieve, right? We've got our data, we plan to do this test, and if it comes out as significant, we rejoice and publish. And if it comes out as not statistically significant, we despair and potentially not publish the result, put it in a drawer. And that's problematic because we can't just publish things that pass this very arbitrary, it will turn out to be a threshold. Here's an example of my very first publication, the one that Effie witnessed me submitting when I was a PhD student in Athens. And my previous work is all significance is written all over it. So I've got this one sentence in there which says, in the Middle Neolithic, the diets of these animals differed on the delta 13C scale. I've come a long way. Don't say delta 13C scale, say delta 13C values. This difference is statistically significant at the 99% confidence level. And then I've got a t-test saying it was two-tailed, it was equal variance, and I've got a p. Okay, so these statements are very common. I've made them in the past. But what I think is really, really useful is to actually pause and think about, what is it? What actually is significance telling us? And is it telling us what we think it is or not? So let's look at an example. Before we go into definitions of like, what's a p-value, what's a null hypothesis, let's look at an example, okay? So it's called lucky, no luck. It's a hypothetical. So we've got two experiments. One is called lucky, 2008. One is called no luck, 2008 also. And both of the experiments are looking on the impact of malnutrition on delta 15 values, okay? The delta 15N. So it's looking to see, does malnutrition cause higher delta 15 n values. In the first study, they had two independent groups. So one group with no malnutrition, one without. The sample size was N22 in each group. And the results of the first study were statistically significant, okay? They found a statistically significant impact of malnutrition on these delta 15 n values. Here's the mean, 3.6%. The standard deviation of the difference was 6.9%. T statistics, 2.43, and P was 0.02. Okay, so the reason we are statistically significant was because this is lower than 0.05. The second study, very similarly designed, looking at the same question, slightly smaller sample size, n equals 18, but they found no statistical significant impact of malnutrition on delta 15 n values. The mean of the difference was 2.2, standard deviation 7.6, T statistics 1.25, but because our p-value came out quite large, 0.22, the results were not statistically significant, okay? Now, this is a hypothetical example, but something like this is really, really common in the research literature because there's lots of studies, experiments or not, where we might seem to get very conflicting results. Some of them are significant, some of them are not. So one of the big challenges of how to move forward is what do we actually do in this instance? Like, how do we actually move forward? Do we say that these two studies are consistent? Do we say they're equivocal, they're kind of in the same direction? Or do we say they're inconsistent? Okay, if I was in the classroom, I'd have people raise their hand, like how many people think they're inconsistent. So some people might argue that they're inconsistent, right? One is significant, one is not. So there's no way we can make up our mind because we can't move forward. We need a bigger sample size. That's a very common way to respond. Another way to kind of look at this is to say, well, they're equivocal. They're both in the same direction. The means are positive. It's not like one is 3.6 and then the other one is negative 3.6. They're in the same direction. They're similarly sized, so they're actually equivocal. Another way to look at it is that they're absolutely consistent, right? We can ignore this p-value and just look at the outcomes and see that they're actually not that different. So that's not ideal. That even for a very simple scenario, people might have very different ways of actually approaching how do we synthesize these results? Like, how do we move forward? There's three very different approaches. Now, let's for a moment forget about what the p-values show and actually look at the numbers, look at what the outcomes are showing. So here, I want you to focus on these point estimates. So I'm using the word point estimate to talk about the mean, right? Point estimate could be anything that you're measuring. In this instance, it's the mean of our difference in delta 15 n values. So the first study, our mean is just under 4, and there's a long error bar on it. Now that error bar is not the standard deviation. Okay, in this instance, I'm showing the confidence interval. We'll get into what that actually means. But the confidence interval basically shows where the true mean is mostly likely to lie. It's not showing us about the spread of data. It's showing us where the true mean is most likely to lie. So lucky up top, no luck on the bottom. So when you look at that, you could be like, well, actually, the two results are very similar. They're both in the same direction. They both have similarly sized confidence intervals on them, which means that the studies have similar precision. So it's kind of looking like there's not some, like, things aren't too different about them. So why is one actually significant and the other one isn't? Does anyone want to take a stab? Why is it that the second one just misses the threshold of significance? And you can tell that this is a nice trick to know. You can tell just by looking at where the point estimates are, what the outcome of significance is going to be. And the way to look at that is to pay attention to where your null hypothesis is. Okay, so our null hypothesis in this instance, H0, it's on 0, right? So we're assuming our null is that there's no difference between the group that is malnourished and the group that is not malnourished. So our null hypothesis is 0. The first one, the first confidence interval, does not include 0. That's why it's statistically significant. The second one does include 0. That's why it's not statistically significant. So the only reason why the outcome is so different is because of where that 0 falls inside the confidence interval. But your intervals might be larger, they might be smaller, depending on how your study is set up, depending on how many sample sizes you have. So the actual precision on your estimate might be different. So whether or not you end up including the 0 or not including the 0 might actually have nothing to do whether there's a true difference. It might have to do with how the experiment is set up. Okay, so that's the only reason one is significant or not, includes 0 or not. So one of the main messages for today is that a statistically significant result does not necessarily mean that it's large or important. Okay, the only way to know if something is large or important is to understand the context. Okay, so if we come at this with knowing a little bit about principles of stable isotope analysis, we know that in the past there have been some studies on malnutrition and delta 15N, and we might have some idea about what we would consider to be a small effect, a medium-sized effect, a large effect. You might kind of approach this by saying like, okay, I'm gonna not really consider a difference to be meaningful if it's less than 2 per mil. So if that's your threshold, if it's less than that, if your difference between the two groups is like 0.5 per mil, well, what does that actually tell you? If it's that small to not be meaningful, regardless of what the significance is telling you, the context should be what's driving your interpretation of the result. Okay. Yes.
Most of the participants have some background on statistics, but some may well not, especially the online participants. So can you please give a very brief definition of what the null hypothesis is and what does it mean when we say that the p-value, the significance level is set at 0.05?
Yeah.
Just for their sake.
Gonna get to that.
Okay.
Thank you for mentioning it though. I'm gonna get to that. I just wanted to show this as an example of like, sometimes we get this and sometimes we get that. So now we're just talking about this very common scenario where something is significant, something isn't, but we'll get to the definition of p-values and all, but thank you. Awesome. All right, so, but before we get there, I want to talk about statistical thinking first. So this is usually when I run workshops on this, it's the workshop is called Statistical Thinking, Introduction to Statistical Thinking. And the reason I do that is because it's really important to think about it on day one, not when you're ready to start crunching your data, not when you're ready to like publish your paper, but it's something that should completely frame our approach for doing research. Okay, I'm following or most of what I'm going to say in this section comes from a textbook which is called Introduction to the New Statistics. It's a really, really useful textbook, and the reason I'm saying that is there's other people that have different views, right? Not everyone thinks there's just 3 types of statistical thinking. Some other people might say there's more. Some people say that we need to group them differently. But today I want to talk about 3 different types based on this one resource, okay? So in this textbook, the authors really want us to try to distinguish between what's called dichotomous thinking, estimation thinking, and meta-analytical thinking. And it's really useful to frame our questions. I've got this nice little diagram here to show us that we're thinking. It's the brain. So the first type, dichotomous thinking, is you can think about it as like maybe the simplest kind. It's where you have a yes or no answer. Okay, so if you have a question like, did the diets between men and women in prehistory differ? The answer is yes or no. It's not saying anything about what the differences were. It's just saying, is there a difference or correlation between diet and stature? There either is a correlation or there is not a correlation. So this is dichotomous because the outcome can be one of 2 things, okay? This type of thinking is very common in a statistical approach called null hypothesis significance testing, where we define a null hypothesis, okay, of no effect or no difference. So we go in saying there's not going to be anything there, even if you don't have a reason to believe it, okay? You need a null, you need this no effect thing. So you go in and say, okay, I'm going to study a phenomenon, but my null is going to be that the phenomenon doesn't exist. So what my aim will be to actually show that that null can be rejected, that I have some evidence, I've made some observations to show that, okay, it's most likely that there is an effect that we can reject this null. So set a null of no effect, then you look for the evidence to reject the null hypothesis, and then you reject or not reject. Notice how I didn't say accept. Okay, because that's problematic. You cannot ever really accept the null. You can only reject or not reject it. And that's one of the reasons why null hypothesis significance testing can get a little bit kind of murky, because sometimes we use language that suggests that we're accepting it, even if we don't necessarily mean to do it. But NHST, very common, a vast number of papers in the scientific literature uses this because it's a very kind of easy way to do statistical analysis. So you would commonly see in the literature statements like, we rejected the null hypothesis of no difference and concluded that there was a statistically significant increase at the 0.01 level. People say levels because they're talking about this confidence. How confident are you that we can reject this this null? So I've written statements like this in the literature. It's very, very common. But there's challenges with making statements like that. Different people call the challenges different things. The textbook I've already mentioned, they say that there's red flags. There's 5 red flags that we need to be aware of when we talk about significance outcomes. Another really good paper by Goodman, 2008, is called The Dirty Dozen. 12 p-value misconceptions. So now they're going from 5 to 12. They're saying there's 12 massive problems with using this kind of approach. Gerd Gigerenzer, who's one of my favorite people, he is a researcher. He's a statistician, I think also a psychologist, but he talks about risk literacy. He goes around the world. He has a fantastic TED Talk talking about how we need to start teaching kids from very young age what risk literacy is. What are probabilities? Probabilities might be hard to calculate, but they're not that hard to understand. Like small kids can understand what probabilities are if we explain them. So that's the guy who talks about risk literacy. And he's got a paper on significance testing. And he talks about these collective illusions, right? That we get these results, but we might have an idea about what they are, but the reality might actually be different. So common approach, but there's challenges that we really need to be aware of. Okay. The second type of thinking is called estimation thinking. And this is where we move from just talking about a yes or no question. Is there a difference? Was there a difference in diets? Was there a correlation between stature and delta 13C, delta 15N? Now we're moving beyond that and we're talking about how big the differences are. So when you ask questions about how much, to what degree did groups differ, now you've shifted from dichotomous to estimation thinking. And this is where you can really bring in more information, right? Because most of the readers of papers are probably more interested to know how big a difference was than just saying, there was a statistically significant difference, it passes a threshold, and kind of leave it at there. So I will argue that estimation thinking is more informative. It's better science because it's actually drawing on the context. It's using your knowledge of the background to make interpretations about findings. So if we say something like a healthy diet is correlated with a moderate increase, 5 centimeters plus or minus 2 in stature, that's an estimation type of outcome. It's not just saying that there is a correlation. All right. So with estimation thinking, we could ask questions like how big is the effect? To what extent do the groups differ? To what degree are the results consistent? How big does an effect need to be meaningful? And this is important. This really reminds us that we need to start thinking about our effect sizes and what we expect them to be early on, not after we collect the data, but if you go and approach your project and say like, okay, I'm going to look for differences in diets. If the differences are like 2 per mil, yeah, okay, maybe that's a small difference. If they're 4 per mil, that's a moderate difference. If they're like over 6 per mil, that's a big difference. So having a hypothesis, right? Like having some idea about how your outcomes, how you would interpret your outcomes depending on what the results would be. So setting kind of thresholds of what you would think would be good ways to interpret the results. Another question we can ask is, in the given research context, what is a small effect size, medium effect size, large effect size? That it's really good to spell it out, like in the background section of a thesis or in the introduction of a paper. It's really useful to kind of signal to the reader what you would think would be different sized effects. And how much certainty do we have in saying there's a difference? This is another big benefit of estimation thinking, in that it kind of drives us to not just be interested in saying what is the mean, but how confident are we in saying that the mean is where it is, right? There's always uncertainty, but we need to communicate that uncertainty in good terms. And standard deviation is not always the best way to communicate uncertainty. It's a descriptive statistic. It has a very specific function. It tells us how data is distributed, but it doesn't tell us where the most likely kind of interval where the true mean lies, where that is. That we need inferential tools for that. All right. Last type of thinking is called meta-analytical thinking. This is a picture I pulled off the internet. It's just a very simple way of kind of breaking down different approaches to research. So we've got case studies, case theories, cohort studies. randomized controlled trials. And meta-analysis is at the top because it's what we really should be striving for. Individual case studies are useful, but what is really going to drive science is synthesizing studies. So putting the data together. It's very frequent that we might come across studies that either are consistent or inconsistent, and then we kind of make arm-wavy explanations about saying like, okay, there's an effect there. Well, we can do better. We can actually combine those outcomes and say what the overall outcome is. And the great thing about this is that the overall outcome is almost always going to be more precise. That confidence interval, that uncertainty, it's going to go down. Even if you put two studies together, like it's really, really useful. So I'll show you today some examples of how to do very simple meta-analyses. So meta-analyses can be large scale, like absolutely. There's studies that have millions of lines of code, millions of lines of rows of data. That's a big meta-analysis, but we can have meta-analyses on the small scale. So remember our lucky and no luck study, that was just 2 case studies. We can put those 2 together, get an overall meta-analytical effect size, and notice how the plus or minus, the interval, the error bar is smaller. It usually goes down. So that's really useful. And if you care about significance, notice that 0 is not included in that confidence interval, so it does pass statistical significance. All right, so let's kind of take a step back and think about these types of statistical thinking. I've color-coded them because I think estimation and meta-analytical ones are the most useful, the most informative, but dichotomous is out there. Every day I come across papers that use dichotomous thinking. P-values are not going anywhere. For decades, statisticians have been saying we need to abandon them, but it's not going to happen. So we need to learn to live with them. And the way to move forward is to really kind of understand what null hypothesis testing gives us and also how it came to be. Why does it persist? This is Jacob Cohen. He's one of the most prominent statisticians of the 20th century. He's amazing. He's written really, really good work. And in one of his papers, he said, a p-value does not tell us what we want to know. And we so much want to know what we want to know that out of desperation, we nevertheless believe that it does, right? Oftentimes, I think we panic when people get to the stage of being ready to publish the results, being so close to kind of tying together their thesis, and this was my case for sure. I just wanted to put the statistics together, just put the final touches on my thesis. I kind of reached for the closest statistical textbook, learned how to do a t-test, ANOVA, and then published it because I was so desperate to just get a stamp of approval, just do the stats and kind of just move on with my life. So he talks about how sometimes we do it out of desperation. But how did we actually get here? I don't want to spend too much time on it, but I think it's useful to actually know what the approach for doing statistical significance, what it actually is. And what it is a mishmash of 2 different approaches. So Sir Ronald Fisher, over 100 years ago now, or close to 100 years ago, he came up with the idea that p-values can be used as a guide for reaching a judgment about a hypothesis. Okay, so he had a research question. He made a hypothesis, and then he said, if we calculate this p-value, which has to do with the area, like probability under a curve, we'll get there, you can use it as a strength of evidence against the hypothesis. So remember, we have a null, we want to reject it. So p-value gives us a strength of evidence against that hypothesis. So the smaller the p, the stronger the reason to doubt it. That's all he said, okay? He said p-value provides strength of evidence, but he didn't say that it gives us evidence that a hypothesis is true. And so a lot of the times in research today, you'll come across papers that say, okay, we found no difference, so there is no difference. That's not what he was saying in the early days. Another approach was by Neiman and Pearson. They came up with the idea of using an alternative hypothesis and using thresholds. You might have seen these alpha levels. So basically he said, okay, we can have a question. We have an alternate hypothesis, which is just, it's not a null, it's something else. Like, so if you're expecting the diet, the difference in diets between men and women to be 2 per mil, and then you test against it, that's your alternate hypothesis. And with this approach, all you need to do is decide how willing you are to be wrong. Okay, if you're willing to be 1% wrong, you have to use strict, 99% confidence. Your alpha has to be high. You want the p to be less than 0.01. If you're happy to be 5% wrong, you can go a little bit lower. So you can go to like p is equals 0.05 in terms of the probability of your null being captured under a specific curve. So that's what they said, okay? They had these alpha levels. They said you have to decide before carrying out your research how willing you are to be wrong, and then you accept it. You don't decide what your alpha level is after seeing what the p-value is. And I've definitely done that in my previous research. I saw my p, and if it was like 0.02, I was like, okay, it passes 0.05, so I'm gonna say that that's what I assumed at the start. If it was less than 0.01, I said like, okay, I assumed that alpha was much higher, 99% confidence. But they didn't say that. They said you have to decide how willing you are to be wrong ahead of time. And then when you get your p-value, then you stick with that and kind of move forward. But they didn't say that p provides the strength of evidence, which is what Fisher said, for the likelihood of the null being true or not. So two slightly different approaches, one for this idea of using the p-value as a strength of evidence, one for this alternative hypothesis testing, threshold, significance levels. And nowadays, we kind of use a very kind of combined approach. And importantly, they famously disagreed with each other. Like Niemann and Pearson, they did not like Fisher's approach. Fisher was like, I don't like this alternative hypothesis testing. So even after their early papers were written, they were kind of loggerheads about it. However, what we do now is a kind of a mishmash of the two. We look for these thresholds and we say that p-value provides us a strength of evidence. And annoyingly, often people use the wrong definition of p. Okay, so you will find textbooks out there. And even in my, I know this will be recorded, like I took a lecture on statistics in my undergrad. What I learned about p-values is not necessarily the right definition. So you might hear things like p is the probability that the null is true. That's not the definition. Or p is the probability that the difference is due to chance. That's not the correct definition of p. We'll get to the correct definition of p. I like to dangle things. We'll build on it. So it's really important to not say that things are not due to chance. There's a whole book about this. The guy who talks about risk literacy, he wrote a whole book about how science is or isn't due to chance. Like this idea of thinking that a p-value tells us whether or not something is due to chance, it's not correct, and it's been kind of perpetuated. So it's a problem. We've got this mishmash of approaches that weren't meant to work together, and now we often kind of just panic and do something very late in the research process and make statements about something being significant or not. But there are ways that NHST can go wrong. So I've mentioned the red flags, I mentioned the misconceptions, collective illusion. There's lots of literature on this, tons and tons of papers written by professional statisticians. What I want to talk about today are the red flags from Introduction to the New Statistics. Does anyone have any questions so far? I should make sure to pause frequently. Yes.
I was just wondering from the previous part that you've talked about the p-values, how do we know which one to use? If we're going to go with the 95%, if we're going to go with the 1% chance?
So the correct way, the way that like Niemann Pearson would say is you have to choose it based on the research context, right? So if you're doing research in like medicine, you really don't want to be wrong, or like pharmaceuticals, are they effective or are they not? You really don't want to be wrong because people could die. So you want to go like 99% confidence, 99.5% confidence, right? As much as you're willing to accept. With research, and archaeology falls into this category, we don't usually have the luxury of having a lot of samples, or even having ideal samples, or even having samples that preserve well. So it's best to kind of go a little bit lower in this confidence, but I would argue that like I don't use confidence levels at all in my research, but it would be warranted to go down to like 95, because you don't want your error bars to be massive, right? The higher you go in the confidence threshold, the bigger the error bars, because you don't want to be wrong. And with bigger error bars, you can't say much, or like it just constrains what you can say. So the answer is the context. Thanks. Yes.
What our data choices, statistical choices, until when we want to present the result. From what we're saying and from what I know, it means perhaps even before we even go to the field at all, the statistical choices should be part of what we should consider before even moving to the field, considering going to the field at all.
Yeah. So, what is the question? The question is that we should be making.
Yeah, is that what you're saying? That the statistical choices is part of what we should be considering before we even go to the field at all?
Yeah, before you start collecting your data. Because once you start collecting your data, you could be biasing the results, right? So if you make your decisions about like where you want your thresholds to be, or what you would consider to be small effect, medium size, large effect, do it early on after reading the literature, after familiarizing yourself with the background research, but before collecting the data. Because once the data starts to come in, if like, I don't know, you're looking at the difference between size of men and women, if your differences are like around 2 per mil, saying that like, oh, that's what I was expecting, that's bias, right? Because you've already looked at the data. But if before you look at any data, you say 2 per mil is a big difference, then no one can kind of call you out for cherry picking. Yes.
Petra, also another comment. If I'm not mistaken, the sample sizes that are being analyzed can also bias the p-value. So my understanding is that if we have really big sample sizes, like they may have in medical research, they may have hundreds or thousands of participants, it is more likely to get a small p-value. Whereas when we analyze small sample sizes, like the ones we often have in archaeology, it is less easy, less likely to get a small p-value, even if there is an effect there.
Absolutely.
Am I right?
That's really important. But just because we don't find that effect doesn't mean it's not there, right? So if our sample sizes aren't ideal, we get something and it comes out to be not statistically significant. If we say there's no effect, that's one of the red flags. It's accepting the null. We can't accept the null. We can't ever, we can reject it or not reject it, but saying that there's no effect is the same thing as accepting a null. Yeah.
That we can state it, because it seems like saving everything we do, even when you compare our samples and names, pigments, after the lower class, rural, urban, in there. You really mistake somehow.
I do. I really do. I am pessimistic about some parts of statistical training, but this is something I'm not pessimistic about because it's like we have it in our own hands, right? Like if we read a paper that's very dichotomous, everything is phrased like significance not passes not, what you can do in your head while reading it is you can rephrase the questions. You could be like, to what extent is the difference there? Like how big are the differences? And if they show you the means, you can do your calculations. You can put, and we'll do some examples today, you can put your confidence interval on it. So as long as the data is available, we can just use the inferential tools on our own. So I am hopeful that we can shift. It's just a matter of awareness, right? Like we need to read the papers by statisticians. Like none of this is new. This has been in the literature for like 60 years. Like even back in the 90s, statisticians were like, you guys, we need to take a pause. Like we're doing this wrong, but we weren't paying attention because even when I was a PhD student, I didn't interact with any of this literature because this just wasn't on the reading list. But shifting, I think we can do it. We're still going to have to interact with NHST because it's going to be out there in the literature. A lot of people are very attached to it. But like personal approaches, we can absolutely shift from dichotomous to estimation. Yeah, no worries. All right, any more questions? No. Good. So let's talk about the red flags. So the first red flag is providing a false sense of certainty. Okay, so this is when we look at a dichotomous conclusion and we just say it passed, so there's an effect, and that's where we can leave it. I've got a nice cartoon. Someone is shouting, "I'm significant." Screen the small effect size. So no one's paying attention to the fact that this effect size is very small. Everyone's paying attention to the fact that it's significant, that it passed the threshold. But what we should be paying attention to if we're using estimation thinking is how big the size is, right? So to use a very non-archaeological example, if you're looking at speeds of cars, right? If you have two different brands of car and they're going as fast as they can go, and you're trying to see if there's a difference in the maximum speed that the two cars can achieve, what if the difference is like 1 nanosecond, but it's statistically significant? Well, 1 nanosecond doesn't make too much of a difference. But if your confidence intervals are narrow, if the interval misses on that 0, now it's significant. So it would be tempting to say like, yeah, 1 car can drive faster. But if the actual difference is a nanosecond, it means nothing. So we need to be paying attention more to the context. Okay. So providing a false sense of certainty is paying attention to these threshold outputs rather than the actual numbers, the actual answers. Another problem with NHST is misusing the term significant. So I love how in this book, they're calling it the S word, the ambiguous S word. So statistically significant does not imply large or important. And it often leads to what can be called the slippery slope of significance. So these are also hypothetical, but it's quite common to see this in the literature. Someone might report there was a statistically significant decrease in rainfall amount. P was 0.03. Okay, so that's in the results section. And then later on in the same paper, the authors might say rainfall amount was significantly reduced. Well, that's a slippery slope because all we said is that it doesn't, that it kind of passes the threshold, that 0 is not in our confidence interval, but it doesn't say that the impact is meaningful or significant. It's also problematic to use the word significant kind of outside of its statistical definition because like when we see that word, it immediately implies importance, right? Which it shouldn't. So slippery slope of significance, finding a p-value that we like, and then slipping into saying there was an important effect. Another problem that's very common is accepting the null hypothesis. So saying there's no difference. So this is the flipped effect. So this is the slippery slope of non-significance. So if someone reports because P was larger than 0.05, we couldn't reject the null of no difference in the diets between the two groups. So if that's written in the results, you read later on in the paper, they might say something like social status made no difference on the quality of diet. That's accepting the null because you're saying there's no difference, but just because you didn't find it and because arguably your very small sample size didn't allow you to capture doesn't mean it's not there. So accepting the null could be problematic. Defining the p-value incorrectly. So this is where we get into definitions, okay? Oftentimes, and I've learned this through like high school, undergrad, when I was a student, I've heard definitions like the probability that the null is true, probability that the difference is due to chance. This is not the definition of the p. The real definition of a p-value is the probability of obtaining our observed result or more extreme, because we're talking about the area under a curve, under a normally distributed curve. So now we're in the tails, more extreme, if the null is true. Okay, we have to assume the null. We can't actually get to the null. A lot of people try to use the testing to see, like, is the null true? Is it likely to be true? Is it likely to not be true? Can we reject it? We can't do that. All we can do is we assume the null. And if we assume it, how likely it is that we get the results we get or more extreme. Okay, so normal distribution, your null is in the middle. Your null is the mean, middle part of the normal distribution. If you go into the tails, if you're really far away from the 0, you get into the tails. If you're at the place where you are or more extreme, that's what the p-value tells you. It doesn't tell you anything about how likely it is that the p-value, that the null hypothesis is true. It's something you have to start off with. Another challenge is assuming that a p-value can predict a replication outcome. This is also really common. We might see a paper, an experiment that says we found this effect. And assuming that you're going to find that effect again, that could be problematic because maybe the first experiment didn't have large enough sample sizes, or they just missed seeing, missed seeing a true difference, accepted the null, and then kind of implied that in the future we're also going to be able to not see that difference. So here's an example. This is a simulation that I made based on a paper that 2014 paper that I mentioned from the site of Kufovano. I had some goats from the Middle Neolithic and from the Late Neolithic, okay? These are the true values that I measured. So these are the descriptive statistics of my goats from Kufovano, okay? The delta 15N mean of the Middle Neolithic ones was 5.0 plus or minus 1 per mil, 1 standard deviation. The Late Neolithic goats had a mean of 4.2 plus or minus 0.9 per mil, 1 standard deviation. So that's what I measured. That's descriptive. It's describing how many kind of I measured. Now, I assumed that were the true means of my two populations. There was a Middle Neolithic goat population. There was a Late Neolithic goat population. I assumed that was true. And then I generated data using R. I just said, hey, R, give me sets of 20 samples that conform to these descriptive statistics. I want the mean of the Middle Neolithic goats to be here. I want the mean of the Late Neolithic goats to be here. Give me some numbers and see what we come up with. So in the first simulation, my middle Neolithic goats had a mean here, my late Neolithic goats had a mean there, and I had a standard deviation 1.1, 0.8. In my second simulation, very similar numbers. So if we're saying 5.0 plus or minus 1.1, 4.8 plus or minus 1.0. Okay, so these are realistic numbers you might get if you sample from this true population. These are realistic samples of 20 individuals. Now, if I test these, if I test the difference between my middle and late Neolithic goats, test to see if there's a statistical significant difference. If I find a difference in my first simulation, what do you think that tells me about the second simulation? Will I also find a statistically significant difference? The answer is, we don't know. Maybe you will, but maybe you won't. In this specific scenario, look what I got. When I tested for the difference in the first scenario, I got a P of 0.01. That's statistically significant at the 95% confidence level. But in the second one, I did not get a statistically significant difference. It's the same underlying true population. It's just simulated data, simulated just 20 grabs of realistic goats from my underlying population. In the first instance, I found a statistically significant difference. In the second one, I didn't. And this is nothing that I did. I just followed protocol. I just randomly simulated data and then calculated a p-value. So this tells us that we cannot rely on p-values to predict what will happen in the future. If this is what you measure in a study, you do that same study again, you might not get the same results. And that's because p-values can be really, really variable, which is a problem because we like to predict what's going to happen in the future, right? Especially with experiments, we want to be able to say like, okay, if I have a larger sample size or a smaller sample size, am I going to be getting consistent results? So we can't predict. P-values can be really variable. A really nice way, I'll show you that in the second part of today, probably before the lunch, the dance of the p-values. There's these dances. This is a simulation that accompanies the book I've been talking about, but I'll show you how you can use it. You can simulate experiments from a true underlying population, and then you look at how do the p-values differ if you kind of keep running the same experiment over and over. You can see how the confidence intervals differ. You can see if they're being captured, if it's capturing zero of null difference. So the dance of the p-values is a really useful simulation, and you can find it on this website, but we'll look at it together in a few moments. All right, so in this section, lastly, I just want to say, don't fall victim to the cult of significance testing. There is a lot of literature out there that uses language that's just a little problematic. No citations. This is from actually a website that just listed ways that people have talked about significance. People said there's a clear tendency to significance. There is a non-significant trend towards significance, as good as significant, fitting with conventional levels of significance, or just fail to be significant, or near certain, or someone tantalizingly close to significance, vaguely significant, well not significant. Well, no, like this kind of language is problematic because it's very vague, right? Like, are they accepting the null or are they not? We should be using, if we are using null hypothesis testing, we should be using it in the way that it's been designed. You have a null, you get a p-value, you decide how confident you are, you decide ahead of time how willing you are to be wrong, and then whatever your p-value shows, that's that dichotomous outcome. That's what it tells you. Nothing more, nothing less. But using language that's kind of twisting a little bit. Like some people, when they get very close to that 0.05, they're like, well, it's remarkably close to significant. Well, significance is a threshold. It's actually an arbitrary threshold. So just because you're super close to it doesn't mean that you're almost there. Like that's not how we should be framing it. It's dichotomous. That's all it is. Okay, now something I really want to make clear is that this is not just my opinion, okay? I don't have a PhD in statistics. I've gone down a rabbit hole after reading a paper by the American Statistical Association, and I've been doing readings on this because I was really interested in it, but there are a lot of professional statisticians who are saying the same thing. So the paper that led me into the rabbit hole was here, the ASA statement on p-values, context, process, and purpose. And they say it, I mean, the way it is. They say that while the p-value can be a useful statistical measure, it is commonly misused and misinterpreted. At the end, they say that statisticians and others have been sounding the alarm bells about these matters for decades, but we just haven't been paying attention. Really useful paper. It's very short. It's about 2 pages, and most of the main ideas are bullet points, so very, very accessible. Highly recommend to anyone to read it. There's another paper called Retire Statistical Significance. This was actually a petition by, I think, over 800 signatories, scientists around the world. They're like, we need to stop being so dichotomous. We need to pay more attention to effect sizes, to talking about how big differences are, but just using these arbitrary thresholds is not going to get us very far. Another paper, Life After NHST, How to Describe Your Data Without Peeing Everywhere. That's a good one. That one's in biological anthropology. If you publish in Nature, they're going to have you fill out a checklist, and one of the sections is on reporting result, and they're going to have you read this paper called The Difference Between Significant and Non-Significant is Not Itself Statistically Significant. This is written by professors of statistics, like ones that have been at the forefront of this debate. Not, you know, they know what they're talking about. This is the paper I mentioned earlier, the Dirty Dozen, 12 p-value misconceptions, so wasted p-value interpretations can go wrong. Gurjit Drinzer, the one on who talks about risk literacy. This is a great paper called We Need Statistical Thinking, Not Statistical Rituals. So the reason I spent a whole section of today talking about statistical thinking is it's so important to think about the early stages, what your question is, what your approach is, not just about kind of planning to do this ritual. T-test and statistical testing, it's a ritual. We just have this arbitrary threshold. We look to see if it passes or not, and then we report it. That's not actually using the context or using our knowledge of the research to make the interpretations. Really, really useful paper, and written in a very accessible language. He wrote another one called Mindless Statistics, which is useful too. This one is also, I think, from biological anthropology, the continuing misuse of null hypothesis significance testing in biological anthropology. So the research is out there. I didn't interact with any of this when I was a student because I wasn't in the rabbit hole yet. But it's out there if you look for it. In archaeology, I think back in the 70s, someone started ringing the alarm bells. So David Hurst Thomas wrote a paper in which he said, but statistical revolution in archaeology is not without its price. We must now face the fact that all applications of statistics to archaeology can no longer be applauded. The archaeological literature is badly polluted with misuses and outright abuses of statistical method and theory. So that's in the abstract. And later he just goes on to spell out what he thinks are the misuses. And the first one, slavish adherence to the 0.05 level of significance. Second misuse, inferring causal relationships from statistical significance. Third one, confusing statistical significance with strength of association. So notice that the top 3 problems in statistics that this archaeologist, I think he still works at the Museum of Natural History in New York, the first 3 problems have to do with statistical significance because it's not being used in the way that it's been designed to be used. I had a paper recently, which is called How Do We Improve Statistical Training in Archaeology? There's a wonderful illustration that I had a professional illustrator make. I framed the paper around things we don't talk about, so elephants in the room. And the first one is statistical thinking should come first. We don't talk enough about dichotomous thinking, about estimation thinking, about meta-analytical. We don't talk about the difference between descriptive and inferential enough. We don't talk about this variability around the p-value. Remember that simulation I showed? We don't talk about that. We don't necessarily distinguish between different types of precision. There's instrument precision. There's statistical precision, which has to do with how close a thing is to like the true estimate, true mean, if you're looking at means. And we don't talk about forward plot enough. So if you're interested, you can read this paper, and there's supplementary materials online where you can follow the examples and kind of put your own confidence intervals really easily on whatever you see in the literature. Okay, we're doing good on time. So how can we do better? We can acknowledge that there's that there's challenges with using statistical significance, but actually taking the step is harder. And I know this from personal experience because I have been trained like this as a PhD student. So I had to kind of fight my way through trying to resist significance, but still wanting to say enough about my data. So here's kind of some advice that I came up with on where do we go from now. So step one, I think is really useful to decide early on what kind of thinking you want to use. If at the end of a paper, you want to say there was a difference between the diets of men and women, if that's all you want to say, sure, you can be dichotomous, that's fine. But if you want to say something more, like how big was the difference, then you have to reframe your study around that estimation thinking approach. So start thinking about which type of approach you want to use early on, ideally on day one, not after you've collected the data, not after the reviewers have asked you to insert more statistics, or not after your supervisor told you to talk to a statistician to finalize the results. The earlier you can start thinking about it, the better. The second step is report and interpret effect sizes. So effect sizes are anything you measure. Okay, it could be a mean, it could be the difference between means, it could be a correlation coefficient, it could be a proportion, it could be difference between proportions, it could be regression. Sometimes correlation and regression is used interchangeably. Technically, they're not. Correlation describes the relationship, like if there's a positive kind of linear relationship between two variables. The regression is the actual line that you draw, okay? So regression makes predictions about where a y value would fall given an x that you choose. So they're related, but it's not the same thing. So an effect size, it could be anything you measure. And we should be focusing on that rather than saying kind of, is there a difference or not? So anything you can measure, you can quantify, and then you can put uncertainty brackets and uncertainty kind of error on it. So this is where we come to looking at the difference between descriptive and inferential statistics. Descriptive statistics is anything you say about your sample. Okay, if you measure your mean, if you measure a standard deviation, you have a specific sample size, anything that you can say, the observations that you've made, that's descriptive. If you want to move from talking about your sample to talking about the population from which the sample derived, which is usually what we're interested in, right? Like we study subsets of archaeological populations, but we rarely just want to talk about the subset. We don't want to write a thesis on 5 people. We want to write a thesis on the population from which the 5 people derived. So moving from descriptive to inferential, we need different kinds of tools. And it's not always that difficult to actually move from descriptive to inferential. It could be as simple as putting a confidence interval on your mean. Right? If you have a mean, you put a confidence interval to say this is most likely where the true mean lies. Now you can talk about the population because you've got an estimate of where the true mean is most likely to lie. So you're no longer just talking about the people you measured, you're talking about the true underlying mean. And we'll do some examples today on how we can calculate confidence intervals. So really, really important to both talk about how big effect sizes are and how confident we are in saying that they are where they're placed. And the good thing about confidence intervals is that they're very dependent on your sample size. So if your sample size is small, your confidence interval will be wide. So yes, it's good to remind your reader, like my sample size was small, but they won't be able to kind of make an incorrect interpretation using your mean and confidence interval. They won't be able to say something kind of groundbreaking from a massive interval. So you don't have to kind of keep reminding them that your sample size was small. So confidence intervals, super useful. Here's the example that I mentioned earlier, how I looked at the difference between my sheep, and I had statistically significant difference between my Neolithic and my late Neolithic. Now that's very NHSC, that's very dichotomous. How can we do better? In the kind of spirit of reporting and interpreting effect sizes, well, we can actually report what we found in full. I had a paper in 2022, which is on like best practices in isotope archaeology. And the second author of that paper is one of the co-authors of that ASA statement on p-values. She was at the time the president of the American Statistical Association. So I got in touch with her. I was like, look, I'm writing a paper on best practices in archaeology. I want to incorporate all of what you're saying about the problems of significance testing. I want to incorporate it in my paper. Can you help me write a section? So we literally took apart the Kufovano study and we said, how could it have been reported better? What were the ways that we kind of didn't go the full mile? So one of the things that we could have done is to actually show the difference between those middle and late Neolithic sheep. So instead of just saying, that's what I found, it was statistically significant, you can actually just show to your readers, here's my middle and Neolithic sheep. Sample size is quite small, but that's why the error bar is equally large. Those are my late Neolithic. And if I want to talk about, was there a difference in diets between the middle Neolithic and the late Neolithic, you can actually calculate the difference, put a confidence interval on it, and now you can talk about the most likely true difference between the two. And you don't really need a p-value to do that. So if you get something like this, you can talk about the data being compatible with a difference between 0, very close to 0, and 0.9. Okay, that's the best I can say with the data I collected from Kupovano. So even if, yeah, like you'd really have to stretch it to talk about this difference in diets being meaningful, because it's less than 1 per mil, so that might not mean much. This is why it's useful to have hypotheses, to know how you would interpret different types of data depending on how they showed up. So if at the start of my study, I kind of set thresholds and I said that if my difference between diets was less than 1 per mil, that's not too meaningful. If it was 2 per mil, okay, maybe there's something there. If it's over 4 per mil, that's a big difference. So setting kind of expectations for what your data will look like, really, really useful. So that's an example of effect size. Another type of effect size, so correlation coefficients. This is not an example from isotope archaeology, but more from bioarchaeology. So if you're looking at correlation between stature, so height, and the length of a femur, very common, lots of papers on this. If your paper reports something like the correlation, and this is Pearson's like linear correlation, Pearson's R was 0.66. P is less than 0.001. All that the P is telling you here is that confidence interval doesn't include 0. Okay, it's not telling you how wide that confidence interval is. It's not telling you what the most likely true correlation coefficient is. It's just telling you if 0 is included or not. And that might not be as informative as you would like it to be. So if you actually put a confidence interval on it, if you say, I was looking for correlation, I find 0.66, but my interval is from 0.46 to 0.78. Now you have to take that interval into account and use it in your interpretation. So you could say that most likely the true correlation is somewhere between 0.46 and 0.79, but that's your best estimate. So it's a little more, it's a bit more nuanced. And then you can say where your thresholds were. If you decided that 0.46 was in the moderate category, you can kind of go on to clarify that statement and say that based on this, the true correlation is somewhere between moderate and strong. That's as far as you can go. All right. Another way to, this is a little bit heavy, but there's a great paper that is, it's kind of a companion paper to that ASA statement on p-values. Just to give you a bit of context, the ASA statement of p-values came together because the association, these are thousands of professional statisticians, they got together and they were like, okay, we need to say something to the statistical community. There's all this abuse of p-values, all this abuse of NHST. Let's have a coordinated effort, say something that kind of represents us as a society, and that's going to be the statement. So they did that, but as you will probably also be asking yourself, what people did afterwards was, okay, how do we go from there? Like, we understand the problems that you're telling us, but how do we move on? So they had a companion paper, which is called Moving to a World Beyond P is Less Than 0.05. Really, really useful, much denser than the 2-page first paper, but it gives a lot of useful advice. The annoying thing for us is that statisticians don't all agree amongst each other, and they don't even agree on how to interpret a confidence interval. We'll go into different ways that it could be interpreted, but there's like the safest type of interpretation, and some kind of argue that it could be used for different things, which doesn't make our life easier, because if we kind of want to learn how do we move on, and we don't want to insert ourselves into that debate, it could be tricky. But all the advice in this paper is really, really useful. And there's a section in there called "Don't say statistically significant," and don't even kind of indirectly say it, right? So they say whether expressed in words by asterisks in a table, like have you seen those tables with all these asterisks where p-value like didn't pass the threshold or pass the threshold, or people have like these massive correlation matrices and kind of highlight where the correlations are significant or not. Or recently, I've been seeing a lot of figures where people have box plots and they have these like square brackets and they indicate which ones have like 1 asterisk or 2 asterisks or 3 asterisks of significance. Strictly following the advice from the statisticians, they say that that's not useful. We should be having clearly set out research questions. We shouldn't be cherry picking from a context matrix which of the correlations we want to focus on. We should have questions that are like outlining what actual variables we want to compare, and then look at how big the differences were. That's more useful than kind of putting asterisks in a table. All right, so this is an example, not an archaeological one, but it's really useful to kind of show how very subtle changes in the way that we phrase results can have a big impact on how the results are communicated and understood. So Nicole Lazar, who was that co-author on the best practices paper that I wrote, she was the president of the American Statistical Association. I asked her if she had like a really nice example that I could share with people on how rewriting the results to make them more in line with what they were writing about in the statement on p-values, how we can rewrite it, okay? Like, does she have an example? And this is the example that she sent me. It's a study that was carried out during COVID, and the medical researchers, they came to her and they were like, okay, this is what we found. Should we publish it? Like, do you have any advice on how we can reframe it? So the study was about a new treatment for COVID. It was called lopinavir or ritonavir. They didn't say how many individuals were. I think there were like 200 people included in the study. But the result, the way that it was phrased initially, was that mortality difference at 28 days. So you have a control group that didn't receive the treatment. You have the test group that did receive the treatment. Everyone had COVID. In the two groups, they were already at a hospital. The mortality difference at 28 days between the two groups was negative 5.8 percentage points. Okay, they put their confidence interval, 95% confidence interval on it. But notice how big it is. The difference is from negative 17.3% to 5.7%. So notice that 0 is included in there. Really big confidence interval. And the way that the conclusion was phrased was mortality at 28 days was similar in the lopinavir-ritonavir group and the standard care group, okay? 19.2% in the first group survived versus 25.0%. Didn't survive versus 25%. In hospitalized adult patients with severe COVID-19, no benefit was observed with lopinavir-ritonavir treatment beyond standard care. Okay, so that's how the results were phrased. Now, I'm going to put up these red flags of NHSD. Can anyone notice any red flag having been fallen victim to? So they said mortality difference at 28 days was very similar for the two groups. It was negative 5.8 percentage points, massive from negative 17.3 to 5.7. Did they fall victim to any of these red flags? I'm going to take a sip of water. So the red flag that they committed is accepting the null, right? They looked at their confidence interval, noticed that it included 0. See how it's from negative 17.3 of mortality to 5.7 mortality. It included 0. So now it's not significant anymore. So they accepted the null, that there's no benefit from the treatment over not having the treatment. I highlighted here. No benefit was observed. So if you think back a couple slides back, that slippery slope of non-significant, didn't find a significant difference, and now they're talking about no benefit. That's a problem. That's accepting the null. So a better way of phrasing it is to be a little bit more nuanced and a little bit more informative. So instead of just focusing on is the 0 in the interval, they ended up, these are the way that the results were phrased. They said, lopinavir-ritonavir to standard care could result in a clinically large decrease in mortality. Negative 17.3%. That's a large decrease in mortality. but possible mortality differences that are highly compatible with our data range from -17.3, which they said was large decrease, to 5.7. So that was a large increase. Our trial was small, including over 100, only 199 patients, all with severe COVID. Further study of this potentially effective treatment is needed. So now they're not accepting the null anymore. They're not saying there's no benefit anymore. They're saying there could be a big benefit because, mortality decreasing by almost 20%, that's significant. That's meaningful and important. But it could also be small because the confidence interval was quite large. So like small changes in how we report the data could have a big impact. Don't just look at whether significance was achieved. In this case, it wasn't, because the actual impact could be quite large. It could be there. All right, so this is just last step of what to do. I was last year at this event for early career researchers. This is our previous vice chancellor of the Australian National University, Brian Schmidt. He got the Nobel Prize for finding out that the universe was expanding. So he's, he knows his science. And I went to this event. It was like a Q&A session with him. And I raised my hand. And I said, I'm really keen on statistical reform. But I come across a lot of people, particularly, I didn't say names, but I said particularly senior researchers are a little bit resistant to kind of talking about these problems, right? It's hard to include everyone in the discussion. If someone has been doing something for 40 years and it's working for them, why would they need to change now? So I said, what do we do? And he said, you can't teach an old dog new tricks, which is not too helpful. But he just said start from the ground up. You got to start with the students, start with the training, and make sure that the momentum builds from the ground up, because you can't change everyone. So just small steps at a time. So I'm putting it here to say, don't be afraid to step outside of the tradition, right? There's a lot of papers out there that talk about significance, that present a p-value and then accept the null, or just make the results seem very, very transparent, very black and white, when they aren't necessarily black and white. And it might feel really challenging to present the results differently, because there's decades of literature that seems to have this momentum on it, but there's also a lot of literature that says that it's problematic, and that's the literature that we need to be kind of bringing into discussions more. So don't be afraid to step outside what seems to be the norm. It's okay to like, I don't report p-values at all anymore. I just talk about differences, and that's more like, I'm more interested in showing how big a difference was and then interpreting it. So if there's a reviewer that says like you need to show the p-value, I could be like, well, actually, there's a lot of literature that says it might not be helpful. So it's possible to push back. But also, I haven't had too many reviewers say you need to insert p-values. I've heard that it's the case. I've heard a lot of people say that they're afraid to not include p-values or not use statistical significance because they're worried that the reviewers might think that their stats aren't robust enough. I've heard that said, but I haven't actually seen it in action too many times. But if it does come up, it's possible to kind of say there's a lot of literature that supports this new approach. All right. How are we on time? Should we take a break? No. Okay. Mm-hmm. Yep. Oh, yes. Hello, people online. We're going to take a 5-minute break to digest. Oh, 10 minutes. Sorry. So 10 minutes break, a 10-minute break to digest. If you have any questions that come up in the meantime, please feel free to share them on the chat, and we'll be back at 10. if anyone online can't hear, let me know. I'm just gonna have a quick look through. Oh, this doesn't show up, but questions. Please turn on the microphone. Okay. Can you hear it? Can you hear now? We're starting now. Okay, can we hear? Yes, we can hear. Great. Wonderful. Okay. I'm just looking through if there are any questions. Someone asked if there would be a reading list. I can provide a reading list. I still have to prepare my talk for tomorrow, so it might not be tonight. But also, if you go to the paper I mentioned, the one I wrote about statistical training, it's all in there. Like the whole bibliography for that paper is the massive body of literature that I've been drawing on. So if you want references right now, and you're eager to start looking into them, have a look at my paper called How Can We Improve Statistical Training in Archaeology, and the bibliography there has a lot of the useful papers. You can always email me directly to ask questions as well, and I can put together a paper of or like a list of the specific papers that I mentioned in today's presentation. Are there any other questions? I'm trying to see.
If I may add, what we can do is we
Yeah.
can put online the list of bibliography you will prepare. We can put it on the One Archaeological Science website, Andre. Okay. Okay, so
Okay, sounds
Andri, the One Archaeological Science project officer, will email the list that you will prepare to
Wonderful.
all the participants because we have them registered. So
Sounds great. Wonderful.
yeah, I think that's the
Awesome.
most efficient
Great,
thing to
thank
do.
you so much. So it will be ready, and always feel free to email me at any time if anything comes up. Okay, are there any questions about what we talked so far? I know I talk fast. Just get so excited about stuff. But if you ask me to repeat it, I'm gonna say it slower. And if you ask me again, I'm gonna say it even slower. So if there's any parts that I've gone over that are too kind of you'd like me to repeat or rephrase, no, no one online. Okay. So just to summarize, what we talked about so far is different types of statistical thinking. I've hopefully made the case that estimation thinking is more informative than dichotomous thinking. So if we can talk about how big differences are, and talking specifically about this term effect sizes. So anything we can measure is an effect size. And if we talk about that instead of saying whether a result passes an arbitrary threshold, that's more informative. We talked about the fact that confidence intervals are very useful. They allow us to go from descriptive statistics to inferential statistics. So descriptive is everything that has to do with describing a sample. Inferential is going into the territory of using your sample to talk about the underlying population. And sometimes it can be as simple as putting a confidence interval on a mean. And so that's what the next section will be about. But so let's dive into it. I want to talk a little bit about kind of the underlying theory on what confidence intervals are. I'll give you the equation. If you don't like math, don't worry. You can still use confidence intervals. You can calculate them. You can visualize them. You can make really nice figures. We'll make them together. But I do want to show you the equation just to kind of make it clear like where we're coming from. Like what is it that we're actually calculating, and how does it help us? So let's talk a little bit about what they are. Okay, so how can confidence intervals, so CI stands for confidence interval, how can they be used to draw inference? Now, something that's really useful to kind of distinguish between is you might have heard of the terms frequentist statistics and Bayesian statistics, okay? So Bayesian statistics is very common in like chronological modeling. That's conditional probability. So when we take measurements on like ages, like absolute ages of archaeological materials, and incorporate them with relative information. So things about stratigraphy, how things are associated with one another. When we constrain probabilities like that, we go into the realm of Bayesian statistics, okay? But not all statistics is Bayesian. There's some really good resources on how to use Bayesian statistics in chronological modeling, also in just general archaeology. Eric Otorella Castillo, he's the top person on change your view, top right. Oh, what have I done? Oh, it's okay. Okay, all right, good. Okay, so Bayesian statistics, conditional probability, when we constrain kind of actual measurements with like hypotheses, and go into the realm of like testing the different types of hypotheses. Now, what I'm going to be talking about today is this frequentist perspective. So when we look at confidence intervals, they have a very specific, they provide us with very specific information, which is tied to the idea of repeating an experiment or a study many times and getting an idea of, if you repeat an experiment 100 times, what is the most likely outcome you're going to get, okay? So for example, if you run an experiment, you get a mean, you get a confidence interval in every single instance. If you then construct a 95% confidence interval, what that's telling you is that 95% of the times, 95% of those confidence intervals out of 100 that you've created are going to capture the true mean. 5% of the times you're not going to capture the true mean. So that's what it means, okay? You run an experiment over and over. If you use the 95% confidence interval, you'll capture the true mean 95 times. It's going to fall in your confidence interval. 5% of the times it won't. Okay, 5% it's going to fall out and you won't be able to interpret it. If we use 99% confidence intervals, these are going to be wider. In this instance, if you run an experiment over and over and over, let's say you run it 100 times, 99% of those confidence intervals, 99% of the 99% confidence intervals are going to capture the true mean, and 1% isn't. So that's all that this means, okay? We're not talking about the probability of a mean being in a certain location. We're not talking about the probability of capturing something. We're just saying how many of our confidence intervals, if we run a study over and over, how many are going to miss the true effect size versus not. This is going to become clearer in a second. So let's talk a bit about probability. What is probability? Probability is the likelihood of an occurrence. What do we need to calculate it? To calculate a probability of anything, we need to model the distribution of the possible occurrences, okay? And to model the distributions, we have different types of models. The Gaussian, which you've probably heard of, is the most common, so normal distribution. You've got the mean in the middle, and the kind of how steep or how dispersed it is has to do with your standard deviation. If your true variance, so the standard deviation of your population, if it's known, you can use the normal distribution. But if your true variance is not known, we use what's called a t-distribution. It slightly differs from the normal, but it has to do with these kind of degrees of freedom, which we'll get to. Now, how do we calculate the likelihood of an occurrence? We look at the area under a curve. So here's our standard normal distribution. It's got a mean of 0, and it's got standard deviations of 1. So these are called z-scores. But if we basically look at how much area is covered under this curve, you can get any kind of observation. You can see where it places with relation to the mean of your underlying population or underlying distribution, and then kind of say what's the likelihood of actually lying under the curve. So you probably have heard that 2 standard deviations, 68% coverage of the curve. So that literally means that we're just covering up all the area that's shaded, and if we're outside of that, we're kind of in these tails. Okay, so that's 0.5% tail on one side versus on the other. So that's the standard normal distribution. Now, and this allows us to make really simple interpretations. So we can say something like, if our mean is 0, what is the probability that our outcome is less than 1? So then we look at where is 1, and we add up all these probabilities, and that's the probability that something is less than 1, right? We're looking at area under the curve. If we want to know the probability of our outcome being less than 2, we're at 2, and now we look at everything to the left of 2. If we want to know the probability of something being between -1 and 1, we add up 34% and 34% and get our 68%. Okay, so here are the actual percentages based on looking at the area under the curve. So why is it that the standard normal distribution is useful? It's useful, and a standard normal distribution has a mean of 0 and a standard deviation of 1. It's useful because we can compare any kind of data that's normally distributed to it. And what that means is that we can then convert whatever scale we have into our units of standard deviation and calculate our area under the curve using that standard normal distribution, okay? All we have to do to compare a distribution using any units into our standard normal distribution is we just divide by the standard deviation, okay? So now, once we divide, our x-axis is no longer in the units of our z-scores, but it's in the units of, so it's no longer in the units that we measure in, but it's in the units of the z-scores. So for example, if we want to make predictions about IQ scores, okay, IQ scores have an average of 0 and they have a standard deviation of 10. So most people are at 100. So one standard deviation is 110, two standard deviations is 120, and going the opposite direction, we go down to 80 and 70. So then we can use the same principle of looking at this area under the curve by putting kind of our thresholds and deciding what we're interested in. So for example, if we're interested in how likely is it that someone falls between 90 and 110, which is at 34%, 34%. So the likelihood of someone having an IQ score between 90 and 110 is 68%. Okay, it's as simple as that. How likely is a score above 120? Here's 120. Above it is 2.5%. So we look at the area under the curve, we see where our observation is. These are hypothetical observations, and then calculate the area under the curve. And that allows us to kind of talk about the probability of an occurrence. Okay, now, what if we want to go the other way? From an observation to an area, we want to go from area to these z-scores. We want to say, here's a distribution that we're interested in. Here are some thresholds. We want to be between, I don't know, stature of 155 and stature of 165, with the mean being at 160. We can go the other way by looking at our standard normal distribution and kind of setting our z-scores on the y-axis to be whatever we would like them to be. And there's some really useful resources online that allow us to do this. So if we want to, for example, look at like 95% of the coverage under a curve, we would need to like toggle on our x-axis, select our z-scores, and it turns out that to get coverage of 95%, our z-scores need to be between -1.96 and 1.96. And this is all really important. It might not be apparent quite yet, but it is going to be apparent very, very soon. So I'll actually just show you really quickly online how we can convert. So I'm going to go to the new statistics.com. Okay, so this is the website for the textbook that I've been talking about, Introduction to the New Statistics. If you go to the tab at the top, it says ESCI. ESCI stands for Estimation Statistics with Confidence Intervals. There's two things you can select, ESCI and Jamovi, which we'll look at later today, and ESCI Web. If you go to ESCI Web, you can have a look at these distributions and play with it on your own. So on the left-hand side, you've got these distributions. There you go. And here is our standard normal distribution. It's got a mean of 0, and it's got these z-scores. So to know what z-scores you need, remember z-scores are your standard deviation units. You can toggle, let's say you go 2 tails so that we're taking into account both of the ends of the distributions. You color in your area. So notice now our z-scores are like way over there at -5 and way over here at +5. So it's pretty much covering 100% of the area under the curve. If I want to constrain it, if I want to know where I need to be to get 95% coverage under the curve, you can grab one of these toggles and then see how you go. And if you go to -1.95, you can move them a little bit more. So now I'm just using that button. And eventually it's going to get to 9. Oh, there it is. 9. So 0.95 is 95% coverage under the curve. So we need to be between this z-score and that z-score. But you can decide that the coverage you're interested in can be whatever you want it to be. If you want it to be 99.74%, that's what it is. There's your z-score there, and there's your z-score there. So this is just a tool that you can use to kind of play around with what z-scores look like, what the area under the curve is. And this is important. It's going to become very clear why very soon. So to actually calculate a confidence interval, we need to understand how the population, the true population we're trying to sample, how it relates to what we're actually measuring. And we need to visualize redoing the same experiment over and over and over again and getting a distribution of what the outcome is. So now is the time for the dance of the confidence intervals. Okay, so we're in SQWeb. If we go to our home, okay, show details, go there, open. Okay, so if you go to dances, the first thing at the top, dances. Here you can select whatever population, whatever descriptive statistics you want. So we've got it set to the default, which is mean of 50. So you can see your mean of 50 and standard deviation of 20. Okay, so I'm going to run an experiment, and the experiment is going to take a certain number of samples from this underlying distribution, and you can set it to be whatever you like. You can have the mean higher, so now the mean is at 64. You can have it lower, so now the mean is at like 29, and you can have the standard deviation wider, so it's more spread out. You can have the standard deviation narrower, so it's right here. I'm gonna go back to having it sort of in the middle of the screen. There you go, and having it. So now we've got mean of 51 and standard deviation of 19. I'm going to select how many individual samples I'm going to draw at a time for each experiment for my underlying population. It's set to 20. Let's go to 25. So each of my experiments is going to have an n equals 25. So what I can do now is I can take a sample, okay? And what we can see is, see those little circles up there? That's my hypothetical simulated set of 25 samples from my underlying population. Population's at the top, set of 20 is under it. And then the green dot over here is the mean of that grab of 25 samples. And I can do it again. I can press take sample, and now I have another set of 25 samples, and they have a mean that's a little bit lower than the first mean. And then I can do it again. And now here's the next set of 25 samples from the same underlying population, and see how the means are very close to each other. The means are in the green. So what I'm going to do is I'm going to actually let it run for a while and then see what happens if the same experiment goes on and on and on. So I'm just going to press run and stop, and notice how these are the means of each of my experiments, each of my independent studies. Each has a sample size of 25. And notice what's happening. This is the distribution of the means. So now we're not looking at how widely distributed are the individual samples. We're looking at how widely distributed are the overall means of each experiment. And notice what's happening. It's giving us a normal distribution, and that's not by chance. So I'm gonna stop it now, and I'm gonna put my standard error lines on it. There you go. Here's the red is the distribution of the sampling mean. I can put standard error lines on them, and I can put my confidence interval. So when we talk about confidence interval, we're talking about describing this distribution here. Okay, so all I've said so far about z-scores and standard normal distribution is to get to this idea that when we have a mean, we want to visualize what the mean is doing in the context of what it would be doing if you were just rerunning the same experiment over and over and over. If you were rerunning the same experiment over and over and over, all the means would have a normal distribution, and most of the means would fall close to the true mean, which here is 51. And that's my distribution of the sampling mean. There's a very easy way to convert between the true standard deviation of my underlying population and the distribution of your sampling mean. And that is to divide by the square root of n. Okay, so if I take the square root of 25, divide my standard deviation up there, I get what's called the standard error. Okay, this is really important. Standard error is basically a standard deviation of the distribution of the sampling mean. Does that make sense? Should I say it again? I should say it again. So we've got our experiment, underlying population. We're taking 25 grabs of samples at a time. Each time I take my 25 samples, I calculate a mean, and these are all the means of all the experiments I've done. Okay, and so overall, what I want to know is how likely it is that my mean of each individual experiment how likely is it that it comes close to the true mean? And the only way to talk about it is to talk about it within the context of what the distribution of these sampling means is doing. So we've got our distribution here. If we put our standard deviations of the sampling means, those sampling means are standard deviations of the sampling means, is a standard error. And that's how we calculate a confidence interval. See how we've got this green bracket here? This is our 95% confidence interval, because you can set it to something different. If you want to set it to like 99, let's run it again. We're going to clear it. We're going to stay with that, run it again. And this time I want to put confidence intervals on it. Okay. So see how each of my means now has a confidence interval on it. And that confidence interval is most of the time gonna capture the true mean. The true mean is over here, but sometimes it doesn't. And that's where that's where the confidence levels come into play. Where so far we haven't had any red mean because we have a really high confidence. But let's see what happens if we go back to 95. If you go back to 95, run and stop again. Notice how most of them are green, but every once in a while, we're gonna get a red one. Come on, red. Come on, red. 5% of them will be red. I've got to, maybe I need to adjust a little bit. Let's make this standard deviation a bit wider. Okay. We'd have to let it run for a really long time. But the main point here is that we're relating to what's happening in the population, what's happening with the distribution of the sampling mean, and that's our standard deviation. That's a standard error, and that's a standard deviation of the underlying population. So that's how we calculate a confidence interval. Okay, we look at the distribution of the sampling mean. So back to my slides. This is it just labeled. That's a 95% confidence interval. That's the distribution of sampling mean. The standard error line. So that's 1 standard error, 2 standard error, 3 standard error. And to convert from standard deviation to standard error, you divide by the square root of n. Okay, and here's the actual equation. If you're worried about math, don't worry too much. The main thing to notice is that in every confidence interval, you've got 2 numbers in there. Okay, so you've got square brackets, you've got 2 numbers. The first number is the lower limit of your confidence interval. The second part is the upper limit of the confidence interval. And in the middle of it, you've got the mean. Okay, and to calculate the lower limit, you take your mean, your point estimate, and you subtract whatever you set your confidence level to be, and the confidence level, that's how the z-scores come into play. You take your z-score that you're interested in, you multiply that by your standard error, and that's your lower limit. To get the upper limit, you take your mean, your point estimate, and you add your standard error times your score that you're interested in. Each of these is also called a margin of error. So you could say that you're calculating this by taking n minus the margin of error, or comma n plus the margin of error. So that's when your underlying standard deviation of your population is known. That's rarely the case. When it's unknown, we have to use these t-scores. So we use a slightly different distribution, which is very close to the standard normal distribution if the sample size is large. But if the sample size is small, the 2 distributions vary a little bit. So that's why it's nice to have large sample sizes, because our underlying kind of theory on how these are calculated, it works out better. Our confidence intervals are truer representatives of what you're looking for. But when the underlying standard deviation is not known, you take your point estimate, you multiply by your t-score, where your level of confidence is, and it depends on the degrees of freedom, you multiply it by the standard error. So similar process, and then you do the same thing to get their upper limit. So each confidence interval, 2 numbers, mean is in the middle, upper and lower limit. Now, how do we actually interpret confidence intervals? Oh, see, I was looking for one to be red. There's a red. There's a red confidence interval, which didn't capture our true mean. So 5% of these are not going to capture the true mean. That's where those confidence levels come in. And we always have to to expect that some of our experiments are not going to capture the true mean, and that's just the way it is. So not all statisticians agree on how confidence intervals can be interpreted. The safest way is to use what I talked about, the frequentist perspective, to just say, if you ran the same experiment 100 times and you use 95% confidence intervals, 95% of them will capture the true mean, 5% of them will not, okay? So that's the first way to interpret it. This is also from the textbook Introduction to the New Statistics. There's 4 different ways of interpreting them that the authors talk about. So one is that the CI is one from the dance. This is our dance of our confidence intervals. Most of them are going to be green. One of them is red. Another way to interpret them, and this is where we get into kind of the debates between statisticians, some of them talk about the plausibility of the measured values across the interval. So if you have your confidence interval, you put a normal distribution on it, you can say that the middle, where the mean is, that's the highest probability of where the true mean lies, and you kind of taper towards the end. So at the limits, that's where the probability of the true mean being there is the lowest, but it's highest at the middle. It's a good way of looking at it, but not all statisticians say we should go there. Another way to look at what confidence intervals tell us is to look at this margin of error. So to get our upper and lower limits, they say that the margin of error is the most likely maximum error of estimation. So important to distinguish between instrument error. Instrument error is the error that you get through measurement. Estimation error is the statistical error, right? So if we calculate confidence intervals, that's the statistical error. That's the estimation error that we're getting, which is very much constrained by what our data is doing. But looking at the margin of error, that's where the most likely maximum and minimum errors are going to be. Another way of interpreting them is to look at what they tell us in terms of the replication. So what would happen next time you run the same experiment? Now, it's not important to go into why it's like this, but it turns out that if you use a 95% confidence interval, where that interval lies, there's an 83% chance that CI will capture the next mean. And there's another kind of simulation you can do online, which shows you with every new experiment that you run, when it captures the next mean, it lights up, but every once in a while, it actually doesn't capture the next mean. So if you want to know why it's 83%, there's a paper on it. You can also read about it in the textbook. It's not important that we go into the math today, but every confidence interval does give us some insight into what the next outcome is going to be of the next experiment. If you use 95% CIs, the likelihood that you'll capture the next mean isn't 95, it's actually 83%, but we don't need to worry about the math there. So different ways to interpret. The best way is just to stick with the frequentist perspective. Not everyone agrees that the margin of error is the likely maximum error. Not everyone agrees about talking about the plausibility. That gets into a very kind of Bayesian framework. When you start talking about like plausibility intervals, it's going a bit Bayesian. In fact, the author of the textbook once shared with me that someone was like, just admit it, you're Bayesian. But sticking with the frequentist perspective is the safest type of interpretation that we can make. All right, here's an example. I'll be talking about this in my talk tomorrow, but an example of how you can present results without relying on p-values, without relying on statistical significance, but just looking at differences and expressing them using confidence intervals, which allow us to talk about where the true underlying effect is most likely to lie. So this is a paper that I published recently. It has to do with feasting in early Neolithic Iran, and I measured 5 individuals, and I measured their stable oxygen isotope values. I did it in situ. We'll talk all about it tomorrow. But what I had 4 individuals that all had very overlapping values. So the ones that are shown in gray, they're all overlapping, okay? But there's one individual, the one shown in red, had different values to all the other 4. Okay, and that's really interesting and important for my interpretations. And that difference was shown both in the oxygen isotope values and the strontium isotope values. So they have, most likely, that one individual didn't come from the same area that the other 4 individuals were grazing. Now, to actually talk about these differences, one thing I could do is just to calculate Is there a statistical significant difference between the red individual and the 4 gray individual? I don't think that's very useful, because I think it's more useful to talk about how big that difference is. And so that's what I did in the paper. I said, I've got this one individual, ASB133, SB449, that's the red, and the 4 are numbered between 133 and 402. And I said, the mean of the gray group that's up here, I said what the N was. Overall, there was 167 measurements. I took their mean. I subtracted it from the mean of my red individual. I had 88 measurements. And the difference, the true difference between those two was 2.8 per mil, and a 95% confidence interval was between 2.5 and 3.1. So now I can talk about how big the difference is. The most likely difference between the gray and the red is 2.8, but it could very well also be 2.5 or 3.1, most likely. That's where the true difference most likely lies. And now I can talk about a true difference. I don't need to use p-values. I don't even need to make declarations about statistical significance. I can use actual estimates of what I found to draw my interpretations. So now what I want to do is I want to get our hands on some confidence intervals. So I'd like you to do 2 things. If you can please go to this website called jamovi.org. I'm going to put it up here. So jamovi.org. You'll get to something like here. Looks like that. And then you get a choice of what to download. I suggest you download the desktop version. So download Jamovi on the desktop. When you click on it, there's also going to be a couple of options. I don't think any of the current ones are less than 2.6.4. That, like, back in the day when that was was very recent, we had to make sure that we had a recent version of the software. You can select the current or the solid version. I think I have Apple, so I would select the first one. But it doesn't matter which of the options you use, as long as it's now higher than 2.6.4, which everything is. So download your Jamovi. Oh, thank you. It might take a little bit of time. It takes a little bit of time. Yeah. No, I understand. And while it's downloading, is everyone able to start the download? Everyone's happy? Okay, good. So you let it run. And while it's also downloading, I'd also like you to create a login on osf.io. So this is the Open Science Framework, osf.io. To be able to access all my materials, you need an account. You don't need to go through like the institution login. I think it gives you an option to like go through an institution to sign up. You can just put a personal email in there or whatever email you want to use, but register for an account on osf.io. And then once you have one, you'll be able to go into my project, which I've created for this workshop, and get all my resources there. Okay, so shout issues, and I'm gonna have a look at online if someone. Okay, no one seems to have any problems so far. Just while we're waiting, I can talk a little bit about OSF. So OSF is really, really useful for many reasons. You can put like preprints out there. If you have a paper that is going through review and you want to put a preprint, this is one of the repositories that takes preprints. But you can also use it to share materials with a project. So I've got some collaborators in different countries, and I have really massive files that are too big to send over email. So I just create a profile for every project on OSF, and then everyone who's added as a collaborator can then go in and kind of add more files, download my files. And the nice thing is it keeps track of this like history. So if someone changes something or if someone uploads something, it has a timestamp. So you can see kind of how different versions are updated. I can show you so if I go to my project, there's one that I created for the paper I'll be talking about tomorrow. So it's a really nice way to kind of put files together. This is how I kind of do reproducibility stuff for my papers. I upload all the supplementary information, Sometimes I have like walkthroughs about how you can get the results. I have some massive photographs, like microscope photographs for some of the board samples I'll be talking about tomorrow. I just put that, they were too big to attach a supplementary material with the journal that I was publishing with, so I put them all on OSF. So it's a really nice platform to have a profile on because it's useful for collaboration and making data accessible. So are you on OSF? If you're on OSF, you can either search for a project called Fundamental Statistics for Isotopic Archaeology. So that's the name of today's workshop. Or down here, I've got a link that you can type in and it should take you straight to it. So osf.io/d4mbw/, that's that specific folder. But you should be able to just search for it with the name. So if you type in fundamental statistics for, you got it, isotopic archaeology, it should come up. Is everyone able to access it? Everyone has OSF? Great. So what you'll come, this is the front page of today's workshop. Eventually, we'll go into files. So up there, see how it says files? If you click on it, I've got a whole bunch of files that we'll be using today. There's 3 different folders. One is called confidence intervals, one is called tidy data, one is called meta-analyses. And I've also got a copy of the Kofovona paper because I'll be referring to it a lot. So if you'd like to open it now, and the full data set as well is over there. So that's OSF. Has everyone downloaded Jamovi by now? Is everyone? It takes a little bit of time. Okay, yeah. That's okay. We can, I can start showing you kind of like what it looks like. You can. I usually recommend people to use the desktop version, but I haven't also heard of any like negative experiences with using the cloud. So that might be okay. We'll wait a couple minutes. I can also start kind of introducing the platform. Okay, should I start talking about what it looks like what the platform looks like even before it's downloaded? And then once everyone is able to get in, we'll do it together. So Jamovi is a really, really nice program because it makes it easy to calculate confidence intervals. Lo and behold, not every program out there actually gives you confidence intervals. So Excel won't do it for you easily. A lot of people use SPSS, I think. The author of the textbook, Introduction to the New Statistics, I asked him a question. I was like, I've got some students who came to me, they really want to use SPSS to calculate confidence intervals. And he's told me that for 30 years, he's been trying to find a way to make it work and he just didn't. Like SPSS won't give you confidence intervals. That's why we're downloading this because it makes it really, really easy. You can also do it in R. Actually, maybe while, no, sorry. Let's not skip the gun. We'll do R after we do this. But the actual program, it's really useful not only because it's free, but also because people can create their packages and then you can use them as these plugins. So the textbook that I use, the authors of the textbook created this plugin, which is called ESCI, Estimations Statistics with Confidence Intervals. And when you download the plugin, which you will once you have the program, you get a button up top there, which is ESCI. So all the examples, all the kind of walkthroughs that the textbook has, you can follow it on your own because it's a free software. And the plugin was written specifically for that textbook. It's okay. Yeah, not all programs allow it, but if they have it or if they have a package, great. Awesome. Okay, so I'll show you an example of one confidence interval even before you get your hands on it. So once you have the package, the one called ESCI, you click on it and you have a lot of different options of what you can do. You can work with means and medians. So that's a type of effect size. You can work with correlations. That's another effect size, proportions, meta-analyses. The first thing we'll be doing is we'll be looking at means and medians for single group and two group. So this is the simplest thing we can do. We can have a mean, put a confidence interval on one mean, or calculate the difference between two means and put a confidence interval on that. So I'll just show you an example just with a single group. So I'll click on single group. And there's a way to do this using both full data sets. So if someone shares a data set with you, or if you download it on an online repository, you can put the data set in Jamovi and calculate the confidence intervals using that data set. But if you don't have the data set available, you can just calculate it using summary statistics, which is great, because you can do this really easily while reading papers and just put your confidence interval on it. So just as an example, we're going to use summary statistics, and I want to calculate the confidence interval on mean of 7. So I'm going to say 7 plus or minus 1. Whoop. And my sample size is going to be 10. Okay, so I've got a mean 7 plus or minus 1 using n equals 10. And I'm going to press enter. And here's my confidence interval. Yay, it's very simple. So there's two things that come out as the output. One is the table, which says what is your outcome variable. You could call it, I don't know, stable nitrogen isotope value. So now it's saying M, which is your mean, is 7. The lower limit of your confidence interval is 6.28. The upper limit of your confidence interval is 7.72. It's telling you that your standard deviation, which here is abbreviated with S, is 1. Your sample size is 10. Okay. You could, if you want, click on this extra details over here, which will just give you extra information. It's going to tell you what that margin of error. Remember, the margin of error is what we use to calculate the lower and the upper limits of the confidence intervals. So our margin of error is 0.72 in this case. But for that very simple example of a mean of 7 plus or minus 1, this figure is showing us that the confidence interval runs from 6.28 to 7.72. So the best way to interpret this is that the true mean, if this is our descriptive for something we're measuring, the true mean most likely lies somewhere in this interval. And that's really useful to say because it's not descriptive. We're not talking about how our data is distributed. We're talking about where the true mean is most likely to lie. And that's that allows us to talk about the underlying population. Now, I will, while it's still downloading, I'm going to go back to my OSF profile here. So if you click on the first folder, there's a couple of examples in there. And these same examples are also in the paper I mentioned, the stats paper that I wrote recently. So I've uploaded these PDFs there that allow you to kind of recreate all the examples that we're going to be we'll be doing together. So example 1 walkthrough is the one that I just did. It's 7 plus or minus 1. And notice it's going to tell you that to follow this walkthrough, you'll need to have Jamovi, you'll need to have that plugin with Eski. We're going to get it together soon, but it tells you what is it that you want to put your confidence interval on. It tells you where to go, that you have to click on single group, you have to go to analyze summary data, and then it's going to give you the output. So if you miss anything from what we do today, you can go over these walkthroughs and follow on your own. It's all there, and it's available. Okay, is Jamovi down? Is it still downloading? It's still downloading. Is it close? For you then. Okay, so it's fine. Okay. How many people are still waiting? Still waiting? Okay. Okay, let's give it a couple more minutes. Yep. Yes, have any questions? How do I find the files in OSF? Sorry. Oh, I'm seeing it on my screen, the chat. It's not showing up there. Yeah. How do I find the files in OSF? Oh, so OSF, once you have a profile set up, you should be able to go to like the main page of it. And if you type the name of this workshop into the search bar, the name of this workshop is Fundamental Statistics for Isotope Archaeology. It's going to take you there. Alternatively, you can follow this link, and that's going to take you there directly. So that's the open access link. You just need a profile on OSF to be able to actually follow it. But that should be doable. Are there any other questions? Okay. No one's shouting with any questions. So maybe let's start going through the other examples. If you still don't have Jamovi, hopefully you'll be able to catch up soon, but also all the walkthroughs are on OSF, so nothing will be missed. Let's go to a new folder. Yes.
Can we install the plugin Esky?
That's what we're going to do right
sorry.
now. Yeah. So for those of you who have downloaded Jamovi, you should be able to see this view. Is everyone seeing this view? Who? Yes? Who has Jamovi? Okay. So if you look at your upper right corner, there's a thing called plus modules. So click on that. Click on plus modules and click on the first option, which is Jamovi library. Okay, and here's a list of all the plugins that are available through Jamovi. And if you scroll down, or you can even type it, but I'm going to scroll down to something called Esky, Estimation Statistics with Confidence Interval, and click on Install. And that one should be much faster. If you don't want to scroll, you can type into the search bar Esky, ESCI, and it will come up. Is everyone's happy with the library? Everyone can at least start the download for the package. Cool. Woo. All right. So once you have the package, you should be able to see this button. Is everyone seeing the button? Great. Is anyone not seeing the button? Okay. If you're not seeing something, just shout, or if it looks like I don't see a hand going up, please let me know. Okay, so everyone should be able to see this main view with Esky at the top. You don't need to see the one with the R, that's okay. So click on Esky, and this time, let's go to two groups. So I want to calculate a difference between the means of two groups, and I want that difference to have its own confidence interval, which will tell me where the true difference is most likely to lie. So I'm going to click on two groups, and I want to go through an example, which is actually from my Kufovano paper. My Kufovano paper is over here. Whoop, nope. I just a little bit. Okay, that's not it. I can't see because the Zoom is covering things. Okay, there we are. Integrated stable isotope data set for Kufovano. If we go to table 1, which is on like page 7 of the paper, we can see that I've measured some free threshing wheat values, some whole barley values. I've got the delta 13C, delta 15N, and then I've got this big delta 13C, which is a conversion. We can talk about why that's done. It's done for plant isotope studies. But notice how I've given the mean of this big delta 13C of my wheat, so average of all wheat, is 17.0. Right? Am I reading the right line? So 16.5. I've got a wrong angle. So 16.5, and then the standard deviation is 0.5. Okay, so that's descriptive, right? We've got the mean and the standard deviation of the free threshing wheat. We've got the same thing for the hulled barley. The mean of hulled barley is 18.4, and the standard deviation of this group is 0.4. So those are my descriptive statistics. Now I want to know, what is the difference between these two means and what's the confidence interval on that difference? So we're just going to take these numbers and we're going to plug them into Esky and Jamovi. So once you click on two groups, so Esky two groups, you'll get to this window. There's two tabs. One is called Analyze Full Data. That's if you have the data. If you don't have the data set, you click on Analyze Summary Data. Once you click on Analyze Summary Data, you've got this view over here, and you can plug in the numbers. I'm going to say that my reference group is my wheat, and my comparison group is my barley. So wheat, barley. My mean of wheat is 16.5. My standard deviation of wheat is 0.5. My sample size was 13. My barley was 18.4. My standard deviation of the barley was 0.4 and N of 7. And then outcome is difference between big delta 13C. And it's going to be wheat minus barley. So I just typed in what I'd like for the here on my axis, but you don't have to change it if you don't like. Okay, so all I've done so far is I've taken my descriptive statistics for my wheat, for my barley. They both have a mean, both have a standard deviation, both have a sample size. And now that I've plugged it in, I get an outcome, which is telling me it's calculated the difference and it's put a confidence interval on it. So it's saying that that's my outcome variable. The barley, that's the mean. The wheat, that's the mean. It gave me the confidence intervals for the individual groups. So the lower limit of the confidence interval for barley is 18.03. The upper limit of the barley is 18.77. For the wheat, it's 16.23, 16.77. Now, if you scroll down, you'll see the barley minus wheat. Oh, wait, hold on. I labeled this wrong. I'm gonna just say difference there. So it's saying that the difference between the two is 1.9. But sorry, I'm looking at the standardized. Let's just not go there so fast. I'm jumping ahead. The difference is 1.9. The lower limit is 1.4 and upper limit is 2.4 ish per mil. So that's my confidence interval on the difference. Is everyone able to see this? How can I help? It's correct? Everyone else okay? Yeah. Okay. Awesome. So we got two groups. We calculate the difference. The difference is in the table, which is called mean difference. On the bottom, it's saying what is being subtracted from what. Wheat is being subtracted from barley, and that's the difference. So the way to interpret this is to say that the true difference between my wheat and barley most likely lies somewhere between 1.4 and 2.4. So that's better than saying 1.9 because 1.9 is just a number. It has no uncertainty on it. But when we put that uncertainty on it, we can talk about that. Now we have an inferential statistic, and we can talk about where the true mean most likely lies. And if you scroll down, it gives you this really nice image which visualizes that difference between the two groups. So it gives you the mean of the wheat, gives you the mean of the barley, calculates the difference between the means, and the mean, it's the difference between the means has its own confidence interval on it, which you can ballpark from this kind of floating axis. The MDiff, that's the difference between the means, and it has its own axis on there just so you can see what the limits of the confidence intervals are. So you can see that the upper one is, what was it, 2.4, there we are, 2.4, and the lower one is 1.4. Nice. It takes time. No, it's so useful. I love this program. It makes it really, really easy. Yeah. Does anyone have any questions? No. Should we move to the next example? All right, let's move to, if you want, you can save it. So up at the top left corner, what I learned recently, that this is called a kebab. So see how there's a line? It's called a kebab. So if you click on the kebab, you can go save as, and then save that specific document. So next time you open it, your graph will be there, the outcome table will be there, everything will be there. You could also, copy this and put it in a document. So if you click on your figure, come on, click. Okay, you double click, so control click. And it gives you the option to copy it or to export it. You could also copy everything, not just the image. You could copy the table and put it straight into a dissertation or straight into a publication. So it makes it really easy to use. If you want to see the individual measurements, you can't see them here because we're using summary data. But if we had the original data set and did this with the original data set, which we'll get to in a while, you could also put in the option of showing all your individual data, which is really nice. It kind of shows you the relationship between the distribution of the points and the actual confidence interval on the mean of the points. All right, let's go to our next example. So now we've gone through example 2. So if you're following along in OSF, so we're in files. So we've gone over example 1, We're in the confidence intervals folder. We've gone over example 1, that was 7.0 plus or minus 1. Example 2 is the one we just did, wheat or barley. Let's go through example 3. And that one is looking at, again, putting in 95% confidence interval and a difference between means. But this time we'll be looking at the measurements of the pigs, the pig delta 15N from Kufovono, and the tissue enrichment. Okay, so I want to basically use the value of the pigs to estimate what the value of the diet, the delta 15N value of the diet that the pig is eating. We're going to subtract the enrichment from it. So let's open a new file, click on the kebab and new. And once again, we go to ESCI at the top and 2 groups. Again, analyze summary data. And this time my reference will be the pigs. So pig. And then my comparison group, this is not an actual group, but what I want to do is I want to subtract tissue enrichment, which is 5-ish, 5 per mil. So I'm going to say tissue enrichment. The mean of the pigs, we can go to the Kufovono paper to get it, but I've got it written down here. It's 5.9 plus or minus 0.9. And then the sample size was 23. And the tissue enrichment is 5.0. I'm going to say the standard deviation is 1.0. Now, I don't actually have a sample size, which was used to calculate the tissue enrichment. So I'm going to have to kind of be creative and use a hypothetical sample size. I'm going to put in 20, but we can actually play with what the outcome would be if we have different sample sizes. So we've got the mean of pig delta 15N, 5.9 plus or minus 0.9. The sample size is 23. And then the tissue enrichment is 5.0 plus or minus 1 and 20. There we are. You can label your outcome variable. You can say stable, nitrogen, isotope, value, and then click enter. And your outcome will be here. So once again, if you go to the mean difference table, it's going to say what the tissue enrichment is, what the confidence interval on it is. It's going to say what the pig value is and what the confidence interval around that is. It's going to subtract it. Now, hold on. Tissue enrichment minus pig. I want to actually go the other way. The way Jamovi calculates a difference is it does M2 minus M1, and I've labeled M2 as tissue enrichment. So I'm just going to flip the two just so we're in the positives. The numbers are the same. It just depends on what you decide is your mean 1 and mean 2. So I'm going to put tissue enrichment here. Tissue enrichment and pig. 5.9, 0.9, and 23. 5.0, 1, and then 20. Okay, so we're subtracting, we're starting with the pigs and we're subtracting the tissue enrichment. So what this is saying is that the value, the nitrogen isotope value of the diet that these pigs were eating is 0.9 with a confidence interval from like 0.3 to 1.5. So that's something we really need to pay attention in interpreting. We can't just say that the diet was 0.9 per mil. That's not a good estimate. We need to put a confidence interval on it to talk about where the true value of the diet is most likely to lie. And here this is saying to us that the true value is most likely between 0.3 and 1.5 per mil. And if we want to look at the figure again, there we are, our tissue enrichment. Second mean is the first mean, and the difference is there, and you can pay attention to where the limits are. So that's really nice. If you don't want the y-axis to be so long, it's basically listing everything that's showing in the figure. You can, I think, you can go delta 15. You can make the actual name of the outcome variable shorter, but you can't, in Jamovi, change the fact that it's saying mean and 95% confidence interval. There is, for the people who like R, there is an ESCI package that works in R that produces very similar figures like this, but there's a bit more coding involved in it. But this is the simplest way of going about it. But in R, it's really easy to change the actual y-axis label. But it's not, I mean, nothing is incorrect about what we're seeing here. All right, everyone is happy with this example. So that was example 3, subtracting tissue enrichment from pigs. Let's now look at the example of dogs. So if we go to my Gufona paper, I talked about middle Neolithic and late Neolithic dogs. Dog, am I going to find it if I say difference? No. I think I'm going to try to scroll to it. Or, okay. Maybe I don't need to find where it actually appears in the text. But if we look at what the actual measurements were of the dog, here's the dog group. There's the average of all the dogs. There's the standard deviation of all the dogs. I've got my middle Neolithic dog, my late Neolithic dogs. Now, in the paper, I talk in very kind of NHST way about, is there statistical significance between my late Neolithic and my middle Neolithic dogs? And that's one way of doing it. What I'm more interested in now is to see how big the difference is. I don't care if it crosses significance thresholds, but what's the difference and what's the precision around the difference? So let's now plug those values in of the middle Neolithic and the late Neolithic dogs into a new folder. So I'm going to open up, I'm going to open a new file, jamovi new, and we'll again go to ESCI, to groups, analyze summary data, and this time we're going to have MN dog and LN dog, and the mean of the middle Neolithic is, now we're looking at carbon isotope values, so negative 18.6 plus or minus 0.5, and late Neolithic is negative 19.6 plus or minus 0.2. Have I got that right? 18.6, 0.5, 19.6, 0.2. And the first sample size, I have massively small sample sizes. You will notice that these aren't ideal, 3 and 4. And my outcome variable is delta 13C. And there we are. So again, looking at that, the table called mean difference, it's saying that the difference between my middle Neolithic and late Neolithic dogs is 1 per mil. We're subtracting middle from late. So the middle Neolithic is larger, that's why it's negative, but the actual confidence interval is from negative 1.7 to negative 0.3. So plausibly, this is from not very big at all, like not really anything I would want to interpret, to something that's possibly interpretable. And that's very common to find an output where your mean is like, okay, maybe it's not very large, but it's really important to pay attention to where the limits are, because if on one end the limit is interpretable, like a difference of 1.7 is not small, with the other end being 0.3, that's not a difference I'd really want to interpret. So we're in the territory of kind of getting results that aren't really showing us much, because they could be meaningful, but they might also not. And that's a little bit tricky. If we scroll down, again, we're seeing the difference, MN, LN, and our difference is around 1 per mil. All right, is everyone happy with this example so far? Good. And no one's online with questions. Let's see. Can I switch the reference group? Oh, there's a question online. Can I switch the reference group and comparison group so I have positive mean differences to interpret? Yes, absolutely. It doesn't matter which one your reference group is and which one your comparison. The numbers are going to be the same. It's just where the directionality of it is going to impact whether it's positive or negative. But when you actually make your interpretations, you're going to know the directionality. So if you're subtracting middle Neolithic from late Neolithic versus late Neolithic from middle Neolithic, you're always going to know, like interpreting the results, you're going to say what you're subtracting from what. So it doesn't matter if it's positive or negative. The numbers are the same. The confidence interval limits are the same. The way jamovi is set up, it subtracts the second mean from the first mean. Some programs subtract the first mean from the second mean. It really doesn't matter as long as you are consistent with talking about it in your in the actual paper. So it's up to you. Thank you. Wonderful. All right. So next, let's look at actually a different type of effect size. Let's look at proportions. Proportions are really useful because they are everywhere. And oftentimes we get results where we might know about like how many pots had a specific type of residue in it, or how many people had a specific type of disease in it, disease showing up on their bones. And proportions are a really useful way of talking about these differences. Proportion is just a percentage divided by 100. But the great thing about what we're talking about today is we can put a confidence interval on a proportion. So then we can talk about where the true proportion is most likely to lie. So I've got an example under number 5. So if you open up number 5, it talks about, this is a hypothetical example, and it's talking about residue in ceramics from 2 different periods. When it opens. Okay, so let's assume that we've got 2 different periods. We've got, I think, the Bronze Age and Iron Age. And in the Bronze Age, 100 out of 500 ceramic sherds contained organic residue of milk. That's my first group. 100 out of 500 had the residue. In the second group, in the Iron Age, 130 out of 500 had the residue. Okay, so my sample sizes are the same. I've got 500 pots from the Bronze Age, 500 pots or ceramic sherds from the Iron Age. But in the first instance, I've got 100 of the sherds are showing residue of milk. In the second instance, 130 are showing residue of milk. How do we interpret it? How can we actually talk about whether or not there is an increase in the amount of milk that's being represented in this data set? Well, the first thing to do is to put a confidence interval on the difference of the proportions that we found. Now, proportions are really easy to calculate in Jamovi and everywhere else because they don't depend on a standard deviation. All you need is your total count and your case count. How many pots had lipid residue? What was your total? And the proportions are right there. So we're going to go to Jamovi. Open up a new file. So open new. Now we're going to go to ESCI, and under proportion, we're going to select 2 groups because we've got 2 groups, Bronze Age and Iron Age. Proportions to groups. And once again, go to Analyze Summary Data. Boom. And now we just have to organize ourselves to make sure that the right numbers are plugged in the right place. I'm actually going to open this just to make sure we're doing it the right way. So we're going to put at the top, we're going to have the phase, so Bronze Age, Iron Age, and on the side, we're going to have the presence and absence of dairy residue. So what you want to do is you want to copy all of that information into your table. So the grouping variable is phase. Oh, open. Why can't I type? Oh my goodness. 2 groups. Okay, summary data. Grouping variable. Why can't I? Not allowing me to edit. One second. Too many things in there. I'm just going to close my Jamovi and open it again. Maybe I've got too much stuff open. Okay. All right, so ESCI, proportions, 2 groups, summary data, and why can't, it's not, are you able to edit it? If you click on, so in the past, every time I clicked on that box, it's editable. Is it editable on your end? It's not on my end. Why is it, this has never happened to me. This is really weird. Specify for market. Well, I'm gonna specify the counts. Why is it saying like specify for more count? It's gonna be there. Okay, let's try something else. Let's go single group. I'm ready. No, we're doing it from the summary. That's why, like, click on. So that the table should be empty. There's no data here. Analyses, ESCI, 2 groups. Okay. Oh, all right. I'm able to edit now. You solved it. Okay, so phase. The first one is going to be Bronze Age. Second one is going to be Iron Age. My outcome variable is the organic residue, presence or absence, or let's say milk residue. The first one is presence, absence. All right, so Bronze Age, I had 100 sherds with residue and 400 without. In the second one, I had 130 with, and is it 370? Am I doing the math wrong, or am I under the, yeah, 370. Great. So this is what we're plugging in. Notice we're not plugging in the actual total because the total adds up, right? We've got 100 with the present and 100 with absent, so the total is 500. We don't need to tell jamovi what the total is. It needs to know the total, but it can do the math. So once you do once you plug in all these numbers, the outcome tells you all the proportions. So it tells you that the proportion of your ceramic sherds with organic residue is 0.3. Okay, 0.33. But the confidence interval around this proportion is somewhere between 0.28 and 0.37. So when it goes to interpreting what is how many pots from the Bronze Age that we analyze, how many of them had organic residue, we have to talk about the lower limit and the upper limit of this interval. So most likely somewhere between like 28 and 37%. Or if you're talking in terms of proportions, 0.28 and 0.37. Had that presence. In the Bronze Age, we're talking about an interval from like 0.17 to 0.24. And the thing that we really want to pay attention to is the difference on the proportion. So we're actually getting an estimate of how much do the two proportions differ. And here, jamovi is telling us that the proportions differ by 0.13, but the confidence interval on it is between 0.07 and 0.18. So the true difference could be somewhere between 7% and 18%. And that's not very big, but maybe we're not expecting the milk residue to like differ by really big amounts. So if you scroll down, again, you can see a difference. The y-axis goes all the way to 1 because that's 100%. If you're not seeing, if this gets too squished, it's possible to reduce the maximum value on your y-axis. So you can kind of stretch it a little bit. But I'd like to have the y-axis go all the way to 1 because it's nice to see where 100% is, right? Like if you have a small proportion, it's nice to see how small it is with regards to what's the total possible. But if things start to get too squished, it's possible to reduce it. But here it is. It's giving us what our proportion is for the Bronze Age, for the Iron Age, confidence intervals on them, and that's the difference. And now we can ballpark what the lower and the upper limits are just by looking at the figure, or we can read it from the table. Now, fun thing with proportions is that as I said, we don't need the standard deviation. All we need is the presence and absence, and we can actually play with what the confidence intervals look like if the numbers go up or down. So I'm gonna choose smaller numbers. I'm going to say in the Bronze Age, we had 10 and 40. In the Iron Age, we had 13 and 27. There you go. Notice how they're much bigger. So if you have smaller sample sizes, the actual imprecision around your estimate is much wider. The error bars are much larger. So if you go to your table to look at what the difference is spelled out as, it says, given the sample sizes we have now, which is 50 for each group, the true difference in the proportions could be anywhere from negative 0.06. So it could be that Bronze Age had more lipid residue, or 0.3. So Iron Age had more lipid residue. Now, if you're thinking in terms of statistical significance, when you have an interval that includes 0, we don't have statistical significance. But it's more important to pay attention to where is the lower and the upper limit. The answer we're getting here is that most likely the true difference is probably minimal, like not very much at all, to like 30%. That could be pretty high. So it's much more important to look at kind of the what's the interval of where the true values are most likely to lie. Does that make sense? Are you happy with proportion? Proportions are really useful. Okay. Lastly, let's look at, do I want to do this? Yeah, okay. So I've said that there's p-values are going to continue being in the literature. A lot of people are really attached to them. So there's never going to be a world where we have complete kind of absence of p-values. So it's important to know how to interpret them. And something that the authors of the book do is they have a way of kind of using that dichotomous approach for doing significance testing, but they kind of put in language that make sure that we don't fall victim into the 5 red flags. So what they actually call it, instead of significance testing, they call it hypothesis evaluation. So let's do a hypothesis evaluation on, again, the Kufawana data set. And now we can test, if you remember that simulation that I ran on the middle and the late Neolithic goats, I had one simulation that gave me a significant outcome, one simulation that gave me a non-significant outcome. I want to see what it looks like in Jamovi if we kind of ask it to report significance to us. So I'm going to open a new file, Jamovi new. And this time I'm going to go, so ESCI, and we're going to go to 2 groups. And again, analyze summary data. And I'm going to plug in the results of my first simulation, okay? I'm going to say simulation 1. Oh, sorry, no. Both are simulation 1. One is going to be in middle Neolithic, one is late Neolithic. So MN goat and LN goat. So in the first one, MN goat was 5.0 plus or minus 1.1, and the N was 20. And the LN goat was 4.2 plus or minus 0.8. 0.8 and 20 again. My outcome variable was delta 15n. So here is something we should be very familiar with now. It's showing us the difference between the 2 means. There's that difference. Now, if you want to go down the road of doing null hypothesis significance testing, you can scroll all the way down. This is still the user interface. Everything that's on the left-hand side is called the user interface. This is the output, okay? Scroll all the way down to the user interface, and there's a section called hypothesis evaluation, and you can open it up, and you can then click it, and you can say what it's basically going to kind of put that significance threshold there. So we're using alpha 0.05. You can't change this because you've got a 95% confidence interval. If you want to go to alpha 0.01, you have to change your CI up there. So if you change it from 95 to 99, now your alpha changes to 0.01. So you can decide where your threshold is. It's best to do this ahead of time before collecting your data. But now I'm going to go back to my 95. What Jamovi gives you is a red line for where that null hypothesis is. So null is at 0. And you can see that the difference, the calculated difference between my 2 groups doesn't include 0. And that's why it's statistically significant. And the way that the authors talk about reporting this value is they say you can reject the null. You can't accept it. You can either reject or not reject it. And they would say that the conclusion should be at alpha is 0.05. 0, the null, is not a plausible value, okay, for our difference. If we go to 99% confidence, now our null is included, just barely clipped. It's in the confidence interval. So now we fail to reject. So it's saying your decision is fail to reject, don't accept. And you can conclude that at alpha equals 0.01, 0, the null remains a plausible value. So all that we're doing is we're looking at how plausible it is that our null is actually included in where the true values are most likely to lie. So that was the first simulation. And we've looked at both a version where the null is rejected and one where it's not rejected. If we go to the second simulation, those values are 4.8 plus or minus 1.0, and our n is 20 again, and then ln is 4.2 plus or minus 1.2, and n is 20. So there we are, 95. And here with 95, it does not contain, did I miss this one? No, it is correct. Sorry, I got my simulations confused. But in this one, our null it's closer to the upper limit, but it's almost touching, but not quite. So the outcome here is to, again, reject the null at alpha equals 0.05. 0 is not a plausible value for the true difference. So it's possible, if you really want to go down the road of testing null hypotheses, you can do it as long as you don't accept the null, as long as you say what your threshold that you've chosen is, as long as you still report what the actual difference is and putting confidence intervals on that difference, people who are going to be reading your papers who are not interested in p-values, they're going to see what the difference is. They're going to see what the outcome is by eyeballing the confidence intervals that you provide. So you can choose to include it or not. I haven't really seen, apart from archaeological papers that need like really complex models, and there is a space for really complex models that we need to work with statisticians on. I haven't seen applications where significance testing really added anything, because it always came, when I was reading the papers, it always came to kind of being convinced whether I think the difference is meaningful. If the authors present that the difference is 2, whatever units, and they make a case for 2 is really big or 2 is really small, that's what makes the difference. That's what the argument should be about. But I haven't seen an application where the kind of the rejecting or not rejecting of the null hypothesis really added anything to that conversation. It always came to interpreting the effect sizes. Okay, so those were the examples of looking at summary data. Let's look now at an example of using the actual data, like if you have it or if you've downloaded it from a repository. So if you go back to my my OSS folder, files. So we're in the folder confidence intervals. If you scroll down, it says figure 1 data. So it's called figure 1 because that's the figure I used in the paper I wrote on statistical training. So we're just going to recreate that figure. And so you can download the data. It's already in .omv. That's the file name. That's the format that Jamovi uses. And the walkthrough for that is the figure 1 walkthrough. So if you download the data, it should be pretty fast. Then you can open it from within Jamovi. Yeah, the one annoying thing about Jamovi is if you have something saved in like a folder, you can't just double click on it. You have to open it from within Jamovi. So you can click on your kebab and open, and then go down to, I have to navigate to that folder. OneDrive, work. Okay, confidence intervals. I've got figure 1 data, so open. So now the data set is in there. We can click on the tab called data up at the top. And if you're like, you can build your spreadsheet from scratch. The one thing about using Jamovi though, is if you're gonna make a comparison between like 2 groups, like middle Neolithic and late Neolithic, the data set, what you're seeing here, only has to include those 2 groups. Like if you have other species that you're not interested in comparing, you have to put them somewhere else. So that's the way it differs from Excel. In Excel, you can have like different sheets open, you can have like the whole data set, and then you can filter for things. Jamovi doesn't really filter easily. There is some functionality to that, but what I find most useful is to do your filtering or your subsetting somewhere else and then import into Jamovi that data set on which you want to calculate the difference. So there might be a little bit of subsetting involved. In this case, I took all the free threshing wheat and all the hull barley data, and that's what we're seeing here. So we can calculate our confidence interval now using this whole data set. So we're going to go to analyses. Right now we were on the data tab. We're going to go to analyses tab. That's where our ESCI button lives. So ESCI, 2 groups. And now we have to tell Jamovi what our outcome variable is. Here our outcome variable is delta 15n. So delta 15n, and you can either drag it over to this box or just click on that arrow. So now our delta 15n is in the outcome, and our grouping variable is a species. Okay, I want 2 groups for our comparison between the free threshing wheat and the hulled barley. And what we're looking at is the delta 15n. So we're seeing what we saw, well, earlier we looked at the big delta 13C values of these 2 crops. Now we're looking at their delta 15n, but notice we can see the individual data points. So now we can see the spread of data points, how they relate to the mean, to the confidence interval on the mean. And it still does the calculation of the difference between those 2 means. You still have that floating axis on the side, so you can ballpark where the lower and the upper limits of the confidence intervals are. But this is really useful I think it's really useful to visualize. Like I find this more informative than if someone just announced there's a difference between hulled barley and wheat. Wheat has higher delta 15n values. Well, if you actually show them what is that difference and what's the precision on that difference, it's easy to convince them, and it's easier for them to also make up their mind as to whether they like believe that the difference is meaningful or not, and how precise the difference is. Okay, last thing I wanted to show is how all of this can be done in R. Now, I don't have time to like go into how R works. So is there anyone who is familiar with R a little bit? There might be some online a little bit. Okay. Yeah, we don't have time to kind of go through R from scratch. But if you open up one of the things I shared on the OSF folder, here is called examples 1 through 6. So that's all we've done already in jamovi.r. That's the R script where you can do everything we just did in Jamovi and calculate the confidence intervals just using kind of the basics without using the SKI package. So this is what it looks like if you download it. The one package you'll need, here you go. The one package you'll need is a package called stat-psych. So you have to download that one. But once you have it, it's really easy to calculate confidence intervals. Like the functions that you need are called CI mean 1. So that's a confidence interval on a single mean. Another function is called CI mean 2. That's the confidence interval on a difference between two means. And then you just plug in what it needs. So for calculating difference on calculating confidence interval on one mean, you need to give it what the mean is. So our first example was mean 7 plus or minus 1. That's a standard deviation. Our n was 10, and we set our alpha to be 0.05. So if we open this package, we run it, there we are. There's our difference. I just ran one function. It says 7, the standard error, that's here. The lower limit of the confidence interval is 6.3. Upper limit of the confidence interval is 7.7. So that's a really easy way. Base R doesn't have functions on confidence intervals, annoyingly. I wish it did. Maybe one day it will. But at the moment, we need other packages to work with it. An example to calculate the difference between two means. Here's the one that we looked at with wheat and barley. So our first mean was 16.5 plus or minus 0.5. Second one was 18.4 minus 0.4. And very similarly, we just plug it in. We say, use the function CI mean 2. We say that the first mean, that's what it is. That's what the standard deviation is. Second mean, that's what it is. But that's what the standard deviation is. So then when we run it, it gives us two different outcomes. One when we assume variances are equal, one we assume they're not equal. But again, we've got the estimate, we've got the standard error. It gives us the t-statistics if we're interested in it. And here's the lower and the upper limit of our confidence interval. So it's quite straightforward. And if you are plotting, if you're like making plots in R, you can use this output and actually put error bars on whatever you want to show to kind of visualize confidence intervals. So what I would be doing if I was redoing the Kufowana study is I would show the mean of my free threshing wheat. I would put a confidence interval on it. I'd put a mean of my halt barley, put a confidence interval on it, instead of using standard deviation, because standard deviation shows us the distribution of our data. It doesn't show us where the true mean is most likely to lie. So it's very easy to adapt it. But if you're interested in looking through the code, it's there, it's available. And if you have any questions, let me know. I'm also available over email if anything comes up. So I should probably leave it at that. Is it time for lunch?
No.
It's not. Oh, okay. I thought it was at 12. Yeah. Oh, okay. Cool. Sorry. I thought it was at 12. Yeah. Oh, yeah. Are there? Yeah. What have I said too fast? Have I said anything too fast? Oh, there are some questions online. Okay. Me too. I've opened the dataset, but it only has one column saying things like alternate ID. Okay, something seems to be glitching. Let's...
It's a mistake. I think they click on the downloaded the JSON file. The data.
Oh, okay.
Instead of downloading the Excel file.
Okay, so okay, someone else made the same mistake. It sounds like you clicked on a JSON file. The metadata, not the OMV file. So make sure to download the OMV file and then open it from within Jamovi. And then it should be, it should be there. Is there a general explanation on how to use these functions in R and Jamovi in any of the publications you've mentioned or in the online SKI resource? Yes. Yeah, there's loads. So The package that I just showed from R with the functions on calculating confidence intervals, all the documentation on StatPsych, the package has everything you need to know about how to use those functions. Otherwise, the introduction to the new statistics, it has all the explanations on how to use jamovi. It walks through all the functions there, gives you examples. They also have like a massive folder with a lot of practice data sets that you can use to kind of try out all the different functions. I talk about it a little bit in my stats paper. Who else talks about it? Oh, and there is also documentation on the actual ESCI package, the R package written for ESCI. It came out a few months ago. It literally came out right after my stats paper was published. And I was like, oh, if I knew, I would have cited it. But the documentation on that specific package is also available where all the package and the documentation is. Yeah, I think those are the main ones. I'd go to the R kind of main files, descriptions, and the textbook has all the jamovi stuff explained. All right. Are there any other questions? Someone has a question about how do we tell if a difference is big or small? Is there a range? So the context, right, tells you if something is big or small. Whatever statistical model you're using, it doesn't have knowledge of the actual research context. If a difference is big or small, that comes down to the researcher and understanding of what we're looking at, right? So no test will tell you if something is large or small. That it comes down to kind of setting your thresholds. It's a good idea to do this ahead of time to say that, okay, if you have a difference in diets of like 2 per mil, that's interpretable. If the diet difference is like 0.2 per mil, that's almost nothing. Like I wouldn't actually interpret that. So that, yeah, it's all to do with the understanding of the context. Yes.
Size.
Okay.
Because is there any like sample size that's too small? When it is too small to use a statistical test, for example, because I'm using it in different, and especially depending on which area you're working with, like especially paleoanthropologists, for example, they work with very small sample sizes. Sometimes I wonder, like, what is even the point to compare 2 individuals with 3 individuals?
No, yeah. So that's a really hard question. The question was about sample sizes. Is there any kind of rule of thumb about how sample sizes should be? There really isn't a rule of thumb. It depends on like what data class you're working with, what type of variables you're measuring. The challenging thing for archaeologists, especially when we work with small sample sizes, is we don't actually know if the true population is normally distributed, right? If it is normally distributed, everything I talked about, how we calculate confidence intervals, that's straightforward, right? But if we're so small and we can't even really see what the distribution looks like, then we get into a territory of like, oh, should we be using parametric tests or whatever? It's really tricky. There's no right answer. The good thing about using confidence intervals is the sample size is incorporated into it, right? So if your sample size is so small that the error bars are massive, the error bars are massive. So you can only interpret what the error bars are telling you. But even if you get a small error bar, like a small confidence interval with a small sample size, then you can talk about the likelihood being quite high that like a difference is real or something like that. So with small sample sizes, it's particularly important to pay attention to where the limits of the confidence intervals are. If it looks like there isn't a difference, there's nothing you can do, right? If it looks like there's a difference there might be a suggestion, and that's what you talk about. But I wish there was a rule. Like a lot of people want to have one for like biological anthropology or isotopic studies. It's just there's no easy answer. No worries. Yeah. Do we always assume the underlying population? Oh, okay, I just talked about it. It is normal. We can't always assume it. With isotopic studies, it might be general, like it might be okay to assume it, but if you're really worried about it, you should tell the reader about it. Like if you have very small sample sizes and it looks like it's skewed or bimodal or something, then make sure to announce it to the readers because they need to know about that for sure. Okay, I think I've answered all the questions online. Are there any more questions? If not, let's jump into another activity. I want to talk about this. This will be a short one, so we can finish it up before lunch. Now, I'm going to close my R here, and I'm going to go back to my slides. And something I want to talk about now is tidy data. Okay, who has heard of the concept of tidy data? Has anyone? Okay, so tidy data might seem self-explanatory, but it's actually not. So it's a very specific definition, and it has to do with data being computer ready. So if we're thinking about programs like R or even Jamovi, which kind of has R running in the background, data sets have to be organized in a way that is called tidy. And there's a very specific definition that has to do with computer scientists. So if you read this paper, it's fascinating. It's called, what is it called? I think it's literally called Tidy Data, but Wickham 2014, Journal of Statistical Software. There's a lot to it, but it all comes down to the fact that when you organize your data set, in order for the computer to understand it, you need to organize every variable in a column, every observation in a row, and every value in a cell. And there's no other way of doing it. Now, this is not usually how tables appear in the literature, because the table might end up being like 10 pages when it could just be a short one, which is nicely organized. So there is a way to make tables like visually, like aesthetically pleasing and easy to read by eye, but then there's tidy, which means it's computer ready. Like R can just filter things, or R can find whatever species you're looking at. And it's really important to keep in mind that variables are always in columns, observations are in rows, because if they're not, then your functions in R won't work. So just to give you an example, these are two types of tables that you might find in the literature. There's a couple people, they underwent some treatments, treatment A, treatment B. There's some measurements on it. Here it is organized a little bit differently. Who thinks this is tidy? Is either one of them tidy? Do we have variables? No, I see shaking heads. That is correct, because we don't have a column per value and a row per observation. Notice how treatment, which is a value, it's spread over two different columns. And we've got people who should be a row, because an observation is a person should have its own row. They're now split over columns. So R can't handle that. This is not tidy. To turn it into something tidy, you would want to have one column with names, one column with the treatment. Now you know what treatment they are, and one column with the result. Okay, so when you reorganize it like that, it makes it easy to filter. It makes it easy to do calculations on them. Because if you've got like your treatment spread over two different columns, you've got treatment spread over two different columns, then you can't filter. And it seems very straightforward, but when you kind of start to look at tables which are not organized in a tidy fashion, you realize that there's a lot of different ways of presenting data, and sometimes it takes a bit of time to kind of get your own workflow for how to turn something that's not tidy into something tidy. So I wanted to look at two examples. This paper I've been talking about a lot today, so the Kufovano paper, this is table 1. And if you go to my Open Science folder again, this time, go into the folder called Tidy Data. So we're in OSF, Tidy Data, and you can download Vaiglova 2014 table 2. So that table looks like that. While it's downloading, I'm gonna open it separately here. Okay, there it is. So this is what I submitted to the journal when I was publishing it. Who thinks it's tidy? And if you don't, what could be changed? How can we make this tidy? I'm gonna make it bigger so we can see. So just to walk through it, I've got these are all faunal measurements. I've got the lab number for each sample. I've got the area or the context from which it came from. I've got the phase, middle Neolithic, late Neolithic, delta 13C, delta 15N, %C, %N, and CN values. I've got my cows. This is the sample size. And then I've got some summary statistics, my average, my standard deviation, then further the different phases. Then I've got my dogs. Then I've got my sheep and my goats. Is this tidy? No. Mm-hmm. Mm-hmm. Yeah, absolutely. So it's close to tidy, because most of the variables have their own column, but one variable, which is species, which is an important variable for this type of study, It doesn't have its own column. I've got something announcing that the next few rows are going to be about cattle. The next few rows are going to be about dogs, but that's not tidy. I need to have a column that announces what species it is. So to turn it into tidy, I'm going to save a copy just so I can write over it. So the first thing to do is just to get rid of everything that's not a measurement. So all my summary statistics, that R can do that. Like any kind of computer, it can do its own measurements, right? So that doesn't need to be in my main data set. So first get rid of all of the summary statistics. And we can keep going. And then you would need another row, another column, which is called species. And then we would say cattle. And then we would copy it. And then with the next one, we'd say dog, and then copy it. Okay, so that's how we would turn something that's not tidy into something that's tidy. And once we have the cattle specified, we can get rid of these two columns, these two rows. Oh, come on. And now it's in a version that R can work with. So oftentimes, if you're working with data sets that you've either just copied from someone's summary table in the literature, or you've downloaded a supplementary material, it's not always necessarily going to be in a tidy format. So you might have to do a little bit of rejigging to get it in the tidy format. Now, another example that's a little bit trickier that I want to look at is the other example in the same folder. So now if you go to, I'm hidden again. There you go. So that's the Schmidt table. So Schmidt 2003. Files. Tidy data. So now the first one, Schmidt 2003. So if you open that, you'll see this table, and it's from a paper that was actually on an experiment of monkeys in a lab. So monkeys of different species, we got the species listed there, they were asked to walk on poles, and what was recorded was how many steps they took on different poles. So one pole was 1.25 centimeters wide, one pole was 2.5 centimeters wide, 6.25 centimeters, 8.75 centimeters, 11.25 centimeters. So different widths of poles, and then they were asked to walk on the ground. So they walked in each of the pole, and the researchers recorded how many steps they took on each pole. And so that's what we have here. We've got one column with they're called subject. We've got the species, and also if they were male or female, and then substrate size is the width of the pole. Now, what can we do to make this tidy? How many variables are there? And how many columns should there be? What is it that the researchers were measuring? What do we know about each monkey? We know, how many steps it took. We know the species, right? We also know their sex, female, male. The row 5 and 6, FA and FB, were two different animals of the same species. So like female A, and that's what that means. So, and we know how many steps. And what's the other variable? The last variable. So the last variable is the tricky one. That's the one that's spread over all the columns. So that's the actual width of the pole, right? So in order to turn this into tidy data, we want to have each variable have its own column. We want a column for species, column for sex, column for the width of the pole, the substrate size, and a column for the number of steps. So to redo that, we could just add another column. We could put sex here. So now we've got a female, male, female, female, male, male, female, male. This one is indeterminate, or we don't know. The next column would be the pole size. Let's call it pole size. And then we would need to have another one with the steps. And then we would just have to keep going and plug the right information in the right place. So the first one for the poll that was 1.25, it didn't actually have any steps. Next one, so we'd have to copy all of that. For this one, the poll that was 2.5, it took 10 steps. Next one, for 6.25, it took 11 steps. So you can see how this is turning it into a very long table, right? Like each step measurement has to have its own row. So it's going to turn out very long. This is called going from like a wide format to a long format. And this is why the tidy format often doesn't occur in publications, because it can be really long. Like once we're done with all of this, we're going to have probably like, I don't know, 30 rows. So that takes up a lot of paper space in publications. And that's why it doesn't occur there. But if we want to kind of be tidy in the computer science sense, we need to translate it. R has very simple packages to translate from the long format to the wide format. If you're interested in kind of gaining a really good handle on the basics of R, how can we use R for data analysis? This book called R for Data Science is excellent. It's online, it's free, it's got lots of examples, it's got the code incorporated into it. I highly recommend. I think the second edition came out 2 years ago, and it has examples on how to go from the wide format to the long format, how to go the other way around. It has examples of how to produce some simple graphics, and then a companion book called ggplot for Elegant Graphics, I think. It has a lot more on like how to create really nice graphics. So for basics, I'd go for R for Data Science. All right, so we've talked about tidy data. Yep. Okay. Yeah, I think this is a good time. Yeah, because yeah. And okay. Uh-huh.
Version of the problems 1 to 6, there was a small error with the very first function. The C1 mean 1 function doesn't exist. It's only mean without the 1. So it's just
did you download this?
But it didn't work for me, so I had to.
And you downloaded this?
That could be, yeah. Yeah.
Are you sure? And you downloaded StatPsych?
Yeah.
Package.
It's just the C1 ci.mean 1 function doesn't exist in my version of StatPsych. It only C1.mean.
Interesting. Because when you go to the documentation on StatPsych, you get a list of the functions. And so this is the main, that's the documentation. And the list of the functions is here. And C1, CI, mean, where's my mean? Yeah, mean 1 and mean 2. I don't see an option that doesn't have one next to it, but if it's a macro. Okay. Oh, okay, so no number is the default. I see. Okay. Oh, thank you for letting me know. So if anyone is getting an error with within the StatPsych package, if you're looking for the function called CI mean 1, it doesn't exist. The default one for putting a confidence interval on one mean is just CI mean. But if it's for getting a difference between two means, it's CI mean 2. Thank you. That's really useful. All right, let's pause and we'll take it up after lunch.
Yes, we'll do that 1 hour. 1:30.
Yeah, 1:30 in 1 hour. See you all here. Bye. On now. If someone online can tell us if you can hear me or not. One, two, three. Is it working? Okay, wonderful. All right. Hold on, this is not sharing what it should be. Share. Oh. Okay. Yeah, but that's interesting. Okay, I might have to scroll through like all my slides until then. Let's just talk about everything super fast. All right, there we are. How is everyone doing? How was the lunch? Was good? Do you feel refreshed to do the second half? Awesome. All right. Well, maybe a good thing to do before we start the afternoon session is I'd like to get an idea of kind of where we're at. If you're comfortable sharing kind of whether there's anything you learned today that is shocking or that you find surprising or that you want to look more into, any questions you might have for me or any directions in research that you've decided you want to go down to. I'm just curious. I'm curious to know your thoughts. Are you more curious or shocked or neutral based on what we've done so far today? And anyone can jump in and online can jump in as well. Go for it. Thank you. Mm-hmm. Yeah. Mm-hmm. Mm-hmm. Absolutely. Yeah. Mm-hmm.
So I was ready to do this the statistics before it's made, and now and I want that different topic.
Wonderful.
So thank you very much. It was wonderful.
Oh, thank you. I'm really glad to hear that. That's really good to know. Thank you. Anyone else? Do you have any feedback? Any responses?
Feedback from candidates was severe feedback. There was severe feedback today.
Mm-hmm.
I have pending the whole
Okay.
morning.
Mm-hmm.
But I feel like it's a lot of information.
Mm-hmm.
And personally, I feel like today I'm just collecting data.
For sure.
In the future.
Absolutely. Yeah, no, absolutely. That's a good place to be at as well. I personally, so I mentioned I don't have a PhD in statistics. I wasn't taught this during my PhD. I just went down a rabbit hole years after I finished my PhD and I never left the rabbit hole. So that's where we are now. But it takes time. Like I understood a lot of the papers that I showed, like the ASA statement on p-values or mindless statistics, like I read it and I understood it, but to actually put it into practice and to kind of rephrase the way you use language to talk about your results, it takes a while. Like it really does. Like the first step that I went through was acknowledging that statistical significance is problematic, but I was still very dichotomous thinking, even though I try to not be. Like I acknowledge the challenges of NHST, but then when I was trying to do my analyses and even talking to statisticians, I still had the mindset of like, okay, but what finding is meaningful? I want something to tell me. I want there to be some kind of method where I know what is meaningful and what isn't. And that's not the way to go because that's dichotomous, right? It's if I'm looking for a yes or no answer, I'm not looking at how big are the changes, what are the effect sizes. So it was a two-step process for me, like understanding the challenges, but then I was still stuck in the mindset of, okay, but what's meaningful? And then I kind of let go of that. And now I'm like, okay, now I don't even need p-values. But I should also clarify that there is a space for them. And the space is in like proper statistical modeling, right? Like if you have really like complex multivariate models that you build with statisticians, they're going to probably have p-values. And as long as the model is written well, everything is accounted for. As long as you don't like cherry pick results, make a massive correlation matrix, and then only decide to talk about the comparisons that are flagging up as significant, like there's a space for models, but they have to be done well and in collaboration with professional statisticians. Anyone else? Is anyone? Yeah, go for it. Mm-hmm.
Maybe as they are coming in as first year, okay,
Mm-hmm.
it should be, gradually be introduced to statistics so that
Mm-hmm.
they will fully equipped by the time they are writing their thesis and all that.
Absolutely. No, thank you for saying that. It really, like, the sooner you start, the better. And the good thing is, it's not just about the models, right? Even making graphs and kind of visualizing how graphs are made, that's statistics too. Or talking about data classes or uncertainty, that's statistics too. So it's important to start talking about it as early as possible, but it's not all black boxes that are really hard to buy with. Does anyone find NHST like really unintuitive? No, I now find it really like, because it's all about these double negatives, right? Like you want to find an effect, but then in order to have this null hypothesis, you have to assume that there is no effect, even if you have no reason to believe in it. And then you like look for data to like reject that null effect. It's all just it's so, I find it really hard to like wrap my mind around it. So it kind of makes sense to me now that when I was in school, it didn't make too much sense. Like it wasn't as, I didn't vibe with it as much, and it's because it's not as user friendly, I guess. Anyone else? No. Oh, thank you. Awesome. All right. I'm definitely going to be more cautious about how we use p-values in the future. Yes, that's definitely a big aim that I was hoping for today. I'm going to rethink a lot how I'll teach next courses about stable isotopes and archaeology. Really glad to hear this workshop. Thank you for saying that. And absolutely, it changed. So I've been teaching for a couple of years now, and it really did change the way I teach as well. It's important to like start with like talking about the data, visualizing data, asking the right questions, rather than talking about questions and then saving the statistics to the end, because one, it might be too late, but also that's just not the right way to go about it. Actually, maybe something that I should really underline is, if you ever come up, or if you're ever in a situation where someone is saying like things that are opposite to what I've been saying. So for example, I met someone recently who already finished their PhD and is like just doing the corrections, minor corrections, but the reviewers or the examiners were like, just insert the stats. And so now they're panicking because they want to put in the p-values. They want to do something so that they can finish. They're so close to finishing. They just need the corrections to be done. And there I am saying like, no, this is all, you have to rethink your whole approach. They don't have much time to do the corrections. So now is not the time to rethink everything. If you ever come up against like examiners who are just really resistant to you talking about estimates rather than p-values, let me know. I can help. Like there's a lot of support. There's a lot of literature backing up what I've been saying about the fact that we need to rethink NHST. Like models are okay. NHST as a model, it's not a good model. It's a flawed like approach. So if you're finding resistance to that, let me know. I can support you, and I can give you some references that you can share with those people. Okay. Let's move to this. If there's nothing else, let's move to the second part of today. So what I wanted to do next is talk about meta-analyses. So I mentioned them earlier. Meta-analyses are really kind of the gold standard that we're trying to strive towards. Individual studies are really important. Individual case studies, experiments are really important. But where science really gets the biggest advances is putting data together. And this can be challenging to various degrees. Sometimes it's easy to synthesize data, and sometimes it's difficult. What I want to talk about today is a really like rather straightforward way of putting together effect sizes, whatever they are, whether they're means, whether they're correlation coefficients, whether they're proportions. There's a way to synthesize them and talk about the data as a whole. So you no longer have to say, couple people in the literature say this, couple people in the literature say that. Some people find significant results, some people don't. And like, how do we resolve this? We need a bigger sample size. That's a hard landscape to be in, because you can't really say much using kind of robust evidence. The way to really kind of synthesize the results is just to combine them and come up with an overall effect size with its own precision, which is usually going to be higher. It's going to be more precise. And there's ways to do this for all the types of effect sizes that I've mentioned today. So let's first talk about just meta-analyses, kind of from step one. There's a fantastic book that came out in the 90s. It's called How Science Takes Stock, The Story of Meta-Analysis. It's a really good read. I highly recommend it. In the first chapter, The author talks about how meta-analyses came about and just how, both philosophically and how it actually happened. So this is the first paragraph. It says, I've seen further, if I have seen further, it's by standing on the shoulders of giants. And that's what Isaac Newton wrote to someone in the 1600s. And assuming this, modest pose, he alluded to the fundamental assumption that our culture makes about science, namely that it is progressive and cumulative, a corollary of which is that forays into the unknown by researcher, however brilliant, are merely extensions of the knowledge amassed up to that time. So no matter how good a study is, a new experiment, a new study, you always have to stand on the shoulders of giants, right? Like you always have to refer back to what the previous literature says, what the previous body of knowledge says. And there's way to do it in kind of an arm wavy way, but there's way to do it in a very kind of robust way. So this is an example, again, no citation because I don't want to put anyone on the spot. And it's an example actually from biological anthropology. This is a paper I was reading recently about monkeys and how there were some observations done on monkey mothers and how their glucocortisol levels changed depending on what their kids were doing. So some monkey mothers had offspring that had disabilities. And it turns out that those mothers had higher stress levels because they were now caring for infants with disabilities. So they had to kind of fill in for more tasks and they had higher stress levels. So this paper was all about the stress levels and all the different factors that were influencing those stress levels. And this is a very common way to present what previous literature shows. So I've kind of highlighted some of the sentences that kind of really stood out in terms of saying what previous research showed. So the author summarized it as indicators of fitness have been highly inconsistent. In a detailed review, they concluded that a consistent, predictable endocrine response to chronic stress does not exist. Later, someone predicts that moderate levels of cortisol may be advantageous and correlate positively with fitness-related variables in some circumstances. So they're talking about moderate levels of stress. I want to know what moderate means. You can spell it out, right? Like, what is a moderate level of stress? What is low, what is high? This is something that's really useful, I think, to say early in a paper rather than later, because you want to kind of signal to the author where their ballparks should be. Another sentence, now challenges associated with long-term physical impairment and disability may influence stress. It was talking specifically about fecal glucocortisol levels. And they had different comparisons with different species. So very common. I've seen lots of papers like this that flag up. Someone found a correlation, someone didn't. Some showed this, some showed that. Well, there's a systematic way that we can actually go into each of these studies. We can get the actual numbers, like what were the stress levels, how much, what was the number, and then put it all together and then see overall, are the levels higher or are they lower, and what's the uncertainty on them? So that's what meta-analyses can do for us. It can find an overall effect size and allow us to kind of draw on previous literature without having to spell out individual studies, which might actually be conflicting. So if you remember this example that we looked at earlier, the lucky no luck, we had two different studies. One found a statistically significant impact of malnutrition on delta 15N and one didn't. And those were the point estimates that we looked at. The second one failed to pass a significance threshold because 0 was included in the confidence interval. Now, if we took it a step further to go beyond estimation thinking into meta-analytical thinking, what we're interested in is to bring those results together and talk about an overall effect size. And this is what it is. This is a meta-analysis. It's very simple. It could be as simple as putting two means together, right? So here, this is the result for combining the lucky point estimate and the no luck point estimate. And now the confidence interval is a little bit narrower, even just with two studies. And that's the real big benefit of meta-analyses. You don't have to be combining 500 studies. Even when you have two, the precision already increases, the confidence interval goes down. And it's usually higher. There's some caveats, but usually it's higher. So that's what we're aiming for, to have something that we can build on. So what are the main advantages? One of the main advantages is that they can produce strong evidence when at first sight the evidence may seem weak, right? It may seem contradictory, maybe it's equivocal, kind of heading in the same direction, but some might be more precise than others. Maybe some sample sizes are really small. When you put it all together, those sample sizes, they're taken care of. Like now you have a larger sample size, and we'll talk about different types of models that you can use that allow you to kind of put different amount of weighting on different results based on how precise they are. They can settle heated controversies, and they have. I think one of the first, I don't know if this was like the first meta-analysis study, but there's a syndrome that I'm blanking on the name of, but the infant death syndrome, like when kids lie on their bellies, the infant death syndrome, that debate was settled by a meta-analysis, right? There's a lot of studies that indicated that if babies are sleep on their front, some of them die during their sleep, and some of them don't. So there's been conflicting, back in the 90s, conflicting parenting advice as to how to put babies to sleep. And the studies were not all showing the same thing. So in the end, someone did a meta-analysis. They put all of the results together, and they found out that it's very, very much likely that your child will not die during sleep if it's lying on its back. So now the advice is to put the baby on its back. But that debate was settled by a meta-analysis. And there's been lots of other ones about like learning disabilities. Every time like governments try to come up with policies, they want to bring together studies, right? They don't want you to just like rely on one study that has the biggest sample size. They want studies to be put together in a way that allows us to kind of draw on the data overall. So it can be extremely powerful for making evidence-based policymaking. Improved precision is a really big benefit. It can turn long confidence intervals into short ones. And forest plots. So today we'll look at forest plots and how useful they can be, how to read them, and we'll make some examples of our own. This is a cartoon from the textbook that I mentioned, Introduction to Pseudo Statistics. And it's a beautiful cartoon because you've got confidence intervals walking towards the meta-analytical effect size. So each of these is a point estimate with a confidence interval over it. And you'll see when we start looking at forest plots, the overall estimate is going to be shown with a diamond, right? So the diamond is the overall effect size. And now here we've got the individual confidence intervals with a diamond at the end. So that's really what we're striving to do. So this is what a forest plot looks like. It can be as simple as putting 3 studies together. That's an example where someone was looking at how people were going to vote. So there's 3 different polls, and the meta-analytical diamond is on the bottom. The way to read it is the middle part of the diamond, where its fat is, that's kind of where the point estimate is, and the end parts are the limits of the confidence interval, right? So here we've got the confidence interval running from the lower limit to the upper limit. And when we interpret the overall meta-analytical effect size, that's what we're focusing on. But it's also useful to pay attention to what the individual studies are doing. And there's a very nice way of highlighting the ones that are more precise versus the ones that are less precise. So what does it show? We've got a diamond. It's the weighted average of the individual data estimates. And the weighting is determined by the precision. And the diamond indicates the precision around the combined estimate. It's usually narrower. What do we need to make a forest plot? We need 2 things. We need the actual effect size, and we need the precision. So if we're combining means, we need the actual means of the studies and the standard deviations of the studies. And jamovi or whatever you're using to do your forest plots, your meta-analyses, it's going to take care of the rest. As long as you have the descriptive statistics, it will calculate everything else you need to make your forest plots. So we need the effect size, the actual mean, the actual standard deviation, or if you have the confidence interval, that can work with that too. But we don't necessarily need the p-value. There have been papers written on how to combine p-values. It's a territory that's not easy because some people don't report the real ones. Some people just say it was less than 0.05. That's not specific enough. Like if you have a declaration that it's less than 0.01, less than 0.05, you can actually put that together. But actual p-values, they can be put together, but not to produce the forest plots that we'll be talking about today. So today we're just focused on how do we combine effect sizes which have their own precision. This is a really great quote by the pioneer. So the person who actually started meta-analyses, and he was trying to show the effectiveness of psychoanalytical techniques in psychology. So there's this heated debate about whether they work, whether they don't work, and at like a massive conference of all psychologists, he presented this and faced some backlash, but then showed that it's actually very effective. And this quote is really, really useful, and it kind of resonates with a lot of what I've been saying today. It says, statistical significance is the least interesting thing about the results. You should describe the results in terms of measures of magnitude, not just does a measurement affect people, but how does it affect them? That's what we need to know. So this is literally the inventor of meta-analyses, and he's saying significance is not how we're going to synthesize results overall. Okay. Now, there are probably the hardest part of doing meta-analyses is the early part. So deciding what studies should be included. This can be challenging. This is probably the most challenging part. I can't go into it because different fields, different topics will have different kind of guidelines about how to put studies together, like what's a good study, what's not. But generally, to combine studies and make a forest plot, we need the studies to be sufficiently similar. Okay, sufficiently could be as similar as just asking the same question. They don't need to be identical, but if they ask the same question, if they measure the same variables, if the procedures were reasonably similar, it should be possible to combine them. If there were very specific ways in which the procedures differed, there's actually ways to do this, what's called a moderator analysis. So if you have a reason to think that maybe a study that was conducted in Cyprus came out differently because of cultural differences to a study that was ran in Germany, you can do a moderator analysis to see whether the location where the study was carried out, whether that has an impact on the results. It can't determine causality. You can't, that's not something it does, but it's a way to see if some of the variability in the results can be explained by this moderator, which in this case is location of where the study was carried out. So studies, they don't need to be identical. If there's some ways that the procedures differed, we can do this moderator analysis. But as long as the question is the same, we have the same effect size, it's possible to put them together. All right. So there's two types of models that we can use. Annoyingly, we have to pay attention to the plural versus singular version. But there's the fixed effect, so this is singular, fixed effect model, and the random effect plural model. Okay, so fixed effect, random effects. Now, what are the differences? Fixed effect model is the simplest. This one assumes that all of the studies come from the same population, everything is homogeneous, and everything can be combined together. It's basically the same as if you took a bunch of studies and created one massive study out of them, right? Like if you put 10 different studies and created one spreadsheet, it almost looks like now you have one study. That's the same thing as doing a fixed effect model. You just assume everything comes from the same underlying population, combine it together, and then do your forest plot based on that. Now, the challenge is that we usually cannot assume that the studies came from the same populations. There's too much variability. Archaeological populations might have their own reasons why they differed. Experiments might have had the reasons why they're set up a little bit differently. So because this assumption is usually not realistic, and it's not realistic because studies differ because of instruments, researchers, the timing, maybe the season at which something is taking place, the year, time of day, country, the underlying populations in like modern experiments that you might do. Because all of these differ, we cannot make those assumptions. So the better option is to use what's called a random effect model. This is where we can make the assumption that studies come from different underlying populations. And this is important because it gives different weighting to each study. And the weighting is determined by how precise the studies are. So always choose the random effects model, because even if the results come from the same underlying populations, even if in reality, all the data is homogeneous, if that's the case, the results would be the same for the fixed effect and random effect. So if everything comes from the same population, the results of the two will be the same. If they don't come from the same population, random effects will give you better results. So it's best to always choose random effects. And when we look at how to do this in Jamovi, there's a really easy way to just, there's like a drop-down menu, you select random effects. So random effects can handle heterogeneity, and if the results are homogeneous, the results of the model will be the same. So there's nothing to lose with choosing random effects. Okay. Here's an example. It's not an archaeological example. There's not too many studies that have used forest plots yet in archaeology. I'm trying to change that. But I wanted to use an example that kind of steps away from what we know about archaeology and just focus on how do we put results together. So this is an example of looking at brain images, so MRIs of the brain. And the research question that these researchers posed was, does adding a brain image to a publication make it seem more credible? Okay, so it was an independent group design. They had a group that looked at some articles that were written by the researchers, and the articles had an image of a brain in them. Now, the important thing is that the image was irrelevant to the article. It had nothing to do with what was being said in the article, but because there was an image in it, now they were in a different group. The second group also read an article, but didn't include the brain image. And what the researchers wanted to know is how credible were the results? The people who were reading the studies, how much did they trust the results from a group, from articles that had the image of the brain and articles that didn't have an image of the brain, okay? And they were measuring credibility on a 4-point scale. So more credible, higher number, less credible, lower number. Well, it turned out that people judged both the title of the study and the conclusions of the study higher when they had the brain images in the article. So they were paying more attention to the fact that it feels more scientific. It looks like it's more science. They might not have been paying as much attention to the actual context or the content of the article, but there was an indication that having the brain image makes the results more credible. Those were the original findings. Now, other people came around and they were like, well, can we replicate the results? Let's see if we rerun this a couple times, maybe in different countries, if we get the same results. So they ran a series of replication studies, and the studies were designed to be sufficiently similar. So the procedures were very similar questions. It was possible to put them together in a meta-analysis. And what they did is then they created a forest plot of the results. So this is what the forest plot looks like. Here listed along the y-axis are the names of the different studies. So the McCabe 1 and 2 were the original studies, and then Michael 1 through 8 were all the replicate studies. Now, what we're seeing inside the forest plot is the individual, the scores from each study that the people, or the difference in the scores between the brain group and the non-brain group. That's why it says brain minus no brain. So the MDiff, that's the difference in the mean scores of the credibility rating scale. So in the first study, the difference in the scores was 0.2 with a massive error bar on it from like almost negative 0.2 to 0.6. That's again difference in the credibility score that people gave it. And then when the studies were replicated, the actual outcomes, the mean differences, some of them were negative, some of them were positive. They had variable amounts of precision on them. So you notice that these two studies were really precise. Those error bars are really, really narrow. And that's why those squares are really big. The challenge with seeing error bars is the longer the error bar is, the more your eye is drawn to them. But we don't want to be drawn to those results with big error bars. We want to be drawn to the results with the small error bars because they're more precise. So that's why this program, it makes the squares, the outcome, bigger, just so you notice them better. So these are more precise. And overall, when we look at all of the studies together, here's our diamond. It is for a fixed effect. We're going to look in a moment about how it differs from the random effect model. But overall, our diamond is saying that the difference in the scores, it was very low. It was, we can see it spelled out here, 0.68 with a 95% confidence interval from almost 0 to 1.25. So very, very small difference in the credibility rating score. That's the fixed effect model. Now, the random effect model, little bit higher and also a little bit wider. And when we look into Jamovi, it's going to give us those outputs. So we're going to just in the same way of what we did earlier, we're going to get a table where the confidence interval is going to be spelled out. Here, we're going to get a table with the meta-analytical effect and the confidence interval around it. So this is how the outputs of the fixed effect and the random effects model differ. Very, very small. But people were still quite excited about it because they were like, oh, we can talk about how the credibility of papers is much improved by having really fancy looking images in them. Then came along, oh, and notice how the size of the square is to indicate the weighting. The bigger the square, the more precise the study, so the more impact it is going to have on the random effect diamond overall. One of the things I mentioned that the people who try to do more replicates, one of the things they try to do is looking at moderators to see if there's something that can explain some of the variability in what we see. Now, what I haven't told you so far about the study is that there were two different setups, which were the presence or absence of a critique in that article, okay? And in this example, or in this instance of using the moderator, what was done is the authors looked at, does the presence or absence of a critique help explain some of that variability? So here are the simple, which didn't include a critique, and critique versions of the study. And these were the replicate studies. So the first original ones, they're listed here. So McCabe 1 used selected science articles. McCabe 2 used the same articles, but included a critique at the end. Michael studies 1 through 5, no critique. Michael studies 6 to 8, critique. So now we can do a moderator analysis to see, does the presence of a critique also influence some of the scoring in the credibility? So here the prediction was that it will cause variation in the study effect sizes. So when we put in this moderated analysis, this is what comes out. So now we have more than one diamond. We have the random effects overall diamond. And now we have an estimate for studies that included a critique and for studies that didn't include a critique. Okay, so simple are blue, and the ones that have a critique are green. Notice how really widely distributed this is. So the imprecision on the overall effect for the studies that had a critique was really, really wide. There's some overlap, not too much, but this is too wide to really make some people comfortable. So Michael then went in and he was like, okay, I need to get better estimates for the studies that did have a critique because these error bars are so big that we just can't do much with. So designed some more experiments which had more critiques built into them. And so that's 9 and 10, 2, oh yeah, 9 and 10. So now we have two more studies. Notice the really big squares, more precise, narrower confidence intervals. And now there's much more overlap between the outcome of the simple studies and the outcome of the critique studies. So it doesn't look like that critique is actually making much of a difference. There's a massive overlap, and the actual differences is very, very small. So overall, after running this meta-analysis, considering the original studies, the replicate studies, the extra studies that try to get better estimates on the critique version of the experiment, overall they concluded compelling evidence that when it comes to brains, the amazingly persistent meme of the overly influential image has been wildly overstated. So the media really picked up on some of the original studies because they were like, well, people are going to want to read about this. But through replication, it turned out that there wasn't too much there. And this is really the only way to put such large amount of data together, right? Like it's possible to summarize all of these individually in your maybe in the first chapter of a thesis or in the introduction section of a paper, you could say that Michael 1 and 2 found really big differences, but they weren't very precise. And then Michael 3 found a smaller difference, but it was less precise. You can summarize all of them individually, but if you put them all together and say, overall, what are they showing? And actually put a number on it, it's really, really powerful. And we need to do this more and more in archaeology. I'll show you an example of what some of my students did in class, and they're really, really great examples. Okay. I'm going to try to take more sips of water just so I slow down more. So this might be a good opportunity to also ask questions if they've come up. So a couple more words on using moderator analysis. So important is to remember that we have to make a distinction between planned and exploratory analysis, okay? If you're ever trying to design an experiment or determine causality, the only way to determine causality is with an experiment where everything is kept controlled except for one variable that differs. That's the only way to infer causality. If you can't design an experiment, you can say maybe there's a suggestion that something influences something else, but you don't have causality. So for causality to be convincing, we need to have planned analyses, and exploratory analyses might give us indication that something is there, and then we can design more studies around it to actually further probe that. But there's a distinction between what is planned and what's exploratory. Moderators don't need to be dichotomous. You don't just need two groups. You can have as many, like you can have a categorical variable that has many groups in it. Remember the consideration of how similar the studies were. So really important with running moderator analyses is to remember why you're doing them. You're not doing them because you don't like the data. You're doing them because there might be genuine differences in how the studies were set up. So if there's cultural differences or if there's differences in the underlying populations, that's a reason to do a moderator analysis to see if it might explain some of that variability, but not if you're not seeing an effect that you were expecting. Okay, so focus on differences in the studies themselves, not the actual data. And beware of implying causation. So now one really, really big challenge to doing meta-analyses is the file drawer effect. So the file drawer effect is what has happened over decades and decades and decades of researchers not publishing results that are not statistically significant. So all of these p-values that don't cross our 0.05 or 0.01 thresholds are in the file drawer because they've not been published. So because a lot of studies haven't been published, if we now run meta-analyses on what has been published, the data might be a little bit skewed. It's probably the case that they are a little bit higher because things that don't reach statistical significance, the effect sizes are most likely smaller. It's harder to find differences if the differences are bigger. So if differences truly are smaller, it's harder to find them, and it's more likely that you're actually not catching them with significance tests. So publication bias has really made it difficult to run meta-analyses. Different fields, especially ones that have been doing meta-analyses for a while, like medicine and psychology, they have ways of trying to get around it. They try to source materials that might have been kind of hidden. Maybe you go to look at conference proceedings or conference presentations that never actually ended up being published. But it's a lot of work to try to locate everything that was ever done on an experiment or a study that was very similar. But in the end, it's persistence. And also, the real way to really solve this is open science, right? If we're very open about all the data that we've collected, make the results available, put it in repositories so that other people can include it in future meta-analyses, that's the way to reduce publication bias and make it so that meta-analyses can be done in ways that are robust. All right. So just as an example, if we look at the results of the study, we still got our McCabe and Michael. Let's look at the studies that are that cross 0 are not statistically significant, and the results that don't include 0. So this one is statistically significant because 0 is not included in the confidence interval, right? So that one's statistically significant. The second one is as well, but the rest ones are not. Now, this also comes from the textbook that I've been mentioning, which I can give you more information about later. If we only include studies where the p of less than 0.05 had been published, we would only be including McCabe 2 and Michael 7. Okay, McCabe 2 and Michael 7. Those are the only ones that are statistically significant. So if they're the only ones that were published, if now we want to run a meta-analysis, our overall finding would be that the difference is 0.32. That's much larger than what we found looking at all the studies together, right? It indicates that the difference between the scoring, it was not massive. It's not like a whole point on the credibility scale, but much larger than what we had before. If only studies that found a positive effect, so some of them were positive, some of them were negative, if only studies that found a positive effect had been published, the meta-analysis would exclude 4 of the studies. So Michael 1, Michael 4 is negative, Michael 9 is negative, and 10. So if publication is only focusing on things that are positive, 4 of the studies would be missing, And now the result would be 0.12. So you can see how the result of the overall effect sizes, the combined effect sizes, they can really be different depending on what's included and what's excluded. So we need to be able to source as much data that is out there about our question of interest in order to avoid problems like this with publication bias. Okay. This is another great cartoon. It's the meta-analysis machine. So here are some researchers. They're chucking in their confidence intervals, and overall they've got their diamond effect size. So it's a way to really kind of make meta-analyses more commonly accepted. There's different ways that we could do meta-analyses. Today we're gonna use Jamovi. There's lots of different effect sizes that it can handle. We can look at means, we can look at differences between means, we can look at proportions, differences in proportions, correlation coefficients we can put together, which is really useful. So Jamovi, really useful. Meta-analyses.com has some useful references and packages. Something called RevMan from the big Cochrane collaboration. Cochrane collaboration might have been defunded recently, but I don't know. I think they're having problems with funding because America. I didn't say this. But anyway, so there's a lot of metaphor package and art. There's lots of ways to carry out meta-analyses. The main thing to do is to be kind of thoughtful at the initial stages. Include studies that pass a certain threshold of quality. If the results don't look like what you want them to look, that's not a reason to exclude them. And if something is not published, that's also not a reason to exclude them. It might still be good data. So look at the quality of how a study was carried out and then put them together. But today we'll look at a lot of examples in Jamovi. These are some examples that either me or my students have put together. So here is a compilation of stable carbon isotope values from China. It's a lot of studies, archaeological assemblages, where the question was there a difference in the delta 13C value between males and females, okay? So what's on the x-axis, it's the difference itself, right? So the mean of males subtracted from the mean of females. So 0 is over here. You've got the dotted line on 0. Every time it's on the positive, the females are higher. Every time it's on the negative, the males are higher, okay? And when we do this in Jamovi, you're going to get a table that looks like that, which is called the meta-analytic effect size. The overall mean will be spelled out with its confidence interval around it. And then you have some more other information to talk about. But now with an image like this, you can really start to go in and kind of scrutinize what the different studies are doing. How precise are they? Are they really fluctuating? Are they really all over the place? Are some do some have really striking differences on the positive side versus others that have differences on the negative side? Notice this one study, which is massive error bars. I think the sample size of that one was super, super tiny. But it's really useful to both see the overall effect size. So if we were just looking at all these archaeological sites interested in the difference between the delta 13C of men and women, this is what we would spell out, okay? It's a very small difference. It's like 0.32 per mil. That's not something really that could be interpreted too much, but it's not 0. And looking at the studies individually also gives you a good idea of how precise the results were. The bigger the square, the more precise the results. So that's delta 13C. These are the delta 15N values. A little bit more variable, also a little bit more fluctuating. But overall, the actual diamond is smaller. So now it's 0.2. And that's because we got some more on the high, more on the low end. So it's kind of balancing itself out on the end. And the difference between the random effect and fixed effect random effects is not too big. Sometimes it is, sometimes it isn't. The random effects is usually a little bit wider in terms of its precision. Something that you can also do with meta-analyses, which is really useful and easy to do in Jamovi, it's just another matter of selecting something from a Dropbox menu, is you can do standardized differences. Standardized differences are really useful because the underlying variabilities at each study might be different. Okay, so if you think about, think back to like the IQ study, right? Like IQ, the mean should be at 100, one standard deviation should be 10, right? So 68% of the population should be between 90 and 110. But if you then go in and take groups of people and test them for their IQ, the actual values and the variability in the values might depend on what school they are, what kind of training they had. Maybe some schools specialize in math, some schools specialize in something else. So the actual values, actual means, and how the means are, how the actual scores are distributed could vary. And that makes it hard to make comparisons, because if you're trying to put together things that have different variability, you're kind of comparing apples to oranges. So the way to deal with that is to standardize everything. And the way you standardize studies is to divide every point, every effect size by its standard deviation. So now you're effectively kind of turning everything into z-scores. So the mean is at 0. If a mean of the difference between men and women was at 1, then it's saying that the difference at each of the side was literally at 1 standard deviation for what's happening at the side. It doesn't matter what the standard deviation is at each side, but compared to what the variability is there, now we're looking at how far from the mean and how many standard deviations away they are.
Is for this example, the error bars are no longer referring to the confidence intervals, but to the z-score difference?
So there are still confidence intervals, but they are not in the original units. They are in standard deviation units.
Okay.
Yeah. No worries. Awesome. Yeah, so that's the same study that I showed you, the first one, the delta 13C. Now they're standardized, so we got 0. And it's showing something very similar. And the standardized equivalent is 0.3 per mil. And you would go around interpreting it very similarly, the lower limit and the upper limit, but now you're talking, the units are standard deviation units. This is what the delta 15N standardized looks like. There's that really big, very small size, massive error bars on it study. But the actual shape of what the studies are doing is very similar. This is a really interesting example that one of my students did. She was trying to get an idea of what the amplitudes look like. The amplitudes are the differences in the maximum and minimum oxygen isotope values in teeth. Okay, so this is what I do in my research. I studied tooth enamel, isotopic values. And this is a very common way of measuring them. We would go in, start at the chewing surface, work our way down to the root, and take a sample of the enamel at like 1 millimeter interval. Go in and as many samples that we can fit in at 1 millimeter intervals, that's what we measure. And the expected way that how this is going to turn out is that we're going to have really high delta 18O values in the summer, low delta 18O values in the winter. And so it's like a sinusoidal pattern. Now the amplitude, which it's actually the range, amplitude in the strictest sense of the word, is from like where the line is, the medium line. The amplitude is the difference between the line and the maximum, but we're looking at the difference between the maximum and minimum. So it's actually the range. The range of these sinusoidal patterns has been used to infer seasonality, and that's really important in like evolution studies, looking at how climate impacts people living in different parts of the world. But the more pronounced the differences between the summer and the winter, the higher the seasonality. So we know that. We've known that for a while. We've done it at lots of different studies. This type of sampling strategy has been used very consistently. But what we don't have is an actual estimate of what the amplitudes, the ranges, look like in different parts of the world. So we don't have an estimate of what an amplitude in these values should look like for a tropical climate and for a temperate climate at an altitude of like 2,000 meters above sea level, or even just a different continent. So my master's student, Joanna Evans, she decided to do her meta-analysis for my class on that. She collected lots of different studies that had this sinusoidal data. She combined it. On the x-axis, we have the mean oxygen isotope amplitudes. And so they're kind of the higher they are, the bigger the difference is. And then she did a moderator analysis on geographical region. Okay, so we've got a diamond for Asia, a diamond for Australia, diamond for North America. Now, you can see the diamonds are really, really wide, okay? There's not much you can say with diamonds that are so overlapping, but the actual approach is really useful because this was a small scale study. She's taking it now to a larger extent in her master's thesis. But an approach like this allows us to actually get an estimate. What should the amplitude look like for this region? What should it look like for that region? And then if we measure something that's really off of what we expect, then we can talk about maybe someone originating from a different place, or using these amplitudes as another kind of proxy for geographical origins or inferring climatic patterns. So this is, no one's done this, but the data is out there, right? It's just a matter of putting it together and getting our overall diamond. Here's another example. These are looking at proportions. So I've talked about proportions when we looked at organic residue. So we had like 100 sherds with milk residue out of 500 sherds in Bronze Age and 130 sherds out of 500 in the Iron Age, and looking at, does that increase in 30 sherds between the Bronze Age and the Iron Age, is it meaningful? Like, does it mean that milk consumption actually increased? Well, one way to look at this is to look at proportions, put confidence intervals on proportions, and then calculate the differences in proportions themselves. So this is another student she was looking at the proportion of non-local animals at different sites in China. So these are non-local pig, non-local cattle, and non-local sheep. Now, this was an assignment for a class, so it was quite small scale. That's why the diamonds are very, very wide. If she had more time, she would include lots more studies, everything that was published, but that was not the point of the assignment. The point was to learn the ropes, like how to actually carry this out. But you can see that the proportions were quite low. They're very, very small. The thing with proportions is that the confidence intervals, they are not symmetric, so they're squished. We'll talk about this a little bit later. They're squished because they have a maximum and a minimum, right? Like you can't go below 0 in terms of proportion. You can go below 0 if you're looking at differences in proportions, but one proportion not. And then you can't go above 1, which is 100%. So the confidence intervals they squish towards those ends. But overall, now we can talk about what is the proportion of non-local cattle at these sites. What is the proportion of non-local sheep? And are there any differences in the species? So we can see that with the sheep, there's a massive amount of variability. The diamond is really, really wide, versus for the pigs, it's much more narrow. So it looks like the proportions of pigs are more consistent between different sites that were studied. But with the sheep, the proportions are more variable, which might be real, or it might be the result of sampling bias or the actual studies that made it into this meta-analysis. Yes.
Really relevant for us, as we discussed earlier, not for isotopes, obviously, but for every other kind of data that we typically collect. So for proportions, the sample size doesn't matter.
No.
Okay.
Because you're dividing by the total.
No, I understand. This is why I'm asking. I'm just surprised because it would affect. I mean, it's a different thing to have a proportion of 30% because 1 out of 3 has some trait present, and another thing to have 1 out of 3 because 30 out of 90 have.
So the way this shows up is the confidence interval. So if the sample size is really big, the confidence intervals will be narrow. If you have a small sample size, the confidence interval will be
that's my question. So it does come into the analysis. So when I put the proportions in Jamovi or wherever, I am putting I'm not just putting the. Yes, okay. I am putting the cases versus the total. Okay, so there it comes into the analysis. Okay,
yeah, that's really useful because you should still be spelling out what your n equals is in studies, but because the confidence interval is there, the reader already has an idea of how precise is your estimate. If your confidence interval is really narrow, you're precise.
It's a big sample size. Okay, fantastic. Thank you.
It's useful. I love proportions.
And that's the only information we need from the published papers, right?
Yeah, the case counts and the total.
And the total, okay.
Isn't that amazing?
Yes, because with the continuous data, to be honest, when you said what we need, the p-values we will almost always have. But the rest of the stuff you said, the effect sizes, blah, 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 I suppose we would need to estimate in most cases based on what is reported in the paper.
Yeah.
And I'm not sure that it is always feasible to even do that with the information reported very often.
But for the proportions, hopefully they give the total. They should. If they didn't,
and I was thinking with isotopes, okay, they always report the raw data. But with other stuff like, long bone measurements, hardly ever people give their raw data. They just give you descriptive statistics, from which I suppose you can do some meta-analysis, but it does restrict you, right? Did I understand this correctly?
If they give you the proportion or the percentage and the total, then that's enough.
I mean,
But-
now for the measurements, for the linear measurements, let's say measurements of bones, where you don't have the raw data, you don't have the measurement per individual, but you just have, the mean male stature was 170 centimeters, and the standard deviation is this big.
Yeah.
Could you use that to?
You could put it together. So if you have 3 studies that reported that same thing, you could put it together. Each one would be a point estimate. So 170 plus minus 5, 172 plus minus 4, 100 and whatever, 68. And then the diamond that you would get at the end,
It would
your
feel
overall
so.
represents the data from all 3 studies. And now
Okay.
it's more precise because you've got a large sample.
So even with mean values and standard deviations, without having effect sizes reported in the paper, blah blah, it does it
Yeah.
for you, sort of.
You could argue that the mean is the effect size. Like that's what you're measuring. If
Okay.
as long as you have the mean and the standard deviation, you can do
Okay,
this.
okay, which you would
This
have.
is nice.
It is nice. Yeah, we have to play with that
Yeah,
a
we have
little
to play
bit
with
now.
it. Okay, I've got something back for you.
Thank you very
It's
much.
really useful. Like I highly recommend if you're working with data like measurements or biological data, where it makes sense to look at how many people had a disease versus not. Like proportions is the way to go. And there's a lot of medical studies that do these like 2x2 tables. I don't know if you've heard of them. That's a really good approach. Like you just look at the distribution and then talk about the proportions of like people in each category, and you can make comparisons that way. Awesome. All right. So what I want to do now is to move into our activity time. So if you go back to the OSF page for this workshop, now we want to be in the folder called meta-analyses. So go into meta-analyses. And there are a couple of different studies. If we go back to my slide, I'm just going to summarize them a little bit. We're going to look at putting together means. So that's from a paper by Wallace et al., 2015. It's means of delta 15N values and delta 13C values of pulses measured in sites in Eastern Mediterranean. We're going to look at difference between means. That's from a study by Liu et al., 2020, looking at diets from a large number of studies in China. We're going to look at correlations from a paper by Bridge et al. We're going to look at proportions from a study on non-locality using Strontium-isotope ratios, and difference between proportions, also from that same study. So those are that's where the data is coming from, but all that you need is actually provided to you. So let's first look at the mean Wallace pulses. So if you download meanwallapulses.omv, or actually, maybe you can save all of them now. And as we go through, we're going to open them one by one. So we'll start with Wallace. I'm going to close this. Open jamovi. All right, so you should be familiar with the way that jamovi looks like, just for in case there's anyone here or online who wasn't here in the first session. What you need is this ESCI button, and to get that, you go to modules at the top right, click on jamovi library, search for ESCI, and then download this ESCI plugin. Once you do have that button and click on it, you'll see that on the bottom, there's all these options you have for meta-analysis. Okay, so we're just going to go through them in order. First, we'll do means. I'm going to open the Wallace folder first. So kebab open. Then I will direct to the folders for this workshop. Meta-analyses. Okay, so mean Wallace pulses, open that from inside jamovi. And this is the data. It's not the biggest data set, but it'll be nice to kind of put things together. So we've got a couple of different sites. We've got 6 different sites located in the Eastern Mediterranean. These are big delta 13C values, so they tell us about water status of crops. So that's the mean delta 13C, that's the standard deviation, and that's a sample size for each study. If you want to look at what the original data looks like, I'm just going to pull it up here. Wallace 2014. And no, why is it not coming up? 2050. There it is. Okay, so we're looking at this figure here. Okay, so big delta 13C. We've got a bunch of sites. It was Chital on that list. Maybe it wasn't. Maybe we're just looking at these So what we're actually taking is measurements from one paper, but it's very realistic that you would have each study published separately, and then you might be interested to just put them together. So we're going to treat it as like separate studies that we want to put together as a meta-analysis. So if you open it from inside Jamovi, go to ESCI meta-analyses and means on the bottom, the last option, just to show again, ESCI meta-analyses and means. And when you click on it, you'll get this in the user interface. And all you have to do is put the variables that you have in the right box. So our means are the column called mean. So I'm going to plug that in. As standard deviation is the column called SD. And the sample size is the column called N. So I just plug in. You can either drag or click on a variable and then press the arrow into where you want it to be. You could also put study labels. So I'm going to put site into study labels. That's optional. But this way, your table won't just say study 1, study 2, study 3, but it's going to actually label it with the name of the site. And once you do that, you hit enter. It's going to data crunch for a little bit. Oh, it's really taking its time today. There we are. So at the top, we have a table of what the original results are. So for each site, we have a mean, delta 13C value. We have our confidence interval spelled out. So the lower limits, upper limits of each site. This is a table that gives us the overall effect. So this is the diamond. The diamond of our meta-analysis that we just created is 16.9. But plausibly, the true mean of all of these measurements could be between 16.1 and 17.7. So that's where our diamond is. And then if you scroll down, what we see is it's a little bit stretched, but we can compress it. So if you click on the figure and go scroll down in the user interface and open figure options, you have a way to increase or decrease the dimensions. So the height is now 750. I'm going to decrease it down to like 300 because there's a lot of empty space here, which I don't want. Okay, there we are. So now everything is a little bit, it's not as spaced out. Again, we've got our individual studies listed on the left. 0 is here if we're interested in 0. Our individual measurements, our mean delta 13C values for each site are over here. You can see that most of them have very narrow plus or minuses, but also pay attention to the scale. So the scale is from like 0 to 20. That's a really big scale. So to see the precision a little bit better, it might be more useful to zoom in a little bit. So I'm going to decrease the scale on the x-axis. The x-axis on here, I want the minimum to be like maybe 12, because we don't need all of this empty space. So the minimum on the x-axis, I'm going to say 12. And the max, oh wait, no, that was the font size. Minimum 12, maximum 20. And I'm right of my text size. I deleted my tick size. What is the default tick size you're getting? What is in that 14? Okay. There you go. Okay, so now we're a little bit zoomed in. We can see the error bars a little bit more, but still the squares are big and the error bars are small. So we've got precise measurements on the overall mean. This one is the most imprecise. It's got a sample size. If we want to know the sample size, we can click on extra details under result options. If you click on extra details, it's going to list all your sample sizes in your main table. And there they are. So the second one has a sample size of 10. It's not tiny, but it's the fact that the confidence interval is so wide, it's a combination of the sample size and also the standard deviation. So there's a lot of kind of variability on it. But now we have this diamond and we can talk about what is the overall, if we want to know what was the delta 13C of pulses grown in this specific environment in the Eastern Mediterranean, we can say that the true mean most likely lies somewhere between 16.14 and 17.65. Overall, that's where the true mean is most likely to lie. So as long as you have a reason to believe that you can put them together, that maybe they were grown under the same conditions, or even if they're not grown under the same conditions, seeing how wide the confidence interval is on our diamond tells us about kind of the variability that's in there. But it's a nice way of putting different means together. Is it working for everyone? Is everyone happy? Yeah, okay. And I'm going to see online if there are no questions online, so we're good. All right. Are we ready to move to the next example? All right, so the next one we'll look at is difference between means. So now we'll be using the file called mean difference liu diets. So click on the kebab open. So now mean difference liu. And this is the big data set. It actually comes from a paper that put together lots of different studies. We've got the sites listed here. There were some sites that were analyzed more than once. That's why we have like study Anyang 1 and Anyang 2, but it's the same site. And the actual variables that we have, we can click on, I need to make this smaller. If we're on the data, we have you can double click the names. So we have the delta 13C mean of the females, delta 13C mean of the males, then we've got standard deviation of the females, standard deviation of the males, sample size for females, sample size for males, standard deviation for the nitrogen and the carbon. So we've got lots of information here. What I want to do is, well, we can pick either carbon or nitrogen. Who wants to do nitrogen? Who wants to do carbon? Who wants to do, oh, okay. Oh, yes. So if you go to data, if you're on the data view, up here at the top, if you click on the column label, double click it, then you can like rename your column labels there. And you can also change like what type of variable it is. Is it continuous? Is it categorical? Yeah. And then you can just scroll through them. Yes. Comments online. All right. If this is a question, please can you explain why you would choose to use different kinds of meta-analysis, means difference between means, correlation, proportion? What data set, types of studies, objectives of your own research will encourage these choices? So the choice of, do we look at means? Do we look at differences between means? Do we look at proportions, correlation? It really has to do with the research question, right? If your main research question is to see, was there a correlation between stature and the length of a femur? You're going to be looking at correlations. If you want to know what the mean delta 15 and value of a population living in Cyprus was, then you're looking at means. So the actual effect size that you measured will inform what type of meta-analysis kind of study you want to do. So I hope that answers the question. Let me know if it didn't. Okay. All right. So now we're going to be looking at differences in means, and we've got carbon for females, carbon for males, carbon for nitrogen for males, nitrogen for females. So we're going to click on the tab up here, analyses, and go SE, difference in means. So now there's going to be more options to choose from. So the first choice we need to make is which group is going to be the reference and which group is going to be comparison. Again, it doesn't matter which one is female, which one is male. The only impact this has is on what's going to be subtracted from what. Are you going to be subtracting females from males or males from females? But the numbers are the same. It's just the directionality of the subtracting. So let's say that the reference will be the females. So let's put in and let's look at carbon. So carbon mean female is going to be our reference mean. Carbon mean male is going to be our comparison mean. So far, reference mean, comparison mean. Our carbon standard deviation female is going to be the reference standard deviation. Our carbon standard deviation male is going to be our comparison standard deviation. And then we need the sample sizes. So they're down here. So N female is the reference sample size, and male is the comparison sample size. We can put in the study labels as optional. So the study will be my study label. And that should be enough to put it in. Does that make sense? So we have, this is a big data set. We've got carbon, we've got nitrogen, we've got males and females, and we want to calculate the difference between the delta 13C values of the males and the females. So we set females to be the reference, males to be the comparison, and we just put everything in accordingly. So reference mean is the carbon, mean female, and then we just went through it. All right. Is everyone happy? Okay, and online, oh, there's one more question online. Oh, someone said thank you. Wonderful. If you need any more explanation, let me know. All right, so just like we had before, we've got a table that gives us an overall kind of summary of what we have. We have our mean differences for each side. So we'd already calculated what is the difference in the delta 13C values between males and females at each of the sides, and what's the confidence interval on that difference. So they're all listed down there. Our meta-analytical effect size, so that's our diamond. Overall, the difference is 0.32, but lower limit is 0.1, upper limit is 0.54. This is kind of in a oh, go for it. So for decimal points, there's another kebab up on that side. So now it's 3 dots. See those 3 dots up there? And there should be decimal points. Yeah, decimal points number format too. Yeah, it doesn't go to 1. I'm sorry. Yeah, it goes higher, but not lower. So we'll have to do the rounding to 1 on our own. All right. So once you plugged it in, you can also label. So see how it says. It's just my effect. If you want to be more descriptive, you can call it difference between male and female delta 13C values. So now we know what's in our X. All right, so here's our 0. You can, if you go to figure options, you can choose to not have a 0 there. It might be nice since we're looking at a difference of 0 has some meaning that there is none. But if you're looking at like the mean delta 13C values of crops, you might not need the 0 to be labeled. So it's up to you whether you leave it in or not. But now we've got each study represented by its square, depending on how precise it is. And overall, we've got the random effect model. If you want both the random effects and the fixed effect, you can go up to here, see how model. You can change between fixed effect and random effect, or both. So if you just choose random effects, which is the preferred one, you should always choose random over fixed. But if you want to see what the differences are, you can do a compare. All right, there we are. So our fixed effect, much narrower. Random effect takes heterogeneity into account, is a little bit wider. So overall, what this is saying is that the difference, the true difference between the male and female delta 13C values at these sites, it was very small. It's the actual number is 0.32, but plausibly it could be between 0.1 and 0.5. Like that's kind of on the edge of being interpretable, right? Like if it was above 1 per mil, there's a lot there to talk about. But after you've considered what the measurement error is, what variability between measuring different elements in a body is, sometimes there's heterogeneity within an element. So you might measure like one end of a femur versus another end of a femur, the value might be slightly different. So after taking all of that into account, a difference of 0.3, it's not that big. So you would want to look at something much larger. But this is where the context comes into play, right? It's good to have expectations in the initial stages of your research about where your thresholds would be. Something else we can do is see how on the effect side, there's another drop-down menu, and it says original units. So the original units that we used were per mil values. Here, differences in per mil values, but we can use those standardized mean differences. So dividing by the standard deviation at each site. So all you have to do is just toggle to select standardized mean difference under effect size. And it's just going to standardize everything for you, which is great. All right. So now see how it says DS. So D is Cohen's D. It's like standardized mean. And the little s is for standard. But we've got the same X, difference between males and females. Our 0 is over here. But overall, we're looking at it in terms of standard deviation units. All right. Does anyone have any questions? No, online. No questions online. We're doing good. Should we move to the next example, or do people want to take a pause? How are you feeling? Are we can keep going? Okay, cool. Let's keep going. So next example we're going to look at is correlations. This is really useful, particularly for bioarchaeology. The best examples I found for this work from bioarchaeology. So a paper from Bridge et al. Let me actually show you what the paper looks like. Bridge. Why am I not finding it? What's the year? 2020. There it is. So the paper is called Estimating Stature. Estimating stature using human forearm and leg anthropometric data from an Australian female sample. And I should mention, I'm not saying this is a bad paper. It's a great paper. I'm just using it as an example of how we can do a forest plot. So this is a paper where a number of individuals from Australia were actually measured to see if we can have equations that are specific to Australia to estimate the stature of people based on their leg measurements. One of the underlying motivations for this was for forensic purposes, but the equation can be used for archaeological context as well. So they did have a bunch of measurements. They knew what the stature was of each individual. And then they measured the left ulna, the right ulna, the left radius, right radius, the main sample size was 60, and then 7 of the individuals, can't remember what was up with them. They might have been a different age category, but that's why we have the sample A and A1. But we'll look at just the overall, everyone included, and equals 60. So notice how what we're presented with is a lot of these R values. So Pearson's R is an indication of the strength of linear correlation. So if we put our element measurement, our left ulna on x-axis, and our stature, the height of the individual, on our y-axis, we want to see how well correlated are they. So Pearson's R is linear correlation. So we're drawing a linear relationship between what's in our X and what's in our Y. We've got the Pearson's R here, and then we've got this p-value. Notice how in every instance, the p is less than 0.0001, and that's because the confidence interval on that R doesn't include 0. Okay, it could be that the confidence interval in the first instance spans from like 0.001 to 0.09. That's a very wide confidence interval on an R value, but it could also be from 0.663 to 0.665. Like we don't know. Just based looking at the p-value, we don't know how wide or narrow the confidence interval is. All we know is that it does not include 0. So what I want to know is I want to basically get an overall estimate of the correlation between stature and these different elements. So that's what we're going to do. We're going to create a forest plot, taking in all these R measurements together. So this one is called Correlations Bridge Stature. So if we open it from within Jamovi, correlation bridge stature. Now, I should say I'm not a bioarchaeologist, and this is a hypothetical study. In an actual study, you wouldn't want to combine different elements, obviously, right? Like you would want to have one paper that measures the correlation between stature and the right ulna, and another paper that does also right ulna, and a third paper that does also right ulna. I don't have that. This is an example that has different elements, but in a world where we're interested between the correlation of different elements and stature, that's what we're calculating. But if we're doing this properly, we would want to have the same element from different studies. So this time, we're going to go to SE and correlation. And all we need for this type of forest plot is the R values and the sample size. So our correlation, the column called correlation, will go under R values, and sample size will go under sample sizes. We can have bone as our study label for that. And we're going to hit enter. And there we are. So now we've got, remember how we were given the p-values, but not the confidence intervals on them? Now we have the confidence intervals on the individual correlation coefficients. So what this is saying that in the case of comparing the left ulna to the stature, the R was 0.66, but plausibly the true correlation could be somewhere between 0.49 and 0.78. Like that's probably at least moderate, or if not, moderate to high correlation. So again, having those ballparks of what you consider to be small, medium, large is really helpful, especially for Pearson's R, particularly because different fields have different thresholds for like what R values should be. If you're doing like medical research, you really want your correlations to be really high. For like isotopic studies, they very rarely are going to be like above 0.8 or 0.9. So thresholds differ depending on the question and depending on the field. So here we have the R value, our lower confidence intervals, lower limits and the upper limits of the confidence intervals. And the overall effect size, now we're being told, is 0.71, but plausibly it could be from 0.6 to 0.76. And if we want to look at our table again, it's super stretched. So I'm going to go in and change my dimensions again. So once again, I'll go under figure options. And my height, let's go down to 300 again. There we are, and they're very similar, but and also notice how they're not symmetric as well. Again, because we've got that upper and the lower limit. The upper limit of the R value is 1, the lower limit is -1. So strong positive correlation, strong negative correlation. There is 0. But overall, from all these measurements we have here, the diamond tells us that the correlation is at least moderate. So to spell it out in a paper, we would spell out the whole thing, 0.71, and it's best to use square brackets to spell out a confidence interval. So we'd say 0.65, 0.76, and then close your square parentheses. And we could change our effect to be something like correlation between stature and element. There you go. Oh, something that I like to do when I make forest plots, which makes it easier for readers to kind of see what's going on, is I like to put my sample sizes in these labels. So you could actually go back to your original data here. And in the first column, I would just say, whoop. Oh, well, no, I would say n equals 60. And in the second one, it's n equals 60. Here, all the sample sizes are the same, but in real meta-analyses, they might not be. But now that they're spelled out there, it's easier for the reader to actually see what your individual sample sizes were. You could also ask it to spell out the confidence interval on the side. So if you go to aesthetics down here and scroll down, oh wait, it's not on aesthetics. Is it under? Oh, sorry, it's under the figure options up top, include CIs. So under where we change the height, if you check on include CIs, it's going to have the confidence intervals on the side. So again, it's really, it makes it really easy for the readers to kind of interact with what's going on. And just to remind you how jamovi works, if you were to save this document, everything would be saved on there. So all the adjustments that you did, like the aesthetic adjustments, everything you put into the user interface, all the changes to like the y-axis, x-axis, it's going to be saved on there, as well the outputs. And you can copy like the actual image. I just double clicked on the image and you can copy it or export it and then put it in a Word document or put it in a PDF or a PowerPoint presentation or somewhere else. And you could do the same to the tables. So it's really easy to use and to be completely kind of in line with what the makers of this software did. Is here are the references for how to refer to using the jamovi platform for creating meta-analyses. All right, so we've done 3 types of forest plots so far. We looked at combining means, we looked at combining differences between means, we looked at combining correlations. We have 2 more to go. We're gonna look at proportions and differences between proportions. So proportions, we're gonna go kebab open. So proportion leopard. There you go. And I'm just going to show you what the paper looks like from which this data originates. Leopard All right, so this is a meta-analysis of itself. It's called meta-analysis. They don't use forest plots though. What they did is they put studies together. That's why they're calling it a meta-analysis. But they're not using like a random effects model. They're not looking at homogeneity of the studies. They're not putting together the results. They're just listing different results, which is not a bad approach. Like it's done quite commonly in the literature. We're just looking at how to translate this into a forest plot. So they're looking at strontium isotope ratios, and then they give us this table which has different phases. So we've got some sites that date to the Neolithic, some sites that date to Chalcolithic and early Bronze Age, some that date to Middle Bronze Age, early Iron Age, and then late Iron Age. And notice there's a lot of columns going on here, and that's because the interpretation of how many local and non-local people there were actually changed. So in the original publications of all of these studies, the authors made some interpretation. So they said that at this site, 15 of the people were local and 4 of the people were non-local. Now, the authors that actually created this meta-analysis that put all the data together, they decided to have more strict criteria for who's considered local and non-local. They defined the locality using like 2 standard deviations around the mean. So they had stricter criteria. So now the numbers actually changed a little bit. And that's something we can also look at in a forest plot. That's going to be what we look at with the difference between proportions. But first, I just want to put proportions together, see what is the proportion of people that were non-local in the Neolithic at different sites. So here's the data. When we open it, you should be seeing this. Is everyone seeing this? Okay, awesome. So we got the Neolithic, Chalcolithic, EBA, MBA, early Iron Age, and late Iron Age. We got the site. And for working with proportion, we need the case number and we need the total. That's how the proportion is calculated, right? If there are 5 non-locals out of 20, the proportion is 5 out of 20. And that's all that jamovi needs to create that forest plot. So we're going to go to SE meta-analysis proportions. And then we're going to plug in. So our number total are the sample sizes. So number total sample sizes, and the number of non-locals is the case counts, right? We're interested in the proportion of non-locals. So that's our case count, and the total is the sample size. We can put our study labels as our optional label, and then we wait. There we are. So here are individual studies. Uppercase P is for proportion, not to confuse with lowercase p, which is, we know what that is. We've got our confidence intervals, lower limit, upper limit on each of the proportions. It's really easy to just convert to percentages. You multiply by 100. So that's 4%. And you can spell out the confidence intervals around percentages the same way, right? Like if you were reporting the results from Isotope, you can say that 10% of the people were non-local and the confidence interval is from 2% to 32%. So now the true proportion most likely lies somewhere between 2 and 32. That's a wide interval. It could be almost nothing or very, very small amount of non-locals to quite, a third, almost a third of people being non-local. So that's what we need to take into account when interpreting it. And scrolling down, now we can relabel our x-axis. So instead of my effect, I'm going to say proportion of non-locals and make sure that our random effect is selected here. Click enter. All right, there we are. When I work with proportions, I really like to know where 100% is. So notice how our x-axis isn't going all the way to 1 because it wants us to see the definition of like what the confidence intervals are doing, but it's almost creating a false impression on how big the proportions are. So I'm actually going to increase the x-axis all the way to 1. I want to know where 100% is, just so my eye isn't kind of skewed. So figure options. And my x-axis maximum, I'm going to say 1. Maximum 1. Enter. There we are. So we are a little bit squished. There's a lot of empty space, but we're not led to thinking that there's a lot more, that the proportions are higher than they actually are. That's 100%. So overall, if we want to say how many people from all of those different periods around the Mediterranean, how many people were non-local? Well, here's our overall diamond, and to spell out the difference, we would say 5%. Proportion is 0.05, but anywhere between 0.03 to 0.08. So that's the most plausible interval for where the true mean is most likely to lie. What's compatible with our data. All right. Is everyone happy with this example? Yes? Question? Woo! All right. Can you show us an example of moderator analysis? Oh, I can. I don't know if I have an example. Do you have an example ready? I don't have an example loaded in the OSF file, but there are examples in the textbook. They have really nice ones, but not archaeological ones. Can I get back to you? I'll try to upload something to the OSF file if we take a break, but I make no promises. If not, please email me later. I just don't have anything handy right now. Thank you. Awesome. All right. Lastly, let's look at difference in proportions. So that's the last file that's been shared. So let's go kebab open and proportion difference leopard Neolithic. So now we're looking at the same study. We're looking at that meta-analysis, taking together what the numbers of people that were local and non-local were from the Neolithic. But I want to make a comparison of the proportions that were estimated in the original studies and these new estimates. Now, I know there's a lot of missing data, but we're going to ignore that for now. We just want to walk through the steps, right? So I want to know how much of a difference is this stricter criterion for considering who's local and who's not local? How much of a difference is it making? How much are the proportions changing? So for that, we've got a file called this. We've got all of our sites. We've got the original count, so original count of non-local people. Then we've got the original total. Then we've got the new count, the recalculated number of individuals, non-local individuals, and the total is the same. But we need a new column just so that we could put it into our user interface. So in this instance, we're going to go to SE difference in proportions. And we just have to plug it in. So our reference group is the original calculation and our comparison is the new, the recalculated. So case counts, original count is the first one. Sample sizes in reference group. So that's original total. Case counts in comparison group, that's the new count. Sample sizes in comparison, it's the new total. And the study labels are the site because all of it is from the Neolithic. We're just looking at Neolithic right now. And enter. All right, so there we are. Here are our differences. So P-diff, that's the difference between the proportions of the old calculation and the new calculation. Here are the confidence intervals. Here's our effect, our overall analytical effect. So funnily enough, our overall effect is 0. It's from negative 0.03 to positive 0.03. We don't have a massive data set. This is just an example. If you were doing this more consistently, you would want to have more studies, but the number of studies is not small. Like it just turns out that overall the differences are smack on 0. I'm going to move this a little bit just so I can make this bigger. There we are. Okay. I'm going to relabel my effect. So difference between old and new proportions. I've got my random effect size and enter. So now we are going the negative numbers with proportions, but that's because we're calculating a difference, right? If you subtract a proportion of 0.3 from a proportion of 0.1, you're going to be in the negatives. But if you were just looking at one proportion, you can only go from 0 to 1. So there we are. There's all the individual estimates on the difference, and they're really, really wide because the sample sizes are very small. Like if you look at what the data set looks like, some of them have a case count of like 2, some are 0, some are 3. So it's the actual numbers are very small. That's why we've got such imprecision on some of them, but some are more precise. So there we are, an example that's not so bad. And our overall diamond is down here. Yes.
The P difference value, can we also translate that to percentage difference?
It is, yeah. It's literally the same. So like now the percentage is 0, but the plausible difference is between a -3% and +3%. Yeah, so if you just multiply any proportion, even a difference in proportion by 100, yeah, you've got your percentage.
In terms of total percentage or in terms of difference to the old? So when we had in the original study 20% of non-locals, for example, and now we see, okay, there's a 3% difference. Is that is 3% of 20 or
3? So
in
if,
total
let's
terms?
say your old calculation was 20, your new calculation is 17. The difference is 3%. But if you're working with proportions, you're going from 0.2 to 0.17. So difference is 0.03.
Yeah.
So it's like any of those components, if you multiply them by 100, you'll get to the percentage.
Okay.
Yeah. But you actually touched on a really important point, which is percentages can be tricky. The reason this book and a lot of other books prefer to use proportions is because proportions cannot be misunderstood, right? Especially when we talk about like increases. Increase in percentages could mean different things. So like if, let's say, in Cyprus, in 2024, 10% of the people went to the movies. And in the next year, 20% of people went to the movies. Some people would call that a 10% increase. Some people would call that a 100% increase, right? So you really have to be, because going from 10 to 20, the actual number is 10%, but if you're starting with 10%, you're doubling. So that's an increase by 100%. So the way to not get caught up in language with percentages and changes in percentages is to use percentage points. So if you say there was an increase in 10 percentage points, the only way that could be is going from 10 to 20. Yeah. Or using proportion. Wonderful. Awesome. All right. Are there any questions online? I'm just going to check. It sounds like there aren't. So those were the examples I wanted to look at with moderators. Should we take a short break? Just a little bathroom break, stretch, 5 minutes, 10 minutes? 10 minutes so we can take time. And then when we come back, we're going to be talking about data visualization and more on effect sizes. Yes. All right. See you everyone in 10 minutes. All right, so we're ready to start our last part of today. I'm just going to close these. Or actually, no, I think I can just direct away from it and share. All right, so the last topic I wanted to talk about is graphical visualization. Now, this is a really big topic. There's books and books and books written on the topic. There's a very specific reason I wanted to talk about it today, and that is because, one, it is statistics. That's part of what we should be putting under the umbrella term statistics. But what I'll do at the end of today's workshop is I want to tie everything together. I want to tie what we talked about, estimation thinking, asking questions that are estimation oriented, and thinking about the presentation of data, thinking about effect sizes, thinking about uncertainty, confidence intervals, and tied everything together and talk about ways of just presenting everything in the most informative, clear, and effective way possible. So this is another arena that I wasn't really part of. Oh, there's some online comments. We are back. Okay, there's a long question that I'm gonna get to it afterward. Sorry, I don't think it's not on data visualization. All right. So this is another arena that I wasn't really involved with when I was a student. I didn't really go down the road of reading what are the principles of good data visualization. I didn't read any of those books, or there's papers. I didn't interact with that literature, and I really regret it because a lot of the principles, they're really straightforward and they also save you a lot of time. I feel that a lot of the times we kind of invent the wheel, or we have our students invent the wheel, or we kind of just have students just play with the data and find the best way of presenting the data. Well, there's actual principles of good data visualization that save us time, and that kind of mean that we don't have to invent the wheel. We just take our new question and figure out a way to kind of present it in ways that are more faithful to what we want to do. So I can't cover all the principles of good data visualization, but I wanted to touch on just a couple, and then we'll talk about effect sizes at the end. So next slide. All right. So I'll show you a bunch of examples. This is from the book called Graphical Discovery, A Trout in Milk and Other Visual Adventures. It's a really, really good book. It's from, I think, 2005. It's written by someone called Weiner, and really, really good read. Short and nice and convincing. So here's a figure that Weiner presents in the book. And this is what the caption says. The caption says, operating hours of 9 major currency exchanges shown on a geographical background. Okay, so we've got the globe, and then we've got our different time zones here. It says -1, -2, depending on where GMT is. We've got these different lines, which are showing when different currencies are open. We've also got these pie charts. Now, what do you think is the point of this? Like, what is the overarching question behind it, or even the overarching aim? Why did someone create this figure? Or if that question is too hard, what could we do with it? Like, how can this be useful to us?
Like it's normally
Absolutely. Yeah. So we know there's different currency exchanges in different parts of the world. We have the world, so we know where the locations are, and we have to pay attention to time zones. Absolutely. Anyone else? Yeah. Absolutely. So when is their overlap? And perhaps is there a time when nothing is open? Like, what if there's a time in a 24-hour cycle where nothing is open? Like, is that, and can we read that from this? Is it easy to read? It's not. Yeah, I agree, because it's trying to do too much. It's overlaying the actual time zones with the opening times and the geographical locations, and it's doing it in a way that some people would call chart junk. So just because we can create something doesn't mean that it's necessarily the best way to present data. If our main question is about showing when are the currency exchanges open, when is the overlap, and kind of how long are the different intervals of which they're open, we could do much better by showing something like this, right? It's giving us the same information. It's showing where the different the cities are. It's showing us the intervals of when they're open. Importantly, it's showing us that there's 1 hour here where nothing is opened. So we've got the market in San Francisco closing, but before the one in Hong Kong opens, there's nothing there. We can't figure it out from here. There's too much information on there. So the number one rule of good data visualization is show the data in a way that allows the main information to jump out at you. If the main message, what the figure is trying to show, if it doesn't jump out at you, you need to redo it, because the reader needs to get the actual finding as efficiently as possible. And yes, this doesn't have a map under it. It might look a little bit less fancy, but it's actually allowing us to read the information. So this is a much more effective way of showing the same information than that. So rule number one, don't fall victim to chart junk. A lot of like every year there's more and more programs that are online, or you can download them or work with them in browsers that can create really beautiful images, like so many different like profiles, or so many different ways of just crunching numbers and creating something beautiful. But just because a computer can create a figure doesn't mean that that's the most effective way to show your data. So always keep in mind what you are trying to do. What is your main question? What are you trying to show? What is the purpose of a graph? And that should be the number one concern. So in archaeology, again, no citations. I don't want to put someone on the spot. I actually have an example of mine. I hope this is no one in the room. No? Okay. I found this. And this to me is one of those examples where too much is shown in one. It looks like a quilt. It looks like a painting. So we've got different grave numbers. We got some individuals. We've got so many different variables. We've got height and number of grave goods and bone depth of 13C, then bone depth of 15N. And then the colors, I'm not quite sure I understand. It says detect deviating cells, map of this location, red cells higher than predicted values, orange slightly higher than predicted, blue lower than predicted. But then, okay, but what are we seeing? What is the message? And also, it's not necessarily the case that if like bone depth of 13C goes up, bone depth of 15N goes up as well. I think they were looking at some correlations between the variables as well. So if the message doesn't jump out at you initially, I would say try to redo an image. It's not necessary to show everything at once. Here's another example. I think this is from forensic archaeology or forensic studies. There's so much going on here. Oh my God. Like what? It's a plot. It's got lots of different labels, numbers. This is almost impossible to read. But yeah, text is important in charts, but too much text is, you can't do it. And just so that I don't, only show examples of other people, this is an example, which now I would call chart junk. It's not even that old. It's from my 2020 paper. And I try to graph everything I had from everywhere. So this is a study I did on a couple of Byzantine sites in the southern Levant. And I measured delta 18O values from tooth enamel. I measured delta 13C values from dentine. I measured delta 13C values from the enamel as well, and then delta 15N from the dentine. So I had two different proxies for carbon, one nitrogen, one oxygen. I had different teeth. I got M2 and M3 indication down here close to the x-axis. I had my sites color-coded. The legend for the sites is up here. I had different species which were coded with different symbols. So I had like my sheep and my goats. I had the carbon, whether it came from the carbonate of the enamel or whether it came from the dentine, shown with different colors. It's too much. I don't need to show everything. What I need to show is what answers the question, right? So what would have been more useful is to show, okay, let's look at the oxygen values. What are the mean values of my sheep from one side? What are the mean values of sheep from another side? I made a distinction between what I call dampened and non-dampened sequences. So this has to do with, remember those sinusoidal sequences I talked about? There were some that were really wide. The amplitude was really wide. And there was some where the amplitude was a little bit dampened, which is important for interpreting delta 18O values in teeth. So I had these two groups. So what would have been useful is to show the mean of one group, show the mean of the other group, and then put a confidence interval. And now there's ways to talk about like, okay, where is the true mean of the dampened and the true mean of the non-dampened individuals most likely to lie? So that would have been more useful instead of showing everything at once. All right, this is an example. So this is not chart junk, but I just wanted to show these to kind of talk about how different data sets could be used most effectively in different ways depending on what the question is, right? So these are all sequential stable carbon and oxygen isotope values. And sometimes you're looking for differences. Sometimes you're looking at the shapes. Sometimes you're looking at absolute values. And there's very distinct approaches for how to make those messages jump out, okay? So this is an example where the main question was comparing the delta 18O values of teeth of Neanderthals to the delta 18O values of modern humans from the same kind of climate. And the main finding was that the Neanderthal teeth were all below this 18 per mil line, okay? And all the modern ones were actually above. So it's important to see where the line is and to see that the Neanderthal values are under it. So that's the main message. The message is the values are low, and this graph is accomplishing that message. But in some other instances, you might be more interested in showing the shape. So this is my case study, one of the case studies I worked on in my PhD. This is from Makrialos in northern Greece. And I had some sheep from like a habitation context and sheep from a feasting context. And I wanted to see if the animals from different contexts used for different purposes, if they were managed any differently. Like, was it the case that the sheep that ended up being used for the feast, like were they grazed in a different location to the sheep that were consumed on a more kind of daily occasion? So here it was the shapes of these carbon and oxygen delta 18O values that I was most interested in. I was also interested in looking if some of the values fall into that shaded zone. The shaded zone, the green, indicates input of C4, these more arid adapted plants. So if those delta 13C, which here are shown with the closed black symbols, if they are in the shaded zone, there might be some input of C4 plants. So it's the shading, it's the shape of the sinusoidal curves, and kind of comparing between the shapes of the individuals that was most useful for this particular study. But then in other studies, you might be interested in comparing the absolute values. So you might want to overlay them. Sometimes you might want to kind of adjust the x-axis a little bit in case you're looking at kind of what are the maximum values, what are the minimum values. You might have to do a little bit of adjusting, but if you don't need to do that, you can just plot everything on top of one another to look at, are they covering the same range? Are they covering different range? So always keep in mind what you are trying to show. What is the main question, purpose of the graph? Is it the shape? Is it the absolute values? Is it comparisons between different individuals? Okay, here is another example. It's not showing the x-axis for a specific reason, but it has 4 data points in this graph and 4 data points in that graph. Now, you know that the y-axis is cost in dollars. What do you think we're looking at? Are we looking at, like, what is the trend here? And how did the trends compare? Is anyone seeing like an increase and then a decrease? Yeah, maybe a little bit. And in the other instances, decrease and increase. Yeah. Yeah. So what it actually is showing is it's the same data and it's food, but one is in English and one is in French. Okay. So we got our bread over here and the bread here is there and our meal and our milk. So it's the same data, but our actual categories have been organized differently on the x-axis because they are alphabetic. They're alphabetic in different languages. So because of that, some people might kind of interpret an increase and a decrease. Some people might say there's a decrease. Those trends don't matter. Like, one could argue that you don't even need to connect the individual points because there's nothing about connecting them. You need to know what the absolute value is. And we need to pay attention to like how we present the data, how categorical data is organized on an x-axis. So the second principle, as it's spelled out in the book from Graphical Discovery, is Alabama doesn't need to come first. Now, this might not mean much, but if you've grown up in America, which I didn't, if you've ever tried to memorize all the names of the 50 states, Alabama's always first because it's alphabetic. So if you're memorizing them, Alabama's first. So the main message of this author of this book is you don't always have to order your categorical groups alphabetically. There might be a more useful way of ordering them. So be mindful about how categorical variables are ordered. What is the most appropriate? Sometimes we might want to order them by groups. So here's an example of this is hardness results for bone tool sample. And I think the comparison was done between like one species and another species. I can't see my notes at the moment because we're on Zoom. So I don't have the specific details. But what I wanted to point out is that the two up here are in one category, and the two down there were in another category. So I would argue that it would be best to put those two together, and then those two together. Just because the actual numbers of the context, the features from which these bond points derived, because they order like that in terms of the numbers, that's not necessarily the best way to order them on the x-axis. So I would pay attention to maybe grouping different contexts together, or different like species together. Here's an example of how different species are put into different panels of a plot. This is really common now. People like to use like little animal logos to indicate different species. What I would do differently about this specific example is it's not necessary. I think that the ordering has to do with the names of the context from which these individuals derived. And that's not really doing anything for us. What would be useful in this case is to maybe order it from like lowest to highest. So then it's easier to like ballpark where are the lowest values, where are the highest values, and kind of what range we are spanning, as long as we're not implying that there's like an increase in something or a decrease in something, as long as we know it's like one snapshot of time and we're just looking at kind of the spread of values. So that could be one way to reorder this, or like color coding box plots is also really useful if you're distinguishing between different types of groups. Increasing, decreasing values, that's what I just mentioned. So this is an example of an experiment done on crop stable isotope values, and we're looking at delta 59 and the category that had no manure, the category that had 10 to 15 tons, the category that had 35 tons of manure. So because it's ordered by increasing amount, it's a lot easier to see like what the actual increases were. Here we have ordering geographically. So these are strontium isotope ratios of people from different regions. And we've got Northern China, here in Mongolia, I can't read it. Oh yeah, North Mongolia, South Mongolia, and then BBS, which is not defined in the caption, and I can't remember what it is off the top of my head. But geographical ordering can be really useful, especially if you're looking at maybe like highland altitudes and lowland altitudes, or places that are closer to the coast. So alphabetical ordering, not always the most useful. Try to think at what the context is. Are you most interested in seeing what the range of values is, whether there's an increase, or are you interested in seeing changes across the geographical location, or any other grouping that might be archaeologically meaningful? These are some other examples of plant crop isotope values, but we've already covered the chronological or geographical ordering. All right. Another principle of good data visualization. So what we're looking at here is the finishing times of people running the Boston Marathon. So these are men and women. Men have been running it for a lot longer. They were allowed to run it in 1900s. Women were not allowed to start running it until like the late 1970s. So that's why the data is spanning a different length of time. But if you look at what's happening with the finishing times, is that they're going down, right? Everyone, like over time, people are running the marathon, which is the same length. They're running it faster. The men are increasing like this. The women are increasing a lot more sharply. Now, if we were strictly looking at this, just not knowing what the context is, just looking at what are the data points doing, if we're putting regression lines on the data, which is really common, people often put regression lines even if they don't need them. Even if they just talk about correlation, which they can describe with like a correlation coefficient, lines are really common. But I think lines should only be there if they actually are useful. But if we now look at what the points are doing, what the lines are doing, one could predict that at one point, women are going to start running the Boston Marathon faster, right? Like that's what the trend line is showing. So here's another important principle of data visualization. Don't go beyond what the data range is showing, okay? Our data range is from here to there, and here to there. We can't really project into the future, especially if there's a projection of like crossing, lines suddenly getting kind of, if there's like a switch, it's hard. It's just going beyond the data range could be really, really tricky. So how is this relevant to us? Well, sometimes we get data sets that might actually have flips in the trend. So these are tons of foliar. So these are values of leaves, tree leaves, the foliar delta 15 values from all over the globe. So we've got the mean annual temperature in different parts of the world, massive spans of the foliar delta 15N that were actually recorded. Now, if we are looking at the range here, we're in the positive numbers between like just under 5 degrees to 30 degrees. From here to there, there's an increase. There's a positive increase. The variability is massive, right? Like you can't actually say that if you have a number, you can predict what temperature, what individual temperature it could be assigned to, because there could be so many temperatures that it could fall into the range of. But if we just look at this, we're like, okay, there's a positive trend, temperature goes up, delta 15N goes up. Now, if you remember, be careful about venturing beyond the data range. If we actually see what's happening with the foliar delta 15N value in the negative temperatures, the trend is flipped, right? And this is not something we can ignore. So if we only have the data for the positive temperatures, it would be really easy to just extend that trend, keep going down, and keep saying that the lower the temperature, the lower the delta 15N. But there's a split around just above 0, like 4 degrees, that actually reverses that trend. So careful to venture beyond the data range. Axes are really important. So here's another non-archaeological example. It's this is showing us what the stock market is doing. There's lots of figures out there about this, but this one has a very wide x-axis range, right? So it's got 1900, 1910, going all the way up to 2000, and it's got the Dow Jones, kind of how it's fluctuating, and the author of this figure put important events in the 20th century to see if they had an impact on the stock, right? So we've got post-World War I, there's depression, post-World War II, the 18 years of constancy. So it's kind of making, it's looking for trends on the large scale. But you could go to any scale you like. You could zoom in on this and look at what the stock market is doing, like down to the minute. But that's not useful. Like, why would we want to know what the stock exchange is doing at 11 versus 11:05? It doesn't help us predict what's going to happen tomorrow. It doesn't help us predict what's going to happen in a single year. So there could very well be fluctuations in any given variable on a very minute scale, but that scale might not be relevant to our question. So we should always remember, what is the scale that we're interested in? What scale should we be operating at? And then make sure to use the appropriate scale to the type of data that we have and the question that we're trying to ask. So another principle of good data visualization: use the research question to determine the appropriate scale. What are we trying to show? Which scale will show it the best? I've seen isotopic graphs that go just a little too narrow on the x or the y-axis, and that kind of fluctuation isn't necessarily helpful. So it's the question is really key here. Here's an isotopic example. This is from a compound-specific delta 15N analyses. So we've got the bulk delta 15N values of the whole the collagen, and then the glutamic acid, we've got phenylalanine, and we've got lysine. Now, what you can see is you're seeing a spread of data. You're seeing some regression lines. This is for like regression line for plants only. And what is it? I forget what the dashed versus the. So dashed line is terrestrial plants only. Equation, vision, linear regression, terrestrial plants only. Okay, so all data is straight line, and the terrestrial plants are the dashed line. Now, the reason I bring this up here is notice what the y-axis is doing. The y-axis is different in each case. So here we're going from -2 to 12. We're going from 0 to 25, and we're going to 0 to 15. Now, this is the best way to see kind of the pattern at the highest resolution, like to see only the part where the data is distributed and not have sections of the graph that have empty space. Empty space can be tricky, but the effect that this is having on me when I read it is it's giving me a false impression on how steep the regression lines are, right? It almost looks like that's really steep. But the dashed line looks almost equally steep, but then if you pay attention to what how the y-axis is distributed, the steepness actually isn't the same, just because the scale is different. So especially comparing between different elements, comparing between different data classes or case studies, and especially using regression lines, we have to make sure that if we make comparisons, if we put things next to each other, we at least remind the reader in the caption or somewhere else that the scale is different. Because if they're not reminded, their first impression is to just use the steepness to kind of make an impression about what the variable they're doing. All right, here's another example. These are also foliar delta 15N values. Again, lots of different panels next to each other. I would argue that 2 points, like any 2 points can make a line, right? Like, anything can be connected. But again, we're going from -4 to 2. We're going from 0 to 8. And that's tricky. Like especially for plots that have like 20 different panels, which there are figures like that. It's really hard to choose a scale that fits everything, right? If you've got lots of different variables, you're showing so many different patterns, it might be hard to find a scale that fits everything. But if that's the case, if you can't find a scale that fits everything, at least kind of maybe use some graphical or aesthetic distinctions to draw the reader's attention. Like maybe you can like somehow color code the values, or at least remind the readers in the caption or something that was going to tell them, like, you guys, we're not looking at the same scale in each case. So don't make comparisons about like the steepness of these lines. Here's another example. This is looking at strontium isotope ratios. Strontium isotope ratios, it's important to pay attention to the x-axis scale, because you needed to kind of understand what's happening in the local landscape, right? Like if you're in a region where the geology doesn't vary for like 200 kilometers, you know that everything within 200 kilometers is going to look very local. But if you have a geology that is really, really variable, you need to make sure to tell the reader that you're aware of this variability, and that you're kind of looking at what is the closest possible location where a non-local value could be coming from. And a good way is to use the x-axis for that, right? So in this instance, we've got on the x-axis, we've got an indication of rainwater is. We've got this local baseline that's been calculated, and we're told that the animals, where the animals placed, and we've got the bedrock, the rainwater, different types of soils. So this is kind of giving us you kind of take a step back and say, what is the variability? What could it be? What is the maximum possible range of strontium isotope ratios? And then ask your question about who's local and who's not local. Oh, labeling panels is also really important. I'm really big on this, but I know there's like variable feelings on this. I really like individual panels to be labeled, just so you don't have to kind of keep referring to the caption, right? Like here you have so many different panels. We're looking at plant isotope ratios, carbon and nitrogen. Notice that each of the labels is not actually labeled individually, but we have to go between the caption to know that, like, the open symbols show the dry wash side, and the triangles show the plant side. Like there's so many different groups, but you actually aren't told that this is showing the dry wash, this is showing the arid region, that's showing the one kind of plant, this is showing another type of plant. I highly, highly recommend you use panel labels to kind of guide the reader, because if the main image doesn't jump out at them, they might not actually spend that much time with it. And the point of papers is to kind of make them as skimmable as possible. And explain your colors or symbols. This is a paper, or it's a figure from that same foliar delta 15N paper. I don't know what the red means. It's not described in the caption. It's probably somewhere in the text where I missed it, but it's not explained. And I'm like, well, help me. you got to give the readers as much information to read a graph as possible. Some people like to explain colors like in writing, in the legend. In the caption, I really like there to be legends. Like if you have a red triangle, say what red triangle is. If you have a green circle, say what a green circle is, like in a legend. But a lot of people like to write it out in the caption. I don't think it's not as fast to kind of decipher as a legend is. Something that's also really useful is to check that colors are colorblind friendly. A lot of people have different types of color blindness. Red-green color blindness is the most common, but there's other types as well. And there's simulators online that allow you to kind of see what the image looks like to people with different types of color blindness. So there's one that's called Color Blindness Simulator. You just upload your JPEG and then you choose what type of color deficiency you want to select. And then it's going to show you what I put in that image, which is a lot of green and a lot of red. It's going to show you what the colors look like. And that's really useful to check that main patterns that you want to stand out are actually standing out to different readers. I've heard of an example where someone spent so much time on the color, on the aesthetics for their PhD, and then found out on the day of their oral defense that their examiner was colorblind and they just couldn't see the patterns. And so, yes, colorblind simulators are really, really useful. We should be paying attention to them. Okay, so what I've talked about today with the principles, I didn't talk about all the principles of good data visualization, and I've only summarized the main ones from like one book. There's so many other resources out there. Recently, there was a paper called A Checklist for Designing and Improving the Visualization of Scientific Data. Checklists are really, really useful. There's a whole book on them. It's called the Checklist Manifesto. I told my students about it, and I don't think anyone really read it. But checklists revolutionized safety in aviation and hospitals. It turns out the two arenas have very different approaches to safety. Like aviation, there's so many checklists. Every time that a plane is ready to depart, you have to do a checklist. If something goes wrong, like when the motors went out in the plane that landed on the Hudson, the first thing that the pilots did when they lost the motors, they went through a checklist. Like every time something happens, you have to go through a checklist. In hospitals, they don't use checklists as much, and they should. They don't use them because they don't report mistakes as much as they do in the aviation industry because they don't want to be sued, right? Like insurance companies have a lot to deal with, and the hospitals don't want to be sued by patients. So they actually hide mistakes, which is horrible to say, but this happens. Read the book if you don't believe me. So Checklist Manifesto is great. And I was really happy to see that this paper about good data visualization practices is called A Checklist. And it goes through some really nice approaches for making certain patterns stand out, choosing colors. Like if you have a set of bar plots, you might not necessarily need to show everything next to everything. You might want to highlight a specific bar, like specific group, and you might want to see how that one is changing through time. So if that is the case, make everything else kind of a little bit dimmer and highlight the pattern that you want to stand out. This is not data manipulation. Data manipulation would be changing numbers and redoing kind of calculations to make something look more important than it is, but just highlighting different columns to make patterns stand out, that's, I think, useful. That's not manipulation. That's useful science. This is an online blog that I found out a couple days ago about at a conference, and it's called, "If you can't sketch a figure, then you don't have a hypothesis." And it's true. I had my students in my class on quantitative skills for archaeology. I had my students sketch out graphs. Like everyone chooses a paper, chooses one figure to give an oral presentation of. And the idea behind the oral presentation is not to summarize the whole paper. Like, yes, they have to say what the main question was, what the aim of the research was. But the main idea is to look at the figure, see how it was made. Does it show what the authors say it shows? And then sketch how they would do it differently. And it has to be sketching by hand because I don't want them to be constrained by their coding abilities. So the first step in making a graph is to sketch it by hand, and then we talk about how can we make it look pretty. But sketching is really, really helpful. I highly recommend you to have kind of an image of what you're working towards. All the prospective PhD students I've talked about, or current PhD students that have come to me to talk about the statistics and data visualization, in every instance, I was like, okay, what is it that you want to show? Like, describe to me your ideal graph, and then we're going to talk about how to design your experiment so you get the data that you want to show, and that will allow you to either find or not find the pattern. Okay, so what I want to do for the rest of today's session is I want to kind of turn it over to you a little bit and see what are your interests, what type of data are you working with, what type of effect sizes are useful for you, and then I want to brainstorm how we can make effective graphs from them. So is everyone happy to kind of maybe take a couple of minutes to either think of an example of like a study, maybe it's data set that you've collected or a data set that you found in the literature, and try to see, did the paper talk about an effect size? If they didn't, how can we rephrase the question so that it does talk about an effect size? And then how can we actually design effective figures to show what the effect sizes are and what the uncertainty on them is? Is that clear? Is everyone happy? Okay, so let's take 5. Let's start slow. Let's take 5. Everyone kind of try to think of a paper, or should we open the door? It's a little bit hot in here. I'm having a hard time. Yeah, I can just prop that open. Okay.
So actually we find a paper that describes what we are talking about, we knew what we want to do. Sorry. So let's say how we want to design our own research or a paper that exists. What would you like?
Either.
Okay.
So either you have a paper that you really like,
Yeah.
and maybe they're just a little too statistically significant.
Yes.
And you want to think of ways of presenting that data set in a way that's less kind of reliant on statistical significance.
Okay.
Or you have a hypothetical research.
Yes.
And you want to kind of ask a question and kind of think about what questions can we design around it? What effect sizes are useful?
Okay.
So either.
Okay.
Either an existing or hypothetical.
Actually, I have an example. If
Great.
yeah. So for my project, I'm constructing, let's say, a strontium baseline, a map of Nicosia, of the region around Nicosia and the city as well. So what we're doing, actually, we are trying to map the different geological formations that you can see in the area. I have collected samples from those different geological locations, and we want to see what variability we have with strontium. So it would be really, really interesting to actually ask you what kind of statistics you think match with my question. Maybe I was thinking actually about the p-value, but now it's gone. It's an X. So that's one of my things, let's say, that I'm doing at the moment. It could be variability of the different samples that I have taken. So I have taken different, let's say, plant samples that I will analyze, but also I've taken rocks as well and soil. So it could be, let's say, a differentiation between the results I get from the different samples. Yeah, that's one thing.
Would you sketch out a figure?
Yes, how it would look like, right? Yeah.
We can talk about
data. How visualize it? Yeah.
My own has to do with ceramics. I'm working on ceramics from parts of Nigeria. Actually, my purpose of being here is to have a standardization of ceramics in Nigeria and some parts of West Africa. So I want to see the various varieties across ethnic groups, across various nationalities. Later on to extrapolate to other parts of West Africa. So it will be very interesting to see, because it's very obvious now that I actually need this to be able to differentiate and be able to farm properly where does this particular ceramic belongs to. At what period? How do I look at possibilities of having this from this area and stuff like that? So you can give idea. No problem. No problem.
What would your figure?
Can you actually say, before even getting your results back? For example, for mine, it's going to be lithology on the X, I think, and strontium on the Y. That's something that I'm thinking. Yeah, I'm not sure actually how it would look like, but yeah. Yes. Mm-hmm.
Have the strength of isotope ratios and And then
They can't hear you, yes.
yeah, I mean, so this part is very hands-on. I'm not sure how useful it would be for people who are not actually here, because basically what we're trying to do is we're trying to imagine ideal graphs for research. So if you have an idea for a question you'd like to investigate, what is the end product that you want to be working towards? So one of the questions is about how do you visualize strontium isotope ratios? What is the best way to show variability in a landscape?
Yeah.
So we're talking about sketching different.
So strontium and geology. So yeah,
Strontium.
different, let's say, lithologies and different plant samples, and the values that they get at the end. So yeah, I don't know.
And you could even divide it into different, so there's geological zones.
Yes.
Right? And then
Yes.
within the zones, you can have different types of samples.
Yeah, exactly.
Yeah,
Exactly.
yeah.
I've got 3 different types of samples. So it's going to be bush and it's going to be grass and tree. And actually not 3, it's 5. It's rocks and soil as well. So it's 5. Yeah.
So if we think about effect sizes are about like where's the true mean, or like where are the true values most likely to lie, and what is the variability on it. Something that would be interesting in that case is to show like you could have different geographical and geological zones, and within you could have like, let's say, the water values, soil values, rock values, and then an overall value of all 3.
Yes.
And then see if maybe in every instance, the water is just a little bit higher than the rock, or maybe it's lower, or maybe it's kind of all over the place because you.
Okay.
It's
Okay. So an overall value for, let's say, every different geological category.
Yeah. And then have a confidence interval on that.
Okay.
Yeah.
Okay.
Absolutely. Oh, there's air. I like this is much better. I'm gonna try to sketch it or imagine one on my iPad here.
Yeah. Okay.
I haven't done anything. I mean, any kind of thing.
Also, that's variables.
We also went to
All right, should we try to regroup a little bit once everyone finish your conversation? All right, so let's first talk about effect sizes. I wanna see what types of questions you have or you're interested in asking, and then what are the effect sizes that we can actually measure. And then I want to talk about how to visualize them, but throw effect sizes at me, right? I've already shared with you some of the ones that I use. I measure stable isotope values, and one of the effect sizes I'm looking at is that amplitude of those oxygen values from teeth. So I have like maximum, minimum, that's an amplitude. Amplitude is a really nice way of looking at seasonality. So that's an effect size. Another effect size would be using delta 13C value as kind of a one way of looking at diets. What other effect sizes are there? Don't be shy. Go for it.
V for the nominal variables, we use it in chi-square analysis to see if the association between the variables is actually strong or not.
Absolutely.
Because it may be significant, but still not strong, especially with small sample sizes.
And I would actually call that like a test statistic. So
yes,
I think that's like how like strong correlation is, that's a test statistic. Absolutely. An effect size, I would say, is something we actually measure. So like if it's like the length of a femur or like the height.
But it is effect size, right? Kramer's V gives you the effect size. It is a test statistic, but it is an effect size.
It is an effect size, but in like the strictest sense of in the way that I'm using effect sizes, I'm talking about it is things we measure. So variables that we measure are effect sizes, and then anything that like a model outputs to you that would be like
okay.
Yeah, but maybe it's a test statistic for an effect size.
Yes, exactly. That's exactly what it is.
But I want to have a more broad definition of effect sizes, like anything you can measure. What can we measure? Someone mentioned looking at like different ceramic types, right? So you could look at proportions. You could look at proportions of maybe ceramics that have manganese in them and ceramics that don't have manganese in them. So now you have a proportion for like period A and proportion for period B. You could look at the difference in the proportion and then have a confidence interval on the difference. So that's absolutely an effect size. You can look at what else is that? We talked about strontium isotope ratios, right? So that's oh.
Well, as we were saying before, so strontium, let's say in early childhood, and then later on when the tooth is formed, fully formed.
Yeah, absolutely. And a good effect size to look at with strontium is like actual differences, right? Like if you have some like local people, or if you have a defined local baseline, and then you're trying to compare people from an archaeological population, try to see if they fit within the baseline or if they're outside of it, you can actually calculate the difference between your individual and where the baseline is. The difference is going to have an uncertainty on it, but we need uncertainty to better communicate kind of how confident we are in saying where the true value is. But like calculating those actual differences, we don't do that enough, but I think it's really useful. What else there? What kind of effect sizes do we have in, like, let's talk kind of very, I don't want to say basic because it makes it sound kind of simple, but like, let's say traditional, like archaeobotanical or archaeozoological analyses. What are the effect sizes that we can use to talk about what we have in an assemblage there? It counts, yeah, absolutely. Yeah, frequencies, and you can very easily convert a frequency into a proportion. As long as you have the total, you can have a proportion. So then you can talk about proportions of cattle in period A and proportions of cattle in period B, and then look at differences. Absolutely. I had a student do their assignment on meta-analyses, and he was looking at the proportion of faunal remains, of domestic faunal remains versus wild faunal remains in Norse assemblages in North America. So he knew when agriculture started in North America, and he wanted to see how do we see that switch from kind of reliance on wild resources to reliance on domestic resources. So literally compare the proportions of domestic to the proportions of wild and how that switched over time. So that's a really nice way of kind of quantifying that change. What else? What other questions can we ask in archaeological science? What else can we measure? What can we do with, well, let's talk about, let's take like metallurgical data, like chemical analyses of like metals or glass or ceramics. What can we do there? What kind of effect sizes, what kind of measurements could we use to answer very specific questions about production of these different materials? Don't be shy. Go for it. Yeah, absolutely. And so yeah. And so oftentimes, like analyses where we have a lot of chemical data, like lots of different columns, lots of different elements, a very common way to look at patterns there is to use like PCA, principal component analysis, which shows us kind of clustering. And that's a way to go about it. I'd say that if you have a very specific hypothesis or a specific reason to think that maybe there was zinc in this material, but not in another material, or zinc increased through time, I would actually look at the proportions of items, like whether it's glass or ceramics or whatever that has that element, and see how the proportions change through time. So looking at clustering, really important to look at compositions, but pure old proportions, they're helpful to see kind of what might be happening through time. And especially if you put a confidence interval on it, like it allows you to talk more about the population from which those materials derived, to talking about kind of, or using what you have from the sample to talking about the population. Yeah, go for it.
Histograms for different metals, different chronological periods.
Yeah, absolutely. So histograms of different of compositions of different materials. Absolutely. Histograms are really useful to look at distributions of things, right? So like what are the compositions of element A versus element B, element C? And you can have different histograms for different periods or from different materials or different forms. Absolutely. For histograms, one of the things that I highly recommend is to kind of think about the groupings, right? There's lots of different ways that you can group histograms. You can group them by chronology, group them by type, group them by like change through time, but you can have the same types next to each other, or you can have chronology next to each other and then like color code them. So the most important thing to keep in mind is the question. Like, is the main interest to show change through time, or is the main interest to change like what is the composition of my ceramics versus my glass or whatever? So the question is something is coming up in here. Unable to establish secure connection to Zoom. That's weird, but it's still, are we not sharing? No, we are, because it's on the, okay, interesting. All right. Where's good? Yeah, so there's different ways to organize histograms, specifically if you have a lot of groups. And it, okay, unknown error occurred. That's not ideal. Okay, I'm gonna stop sharing here and I'm gonna reshare. I think it's my internet connection, because it's saying, maybe I've been connected to the guest account for so long, so it's asking me to reconnect. I think, okay, welcome, guest Wi-Fi. Okay, all right, I think I'm on. Done. Now I'm gonna click on the workshop link. Wow. Passcode. Passcode, where is it? Okay, join with computer audio. And I think now if I share again, sharing is not, well. I wonder if you might have to make me a host again, because it's saying that I don't have permission to share. But also, I don't have that much to actually show. This is more like talking and brainstorming ideas. Yeah, maybe we'll keep it on. Okay, maybe. Just the video. Yeah, I had like one more slide, but it's saying, okay, share. Okay, now we can do it. Fine. All right. Okay, so I wanna keep talking more about effect sizes and idle graphs. What other effect sizes are there? What can we actually measure? What are the questions? Is anyone using stable isotope values for like diets or mobility or climate patterns? Yeah. Yeah, so looking at two variables at the same time gets you into the territory of looking at correlation, right? So if you're like plotting something on the X and something on the Y, carbon, nitrogen, usually the reason behind a scatter plot is to show if things covary, right? Like if X goes up, does Y go up as well? That's not how the CY plots have been designed in like isotopic studies. They've been designed to kind of show clustering, but in like the true sense of the word, scatter plots their main function is to show correlation. If X goes up, does Y go up as well? And how strong is that correlation? So technically, it might not be as useful to show stable isotope data like that, but it's just been so common. Like people have been doing it so commonly to show the clustering. But there is a case to be said about graphing like carbon separately to nitrogen, right? Like I've done it at some studies where I measured both, but what I really wanted to focus on is like, what are the actual values of nitrogen? Are they going up through time? What is the variability? And for that, you could just do like a univariate plot, right? You could have your categories, your species on your x-axis, and then your delta 15 on the y-axis, and then you can characterize that variability better.
variables within your part, for example. Because I want to compare diet between A and B, and whether I know there are factors in A.
Yeah.
So I want to compare diet, and I want to factor for age of death, or possibly social status, or any other factor, for example. An individual who experience stress during childhood, just repeat that. Maybe I want to also factor for this variable also.
Yeah.
So is it that it becomes too much, or do you think?
Yeah, how do we deal with it? So the way I would approach this is, it sounds like the way you're going at it is you have lots of different variables and you want a model that's going to tell you like which variable is explaining another variable, right? That's like one way of going about it, like designing a multivariate model. And that's a way of doing it. Another way, which I highly recommend, is to break your approach down into smaller objectives and literally spell out like what relationships are you interested in? Are you interested in like if delta 15N goes up, does your stress on your teeth go up? Like those are very specific relationships that you can then test. So yeah, go for it.
I think it's great and that with a very large number
of questions. Yeah.
This is why I responded. So it's fine maybe one at a time.
Absolutely.
Progressively, I was wondering if you heard about like just
yeah.
still being like this thing class. But yeah.
Yeah, it's possible to do a lot of them. People who are like really into open science and really trying to like avoid p-hacking and avoid doing like questionable research practices will tell you that you need to spell out what graphs you're going to do before you collect your data, right? Because if you collect your data and then start creating lots of different patterns and what you actually graph is very much guided by what you're seeing, it's exploratory analysis. It's not bad, but it's still exploratory. If you want to say something more kind of hypothesis driven, you should spell out those relationships beforehand, right? You should say, I want to see, is there a correlation between stress levels and levels of, I don't know, zinc in bones, and then look for that. So if you spell it out beforehand, no one can say that you cherry pick that relationship because it showed up to be significant. And it's a little bit more, it's more tied to the variables. Like always ask, like, what are you measuring? What is the variable? And yeah.
Because we know that everything is basically factorial. Because we know that everything is basically
multifactorial, and when we isolate for one variable, so when we look at the difference between males and females, for example, we already know that this is too simplistic. There are so many other variables at play. There is their social status, their family, their occupation. There is so much stuff going on that what I'm thinking is that some of this stuff might actually affect your original comparisons. So when you make your original comparison, you want to see if there is any sex-related differences. Maybe there is another variables that you don't know. It is actually affecting your results. And it could be the occupation, the social status, the health, anything related to literally anything. So in my cases, I was trying the attempt I want to show, but maybe you're actually right. It could be like exploratory. It was more about like making sure that my results were not biased by any other variables that we are not considering in the main comparison.
Yeah.
I don't know if it makes sense.
Yeah, it does. It's always tricky though. And considering how there's so many factors, like everything, especially looking at like diet or health, there's so many different things that are kind of, you know, the strings attached to them. The challenge there is if you don't like spell out a variable ahead of time, you might not be like measuring it in a way that's actually allowing you to like identify it as a confounded variable or like properly control for it. It's good to take as many observations as you can, like along the way, like record everything that you could be recording, but to actually look at like what comparisons are meaningful or not, it's best to have questions, like to have hypotheses ahead of time rather than measure lots of things. Like a lot of people measure tons of variables and then compare everything against everything and then have this correlation matrix, and some things in that correlation matrix light up as significant, some not. That's cherry picking, right? If you then go in and only look at those correlations that light up, that's the definition of kind of being biased by what your data is showing. So I'd say that the way to deal with all that, like being worried about, is there a variable that's affecting my results that I'm not controlling for, is to just look at the research context, right? Like, what do we know about how much stress affects diet? Or what do we know about social differences or class differences that might have an impact on like stature or something else? And kind of use our knowledge of the background research, our knowledge of the context to kind of frame our questions. But it's not easy, but I would say don't be afraid to ask questions that might sound simplistic, but that have a very straightforward relationship, right? Like if you're like it's okay to ask, is there a correlation between this one isotopic value and stress? Like that's not a simplistic question. Like that's a good question. There might be other variables that kind of come into play, but that's where those error bars like encompass variability and kind of bring in the acknowledgement that it might not be as straightforward. Like you're not going to get like a one-to-one relationship. Does that make sense? Like a little bit? Okay, cool. Okay, I want to know about your ideal graphs. Would anyone like to describe your ideal graph? And I've sketched a little bit about what we talked about, strontium isotope ratios. So this is hard to show. But so we talked about measuring strontium isotope ratios from different geographical regions and from different zones. So I've got my different zones, zone 1, zone 2, zone 3, and then I've got my rock values, my water values, and my plant values. I've got them color coded so it's easier to pick them out. And then I've got an overall value that represents all the variability encompassed in the water, in the rock, in the plants for each geographical location. And I think that's a good way of looking at variability and establishing local baselines, because it's geographically specific. And then you can compare any individual to this instead of just having one line. Also, don't have a baseline be just one line. There's always an error bar on it, right? There's always an interval. Yeah, so that's one way of looking at it. You could group it differently. You could group like all the rocks together and all the plant values together and all the water values together. But then what are you actually answering, right? Like that might not be as useful.
I think I would like to do it this way. I mean, different lithologies and the different samples that I have taken, I think is the best way. And then to take it further, when I actually compare it with actual, let's say, skeletons, archaeological samples, then I do it the same way as well. So meaning I've got the different lithologies, and then we have the different individuals with the different values, and let's say a mean value from all my samples that it's let's say how do you say it? It's the actual value of the lithology of the site. That's how it would be.
Yeah.
Yeah. Okay. So a mean value of everything, correct?
Yeah. Or
Yeah.
value per like group. Like if you're looking at group, like men, women,
Yeah.
Children, or
Yeah. No, I mean value of my proxies.
Oh, yeah.
Yeah.
I'd say you can present the mean value of each proxy in a region, but then I'd have one for the whole zone.
Yeah, that's what I was thinking. One for everything. Yeah. Yeah.
Totally.
Yeah. Okay. But how do you know which proxy is more representative of the?
That's a good question, right? Like, we don't always have the luxury of having all the samples we want, right? Like usually water is not measured as much as we measure like plants.
Actually, I'm not going to measure water.
Okay, there you go. So we're talking about plants and rock, maybe.
Yeah, rocks and soil.
Yeah. You could plot them both and kind of take into account that like superficial sources are really, really important. We don't pay enough attention to them. So usually we talk about strontium being completely driven by like the underlying bedrock.
Yeah.
And that's right to a certain extent. Like superficial sources like dust or aeolian pollution or like water can be bringing things in. Like there's a lot of things that are happening superficially that might change things in terms of what is bioavailable. Yeah. But that's where the plants and measuring plants come in. So
you think I shouldn't get a mean value for all my proxies together per lithology, right? Do you think it would be better to differentiate them and keep them as they are? So mean value of the plants, mean value of the rocks, and mean value of the soils, and compare my archaeological samples with this? Or get a mean for everything?
I get a mean for everything within the zone.
Yeah.
Just so you know, like what's the most useful, what's the best way to capture variability for that zone. But then for those that are interested in like how do the proxies differ? Maybe they won't. Maybe the rock values will be exactly the same as the plant values. So then you'll have more kind of ground to talk about like, okay, there's not too many superficial sources that we need to be worried about here.
Okay. Sure. Perfect. Thanks.
Okay, I think there's a question here. Let's see. I have papers that could be useful for this. Oh, thank you. Let's open them. Not my papers, papers I have read. Thank you. Where are they opening? Maybe the person who asked the question, would you like to provide a bit more context on like what your interest is, what the questions are, what the effect sizes are? So sampling plans and okay, implications for isoscape mapping. There you go. This is the paper on mapping strontium variability. Are you on the Zoom? If you're not on the Zoom, I can copy these links and then share them. Or maybe Andre can copy the links. Someone just shared a link that would be really helpful for Despina. Thank you. Yeah. What is it? Oh, like, yeah. It's called sampling plants in Malacofauna. I've never heard that word. Oh, okay. Oh, very cool. Nice. So, yes. Yeah. Nice. Great. Awesome. Wonderful. All right. Yeah. The person who sent the, okay, I don't know, like, can I share this? It's someone called Phoebe. Despina says thank you. Yay. Awesome. All right. Well, we should probably wrap it up. Like, I'm very happy to talk about more, like, if you guys want to bounce any ideas around, talk about effect sizes, talk about types of graphs. But if, oh, you're welcome. Like, should we keep talking or should we kind of wrap things up?
Would recommend we wrap things up now.
Okay.
Petra will be with us tomorrow. She has a seminar at 10, but she will be in the Cyprus Institute all day long. So if you want to discuss more with her, you're very welcome. She is staying this extra day so that we can take advantage of her. So do come in. As she has kindly said, for the people online, you can email her. Okay, let's not abuse this invitation, but
I'm gonna put
do email her if you have a question, if you want to discuss something more specifically with her. So I would say with this, thank you very, very much, Petra. Thank you. This was really informative.
Awesome.
A lot of information. But as you said, okay, you planted the seed. You planted a lot of seeds, I would say, today for all of us. But thank you very, very, very much for this.
Yeah.
And we're looking forward to tomorrow for the case study.
Wonderful. Well, thank you so much for having me. This has been lovely. Yay.